So here are the organizers. I am one of the co-organizers of this workshop. My name is Nalin Miran. I am an Empire Innovation Professor at the University of Buffalo. And I have with me here Quan Chuan Feng, who is a research scientist at MERL, and rest are offline, not in person here, but we are a team that have contributed to the success of this workshop over the years. Prior to this workshop, we were running two different workshops, one on fairness, one on the data efficiency, and one on trusted computing for computer vision. So all of them have merged together in the last 5 years to make this workshop where it is today. So just few logistics. As you know, your Wi-Fi details are right in the back of your registration card. So that's the Wi-Fi part. Then we have few coffee breaks and lunch break. And all of you probably had the same experience this morning looking for breakfast in this building compared to that we were asked to go to the other one. Luckily, it looks like the coffee is going to be here. And so we don't have to waste 20 minutes to go there and come back by the time the break is over. So it's not, so we will meet here for the coffee, and the poster station is at the end upstairs as well. So those are the lunch break is at 11:50 until 1 p.m. So that's sort of the more of the logistics that we are going through. We will have speakers in person as well as remotely. And so those of you who are presenting papers, you all received your in an email, the Zoom link. Please log in to the Zoom so that the people who are attending remotely can also view your presentations. Okay, so we are still waiting for the keynote speaker at 9 who was supposed to speak, as I mentioned before. So he's probably lost in between somewhere. In view of time, we thought we will try to get started with the regular paper presentations first, so that we all can save the time instead of pushing it beyond the time that is allocated to this session. So we have 4 sessions: before lunch 2, after lunch 2, and at the end at 4:30 we have the poster sessions where you can have more detailed interaction with the participants. So that is the overall framework that we are going to have this morning for the workshop. So we will see through as we go through different sessions, and then we are expecting.
Yeah, he just called me. He's still is somewhere in Summit, so we will start with the regular paper presentation first.
Okay,
he's coming
so
here.
At least we know he's
still alive.
We are going to see him at that time. I will come back and introduce him, and we will go through it. Right now, let's go with the speakers of the first session. And the first paper will be diffusion-based inverse network attacks on collaborative inference.
Shared screen. Shared screen. Share your screen. Stop this. Share. Okay.
Right. So, good morning, everyone. So, good morning, everyone. My name is Chenghao Li. I'm from the University of Southern California, and today I'll present our work, which is DIA diffusion-based inverse network attack on collaborative inference. I'll follow this content today. So let's begin with the background, the background of private inference. Private inference allows the client to utilize the machine learning model without exposing their privacy data. So the collaborative inference system split a neural network into two parts. First, the client holds the initial segment, and the server handle the remaining parts, which requires more computational resource. This division aims to balance the computational load between the client and the server. However, during this process, this process involves exchanging or sharing the intermediate feature with the server, which introduce the privacy leakage or privacy other risks. So during this process, the client sends the intermediate feature to the server. So although this feature do not directly reveal the input data of the private data, they contain enough information that the adversary can potentially reconstruct or recover the original input using the inverse attack. The reconstruction is achieved by training an inverse model to map the intermediate feature back to the original space, which caused the privacy issue. So the existing inversion attack has several shortcomings. The first is poor recovery at deep split point. So unsatisfying the reconstructed result from deep split point due to the insufficient generating ability of simple scenes. The second is the leak of data distinction. The previous attack model and the target model often use the same data sets to train, failing to mimic the real world scenery. The third is many attacks focus on simple scenes nowadays, but not addressing more modern architecture like the ResNet or Vision Transformer. So to enhance this reconstruction, a more proficient inverse model with generative capabilities is required. So conditional diffusion models such as the stable diffusion has nowadays shows the superior ability in generating diverse and high fidelity data across various domains, making them potentially suitable for this task of generating lost information based on the intermediate feature map. So motivated by that, we propose the DIA that use a diffusion-based approach to address the inversion attacks. So now let's dive into the detail of DIA. So first is the feature map guidance mechanism for the diffusion process. Previous scene-based inverse attack use the feature map that they stolen from the client as an input directly. But in our work, we use that as a condition for the diffusion process. Starting with the random Gaussian noise, the diffusion process is iteratively denoise under the feature map condition, and finally reconstruct the privacy data. Then is the companion network design. As shown in this figure, the bottom branch corresponding to our companion network, which only accept and process input from the condition Y. So the stolen feature map is first put into the encoder network to perform parameterized reshaping of Y to match the dimension of the original, the original diffusion UNet input XT. Then each downsampling or upsampling layer in UNet, in the original UNet, has a corresponding layer in the companion network. And the output of each companion network is concatenated with the output of the corresponding layer in the UNet along the channel. This companion network provides conditional guide throughout the propagation process, especially during the upsampling part. So we target three types of target model. A basic 6-layer CNNs, the ResNet 18, and the VITs model, VIT models. And our attacker applied two types of data utilizing condition. First, we use a cipher10 to train both the target and the attacker model. The second, we use cipher10 to train the target model, but we use another data set with the same distribution, like the tiny ImageNet, to train the attacker model with removing the overlapping categories with the cipher10. So here is our experimental result. We evaluated DIA using 3 metrics: peak signal noise ratio, PSNR, structural similarity index measure, SSIM, and the mean square error, MSE. PSNR qualifies the pixel level recovery quality of an image. SSIM measures the human perceptual similarity between the 2 images, and MSE measures the pixel-wise difference between the 2 images. We compare our method with the previous approach, which we call the black box attack and the enhanced inversion network attack. Our result is shown in this slide. It shows significant improvement in reconstruction quality across CNNs, ResNet, and the VITs, and across 3 different metrics compared to the prior attacks, even with different split points. We also conducted an ablation study to assess the impact of dataset size on the attack performance, finding a positive correlation between the amount of training data and the effectiveness of our attack. So finally, in conclusion, DIA represent a significant advancement in inverse network attack, particularly highlighting the vulnerability of the VITs on collaborative inference system. Also, this work underscored the need for improved privacy preserving technology in machine learning applications. DIA helps address the privacy issue in machine learning application situations. It also arose information security concern about the popular VITs, calling for further privacy preserving methods. So that's all for my presentation. Thanks for your listening.
Questions? Unfortunately, we don't have a microphone here. So I guess
Yeah, if you have any questions, please come up to the podium.
So I have a question on this one. What's the attack model that you're assuming, or what is the attacker going to do? What does the attacker have access to in your approach?
The attacker, they, like, they have the output of the client side model.
So that means the embedding, I want access to, I give an image,
Yes, they can give an image and they can go through the client side model and but the client side model is a black box for the attacker.
so the underlying architecture is not known
Yeah.
to the attacker.
Yeah.
But you are using a ResNet and VIP to reconstruct the image, is that right?
No, we're attacking the ResNet or VIT, and we use the diffusion to as the inverse model to inverse the CN or the ResNet.
So I guess you're helping the attack.
Yeah. So we need to come up with some
No, what I meant was you are showing the weakness so that the designers can fix it.
yeah.
That's so you are, in the sense, you are showing the current APIs that are there could be vulnerable, and APIs have to make sure that.
Yeah. So we're not bad person.
Yeah, I guess sometimes it's the good person also has to behave like a bad person. But
Yeah.
So are there any questions, comments for the? If
I
not,
have a quick question, Nalini, if you can hear me.
Yeah,
Yes, we can hear you.
Very nice talk. I had a quick question. I noticed all your results are on, academic benchmark data sets and likely controlled settings. To see the benefit of what you're saying, I guess we would have to see how it works practically. How would your experimental setup vary if you go from a constrained public data set to a more practical application? Let's say a healthcare type setting where privacy is paramount, right?
So you're asking if there is a privacy data, if there is a privacy data set, how can this work?
Well, I guess my question is, how would you go from the evaluation that you've done on CFAR type data sets to a more practical scenario? Let's say we want to deploy your algorithm in a hospital, for example. What needs to be done to give confidence to the doctors there that you're actually maintaining privacy? I'm sure it would be more than going beyond the numbers you're showing here, right? That was my question.
Oh, so for example, in the hospital, the
Right.
attack should have to collect some public data set or public medical data to train the attacker models. So the data collected from the attacker have to go through the client side, and the attacker get the client side output and use the output to as a label to train the diffusion, to train the inverse model, like that.
Okay, sure.
Thank you.
Let's thank the speaker again.
So much.
also thank you for filling in now that we have our. I think they were.
So you will be on my. Oh, yeah. So we'll cue you after this talk. Oh, there's the talk.
Okay, So now that we have our keynote speaker in the room, we can, I'm delighted to introduce Dr. Liang Kao. By way of full disclosure, Liang and I used to be at IBM Research a while ago. So I know Liang's commitment and the level of excellence that he achieves in his work when we were there. But just to introduce him, he also has spent time at Google, and now he is a scientist, principal scientist at Apple. But before that, he was at Google, Yahoo, and as I mentioned, at IBM. But in addition to his industry research, he is also part of Columbia and UMass Amherst as an adjunct professor. And he has done significant work in the space on multimedia. So as you can see that he has won first place in LS-VRC Challenge in 2010. Then also that was purely on image. Then he moved to audio. Now he deals with full multimedia. So he is a kind of an expert in all spaces. He also has, he's now
You can share your screen.
AE for the IEEE transactions
Share
and
your
PAMI.
screen.
But today he's going to talk to us about scale learning in image semantics, a 15-year review. So please join me welcoming Dr. Liang Kao.
Thanks a lot for the long introduction. I'm still trying to figure out how to connect this.
Yeah.
Share screen. Yeah, it works. Yeah, you can start this. Okay, thanks.
Okay, thanks a lot. Thanks for the warm introduction. It has been knowing each other for more than decades. I saw the picture you showed. I think that's when I know you. Now we all getting old. So for the audience, so today I'm going to talk about what we learned, especially in semantic, image semantics, English embedding in the last 15 years. So 15 years ago, I think also at CVPR, the internet was released. So I was very fortunate to win the first place internet RSVRC challenge, and then was fortunate to work in IBM, Google with a lot of great, fantastic colleagues. So here is going to share what I learned there. So today I'm going to be fast. So first I will go very quickly from talking from internet to the recent clip. And share my thoughts mainly on the data lesson, how the old technology was replaced by the new technology. And they also show a recent study to discuss about the data and the modeling balance. So, and then hopefully we have welcome your question, comments. Internet was proposed by Jia Deng and Fei Li 15 years ago. So the images are crawled from web. The labels are refined by Amazon and Turk. So they made the challenge very friendly to the participants. That by the way, that all the labels are mutually exclusive. So they host the RSVRC challenge since 2010 until 30 years ago. So the challenge at the time was the largest in image classification. There are 1 million training images, 1,000 categories. If you look at the arrow bar here, the last one, the most left one was me. I work with NEC and the UIUC, where I get my PhD. And the next year, the technologies are similar. So we're still using the safety-based, the image descriptor, so-called handcraft features. We make the presentation very long, called a super long vector. And then the year 2005 changed. The new AlexNet, the deep convolutional neural net comes in, and then opened the door to dramatically reduce error rate. So 2014, the GoogleNet, and then 2015, ResNet, and later on, things just become more and more competitive. So after ImageNet, I think there are a lot of other efforts. So one worth mentioning is called Yahoo Web FCC 100 million images. So that paper was released 2015, but it's probably 100 times larger than ImageNet. And also in IBM, we also try to expand the more concepts. Here's a paper published in 2015. Here, we have a taxonomy and then build a lot of semantic models and use different semantic models to do the image search, so-called IBM research or IBM search IMAR system. And if we look at the other side, the other team also try to exploring the limits of weakly supervised pre-training. So the researchers in FAIR at the time called FAIR, now it's Manta, is trying to corral about 3 billion, 3.5 billion Instagram images, and then use this to train a very highly performed classifier on internet. At the time, it's close to 55% top line accuracy. So the lesson we learn is, although there are a lot of efforts, not all of them are popular. The lesson is the community prefers open source data and open source model. I think very few people is using Instagram data paper now because it's not available to the public. But on the other hand, scaling with more examples, more images, concept, and bigger models are not easy. It becomes challenging how to evaluate a large-scale model. I think WebFCC 100 million was a great example. That time was so good, but not a lot of people are purely building system are using that data. And because a lot of data overlapping issues, it's hard to benchmark general purpose models. So this paper, in fact, was very important for Google. That time was published in WFDM and it's called ultra fine grained image semantic embedding. So still in the setting of ImageNet, so they have many categories. When the paper was published, they have about 40 million fine-grained categories. All the categories are crawled by search engine. The examples can be bridge, or can be steel red bridge, or golden gray bridge. Although not all the categories are mutually exclusive, but if you do sampling, so getting a sample, getting a category, and a sample randomly 100 another example, very likely they are mutually exclusive. So we still can do sample-based classification. But when we scale the category to 40 million, from 1 million of 1,000 to 40 million, and then later to hundreds of million, the embedding just become very popular. For almost 10 years, this is the most, in fact, it's Google almost unified their image embedding. Purely use this method, and this method has been dominating a lot of things, image search, and a lot of other things in Google. So not public data, not public available, so probably not so well known to the external world. But that's a success, I think, showing how much data, how much benefits data can bring us. Then fast forward, another revolution comes. So this is a clip published by OpenAI in 2021. The idea is very simple, just crawling all the web images with the surrounding text. They just try to compute the contrastive loss between the image and image embedding and the text embedding. The idea is if there is a text, then must in some semantics related to the image it's showing. Although there are a lot of noise, but surprisingly, the computed results is so good. When computed train the contrast loss from hundreds of millions of image text pairs or even later billions of image pairs, they get embedding, and using this embedding, they can do zero-shot classification. So that means they don't need to say category 1, 2, 3. You just say, oh, is this close to some category? Next, I can show how to use this embedding. Let's go back to the early days of ImageNet or AlexNet. I found this image screenshot when I worked in IBM. So at that time, we take the last layer of AlexNet, and then we give 3 or 4 images per category and train on linear cluster on top of that. And then for this new cat, we can categorize images and give the label. So at that time, it sounds like easier, but pretty easy. But with CLIP-like models, things just become more popular. More powerful and more easier to use. This one was still from the same ultra fine-grained image classification team. So they show that CLIP-like model can directly use for text to image retrieval. So you can put the text on top, like looking, hill, spider, and night. It's pretty complicated query, and then search for the images. Similarly, we can use the image to get the text, or combine the image plus text for image retrieval. Most surprisingly, I think, is the last picture. So it can give a query as image, high heel shoes, plus some text query like beige, red, or purple, the colors, and then combine this query for search. The reason why we can do that is because now the image and text embedding are the same subspace. So we can use this subspace, unify both multi-model information to do the image retrieval. More like if you look at the few shot situation, previously we need use the last layer of AlexNet or ResNet to train a linear classifier. We can still do the similar thing for CLIP, but the difference is now with CLIP, we can use the text category information to initialize the last linear classifier. Because image, fundamentally, we are computing the inner product between image embedding and the text embedding. So we borrow the text embedding or the category names, and then initialize the classifier, and then choose even one example or 0 example can do the job. So this figure shows that they can use different kinds of representations for category. So in the old days, in ImageNet, we use category 0, 1, 2, 3, class 1, class 0, class 3. And then now we really can use the category name. So now the text semantics matters. We can use the English text name or even multilingual text name, Spanish. And both English and Spanish can do a pretty good job. For one-shot learning, I think we are showing that we get much better compared with the original category name. So just give us more power to explore the text of category word compared with the image embedded only. And we should mention that CLIP's success benefits not only that OpenAI paper, but also the whole field. So one paper I think very important for CLIP and now society is the vision transformer. And the CLIP now more and more teams are building CLIP using the backbone as vision transformer. So vision transformer is motivated by the transformer from GPT, from natural language processing field, and it can scale to allow to a large scale training data with the potential of utilizing the infrastructure built for natural language processing speech recognition. So CLIP sorry, vision transformer is the benefits from the modeling side. From data point of view, the Lion 400 million and the Lion 5 billion are public shared data sets. The author crawl the data, crawl the web image web, and by getting 5 billion image taxpayers and share with the whole world and benefit a lot of public research. So I think I go very fast from ImageNet to Lion 5B. So if we look back now, you can see in the last 15 years, the training data just grows bigger and bigger. The ImageNet RCRC challenge with 1 million images, and then the FCC 100 million. Google has GFT 300 million. Of course, now it's still 100 times or more than 100 times bigger. Meta provide Instagram 3.5 billion. And the most important public data set these days are the Lion 400 million and later Lion 5 billion. And many teams, because of the legal issues, many companies, many big teams are building in-house collected data sets. And if we look at the data is one side, but the model evolution, that's even more competitive. So 15 years ago, we get the super vector trained from handcraft features like SIG and HOG, and then quickly replaced by AlexNet and then ResNet. For mobile applications, I think MobileNet still useful today. And nowadays, people move to Vision Transformer, and then later we have more Vision Tokenizer. And if we look at the system we built, spent a lot of huge amount of effort by a lot of engineers over multi-years. The ultra fine-grained embedding was very successful for 10 years, and then now people move to Click, which is easier to understand, more scalable, more scalable more easier to train. The loss, in addition to the backbone, the loss of the change, we have multi-class, most simply simulation. We have the multi-class cross entropy, and then nowadays two contrastive loss, sometimes combined with caption loss. So looking back, what we can draw a conclusion. What kind of conclusion we can draw? So I decided the data lesson. I think Rich Sultan is a pioneer of reinforcement learning. It's a very short but very popular paper like essay called the beta lesson. The beta lesson is try the seeing that since the early days of AI, like 1970s, we have seen again and again that the great power of leveraging computation of data. So traditionally, the specialized method will always be replaced by general method that leverage computation. And because learning, because search can use the data to power the new method. So the new, always there will be new things. So even today, I doubt Vision Transformer or Click is the ultimate solution. Probably in a few years, there will be new things. But come to the workshop today. So within the big picture that learning from more data, is that possible to learn from smaller data for better accuracy? So next I will discuss a recent study, very simple study to show that it's possible. And the reason I want to share this study is not only because to talk about this study, but also to think what's our strategy these days, considering the last lesson learned from 15 years. What's the challenge and what's our strategy to handle this? Okay, before I move on, any questions? Feel free to comment on future lessons. That's sometimes controversial, but interesting to discuss. Okay, if not, then let's move on. So let's look at the Click embedding. So the first row on the picture is just a simple image. And when compute the image clip embedding, we trained from in-house data with all kinds of categories. We compare this image embedding with the DAC, goose, hen, gauze. So the gauze is non-word, but just showing that it's possible to compute the similarity. Of course, this is DAC picture. So the similarity, the closest category is DAC. But if we put the new text onto the image, this is a goose. And then if we compute the clip embedding again, and then compare the image category similarity, we found that, oh, now the goose is the most similar category. So why? Because the clip was trained by image and the text embedding. So as a result, sometimes it learned how to do the OCR implicitly. So in this case, the OCR recognize the text goose and then say the overall similarity similar with the image with the goose. Although it's a dark picture, it's closer to the text image. Sorry, the goose category. And even more interesting, if we add a nonsense word like G ** O --O SE, it's not goose, but still the clip model thinks the image is more similar with goose after we add these random words. So what can we do? So this one is probably, we don't have any public benchmark to measure this kind of misunderstanding. So what we do is we build a new evil set to study this problem. What we basically doing is we get internet evaluation set. And then for each image, we look for the most confusing category and then put that category as text and then move the text at a random place in the image. So there are about 50,000 images from internet 1K evil set. Now we get about the same, not exactly the same number of images, just with the text. So we call that internet with adversarial text embedding with text or adversarial text. We call the internet ETR. So this data set is publicly available. So if you use the we did have AXLearn, so under Apple. So we put out the script to prepare this data set and just download. People can go to there to download the data there using the Tensor TF record format. After we prepare the evil set, we borrow the OpenAI clip model as well as the Lion public open trained clip model. These two models get pretty decent top-down accuracy on the internet, like 68 for OpenAI clip and 66 for open clip model. They all use the small, not the biggest one, but just for easy evaluation. But we apply the same model to our new evil set. You can see the top one accuracy using zero-shot learning dropped significantly. From 68% dropped to 31%, a little bit more than 31%, or lower than 30%. The question is, how can we do that? Doing better, in fact, is pretty straightforward. We look at all the training data we get from Clip. Our in-house building at the time, we have 1.1 billion image text pair. The reason we have this text pair is because of licensing issue, we cannot use the Lion 5V in Apple. So after looking at this, we found that about 40% of these image text pairs has image regions. The image regions can be the crest, the picture on the right, crest, or some logos on the T-shirt, or even some the gold in the last picture. So what do? We just compare different versions. We can take the original image, remove all the image text pair with text regions, then we get about 700 million images. That's a filter 0.7 billion. And also we can get same size image, EVO training data set by sampling, or we just do the blurring. And how this is the result we get from the training. So we get the first table on the right, table 4 here. You can see that by filtering, we can improve the internet training data and also improve the accuracy on our new EVO set. This is surprising because we are basically training with less data and improves not only internet, not only our new EVO set, but also the original set. We get 2% better, which is pretty significant if we look at the training. And also we tried the COCO. We tried the linear plotting with the linear cut on top of that. Still, filtering get about 700 million examples, still get less performance. So here gives us example that the less data, but give us higher accuracy. Then the question is why? Because intuitively speaking, because the contrastive loss get distracted, it's hard, it's not an easy job to learn the OCR if we just compute the contrast loss. So by removing the image with text, basically the model can focus on more overall semantics instead of doing the hard work. And also explicit reason for the experimental result is because ImageNet or COCO evaluation set has nothing to do with OCR. So if the EVO set is not related to OCR performance, then removing the extra data, irrelevant data, help the model become more efficient. I want to quickly summarize discussion and open for comments. So if we look at the last 15 years, the data lesson is there are always new models. As the author of data lesson says, general method that leverage more data, a bigger model are ultimately most effective one. But interestingly, if we look at the simple experiment, it just show that we can potentially not learn a more efficient model, click model with less data. Why that's, how to explain this? I think the fundamental reason is because evaluating large general purpose model is hard. So of course, there are a lot of problems. There are multiple metrics. It's easier to say we get improvement in a certain metrics, but not better in other metrics. So in our case, because ImageNet, COCO, they are all now related to OCR. So we removing some data does help. But instead of focusing the experiment, the bigger question for the future is twofold. One is how to evaluate. Another is how to scale up. Because until today, clip training or even the vision language training are not as scalable as the other field like NLP. So in natural language processing, we can use the transformer scale out to 100 billion or even more trillion level models, but scaling up vision model are much harder. If we do not connect vision model with NLP model, just vision model only, I think these days, most vision part or the vision model are limited by say 10 billion or much smaller. So the vision transformer probably need more work, or we need more ideas how to scale up vision models and how to do the model scaling more effectively. In the same time, we also need to suffer from difficulty that how to evaluate this model, how to defend ourselves by using so much resource, learning from so much data, and show the benchmark. That's it. Thank you very much.
Thank you, Liang, for a great inspiring talk. So any questions for Liang?
I had one, if
Yeah.
you guys can hear me.
Yes, we can hear you.
Very, very interesting talk summarizing pretty much, I guess, the progress that we've made as a community in the last 15 years. as we think of let's say moving some of these models to real user applications where we talk about practical deployment of models, I'm sure we come across many scenarios where we don't have the luxury to train general purpose models, right? We perhaps don't even have a few thousands of samples. And even if we have to collect a few thousands of samples, perhaps it is cost prohibitive to even gather these data samples, right? Maybe even to get one data sample collected and then annotated would be super expensive, right? And there are many such applications in industrial settings, right? Uh, how would you reconcile the progress the research community has made with some of these practical challenges as we deploy models for real applications?
Okay, thank you. I guess I heard a similar question several years ago when my PhD advisor, Professor Thomas Guang, asked me and also my colleague in Google similar question. So basically, I think these days a lot of research are consuming more computation are becoming more expensive. So academia researchers may feel it's hard to compete with the industry labs. I don't know. It's really hard to predict the future. And also, computer vision is not alone. I think we see similar trend in speech recognition. So speech recognition several years ago, I think a lot of great research teams stopped to compete with the Microsoft, IBM, or Google. So because the research just require a lot of computation. But if we look at another side, I think industry labs, including myself, also feel like less confident. We are not saying that we are beating or we are outperforming, say, my advisor before. We are in the pressure is we don't know what's going on, what will happen next. And we definitely need the suggestions or comments from the academia. Because building a big system and maintaining that is very costly. And also, if Manaset is spending on that, it's very hard to spend outside or embrace new ideas. So I guess that's the reason why I need to move from.
Yeah, thank you. Let's take one more.
Yeah.
Yeah. Can you come up to the podium and use the
Sorry, I talked too
microphone?
much.
Yeah, no,
Oh, no, because for the online attendees.
Yeah.
Yeah, please.
maybe we'll
yeah.
break it, so we'll turn it around.
Yeah.
Okay, hi. Yeah, my question was, so when you got rid of the data with text on them, the performance improved, but also if you evaluated these new models on OCR, then the performance would drop.
Yes.
So do you think that's something that's like an inherent problem of training with efficient training? So once you say you clean up some data,
yeah,
some aspect of your model would improve, but another aspect would fail. So do you think that's like that would always be the case if you're going towards efficient?
Yeah.
Methods?
As today, it's a great question. As of today, my recommended solution is to use an OCR, separate OCR system and the click model combined. So why? Because OCR is much cheaper compared with the click model today. So you have two models, one strong and heavy, another the more efficient. So instead of combining to one, probably you have more flexibility to have a separate OCR and a click model focusing on non-OCR model. Yeah, we can discuss more.
Thank you, Liang. I'm sure we'll keep him here for the coffee break so that he can interact with you all more as well. Let's move on with the next paper in the sequence.
So the next talk will be fast NTK parameter efficient on learning for large scale models.
don't have a HDL.
Oh, no?
Yeah.
Oh,
Do you have a adapter?
no, I don't. Adapter.
Do you have that or no?
Can you send a slide to me?
presentation to one of us, then we will host it.
Oh,
Anybody has an Apple adapter to hold?
2, 4.
oh, one of that, I present on Zoom and you project your laptop. You think it works?
Yes, you can. Yeah, I put your mouth. And then you share on Zoom.
Oh, yes.
Okay.
If you're using an Apple machine without HDMI, please send us your presentation ahead of time so that we can have. Or you have one, okay.
No, I'm projecting my laptop. And
She
then
has one for,
to see whether that works, right? Yeah.
okay, good. Thank you. If you.
So I don't need to unmute myself, right?
Yeah, you just speak here. Yeah.
Hello everyone, I'm Gui Hong. Today I would like to introduce our recent work, Fast NTK, parameter efficient on learning for large scale models. So as we know that we are living in a time of big data, every people is generating the data every second. And typically this data collected by some company or users. And this data will be used to train some powerful deep neural networks, such as the mentioned CLIP model that is trained on the internet collected image and text pairs. But because there are some concerns related to the privacy and some other issues like pornographic violence. So now some laws are published to give users the power that they can remove this data on their demand. And because deep neural networks are very strong, so they can easily memorize the data from the training set. So if we only deleting the data from database, it's not enough anymore. To solve this problem, machine learning is proposed. Essentially, machine learning is trying to selectively remove some unwanted data, or term that forget that here, without retraining the model from scratch. And in the meantime, machine learning will also try to minimize the performance drop on the remaining data, which is the return set here. So there are two perspectives we need to forget. Something we need to forget. In the meantime, we also need to remember the rest of the stuff. And among these approaches, neural heterogeneous kernel based on learning is one of the state-of-the-art approaches. Let's start with some background for the NTK first. Essentially, given the most commonly used setup, for a classification network as theta, and the network could classify C classes, and the parameter here is theta. In total, we have the D parameters for the given network as theta. And based on the network, the NTK matrix for two given data sets, D1 and D2, is defined as follows. If we break down the matrix, it's actually the product of two Jacobian matrices. So this is the basic stuff for the NTK. And based on that, the NTK based on learning is trying to do as follows. Given the return set dr and the forget set df, and we will use the equation in the middle to compute the unlearned with theta r here. As we can see here, because the computation here is one shot, so we don't need to train the model again. That's the benefit for the NTK. And according to the performance, currently it's one of the state-of-the-art learning approaches. But the problem here is NTK based on learning approach is pretty expensive in terms of hardware cost. So let's take a breakdown to see what happened in the mathematical. Here, I don't want to get into the deeply that how this is derived. We can only consider what's the basic component in the equation here. So as we can see, given the chain with theta, and the theta r is computed in the equation. So here we have three matrices, P, M, and V. And for the P matrix, there are two Jacobian matrices again. And for the rest, both of the P, M, V has the NTK matrix, which is the capital theta. And if you remember in the previous slide, the NTK matrix, they are actually the product of two Jacobian matrices. And so in general, the main part for the NTK based on learning is to compute the Jacobian matrix, as we can see here. So here is we want to solve the problem of the computational overhead of NTK based on learning. And if we take a deeper look to see the Jacobian matrix, the size of this matrix is actually the dimension of C by capital D by small d, where the C here is number of classes for the given task. And the capital D here is the size of the training set. And the small d here is the number of trainable parameters. So one idea is how could we reduce the size for this matrix? As we can see here, because given the training set and the task, the C here is fixed. In other words, we cannot reduce the number of classes. And also the training set is given, so the capital D is also fixed. The thing we can do is trying to reduce the value for the small d, which is the last factor in this matrix. And in this work, we are inspired from the approach called parameter efficient fine-tuning. Essentially, parameter efficient fine-tuning is trying to only train the important parameters other than fine-tune the model entirely. So what we do here is as follows. First, we are starting from a pre-trained model, and then we will fine-tune this pre-trained model on the downstream task or the target task. And when we fine-tune the model, we will use this parameter efficient fine-tuning approaches. And after the fine-tuning process, if we want to unlearn on this target task, then we will only unlearn this K parameters, which is involved in the fine-tuning process. And this way, we can significantly reduce the value for the small d, which is number of trainable parameters involved in this process. So more specifically, for the convolutional neural network, we only fine-tune the batch normalization layer. And here, using some simple math, we can show that by doing that, we can significantly reduce the number of training parameters for this process. And for the vision transformers, we leverage the prompt-based fine-tuning methods. And similarly, we can significantly reduce the number of trainable parameters. And now let's take a look at the results. In the experimental part, we start from the pre-trained model and we fine-tune on different downstream tasks. And we report three metrics here, and there are more metrics reported in the paper. So for the three metrics here, we show the accuracy on the return set. And here we should expect that the accuracy on the return set should not have a significant drop. That's the first metric. For the second metric, we also report the accuracy on the scatter set. Essentially, the ideal case is the accuracy on scatter set is 0. And finally, we show the accuracy on the general test set, which is trying to measure the generalization capacity before and after unlearning. And for the baseline, we commonly use the retraining-based method, which means that we retrain the model from scratch only on the return set, and currently is widely considered as a golden baseline. So as we can see here, if we consider the number of trainable parameters, our method only involves at most about 5% compared to fine-tune the whole model. And for the accuracy on the return set, that number is pretty similar to the retrain-based method. And for the accuracy on the general test set, our approach is pretty close to the retraining-based method, but our method is a one-shot based method, so the computational cost is significantly smaller than the retraining-based method. We also show the results on the vision transformer, and similarly, we reported the 3 accuracy on different cases. And if you look at the number of trainable parameters here, actually it's less than 1% for the vision transformer cases. And similarly, for the return set accuracy, it's pretty similar to the retrain-based method. And for the forget accuracy, both of our method, the retrain-based method is 0, which is as expected. And for the final accuracy on the general test set, our approach is very close to the retraining-based method for most of the cases, and sometimes it's a little bit higher. In summary, in this work, we introduced FastNTK, a novel algorithm for efficient learning for the large-scale neural networks. And specifically, we combine the NTK-based learning with the parameter-efficient fine-tuning approaches that we only fine-tune and unlearn these important parameters. And we show that FastNTK has much higher scalability than the vanilla NTK-based method. And finally, we show FastNTK could achieve a comparable performance compared to the traditional retraining-based approaches. Thanks for your attention, and please let me know if you have any questions. Thank you.
We just have time for one question. I think we are running a little bit late. We want to wait for. You tried on the CFAR10, and these are all smaller number of classes, right?
It's not only CFAR10, as we can see here, we also tried on the immediate retention system. So that one is a little bit larger.
Okay.
Yeah. And
yeah, go ahead, complete.
And I think the main part here is if you look at the original NTK paper, we only tried on at most 500 training samples. And here we can scale up to more than 10,000. So it's a significant improvement.
Sure. I guess please follow up with questions with the author during the coffee break. We will take the last paper of the session and
Yep, thank you.
Okay, thank you.
let's thank the speaker.
Thank you.
So next we have the paper presentation from ARCP, Uncertainty-Aware Perception in Adverse Conditions with Conformal Prediction and Augmented Reality for Assisted Driving.
Okay.
You don't, okay, then can you share the screen on Zoom? So I'll project my screen.
Just in the meeting. That's
The presentation.
548923914892391.
2391.
Yes.
We have this presentation. We're just gonna
I'll just project my screen.
Okay.
Yeah, you need to share the Zoom. And share your screen, please.
If you're one of the authors for the next session, which will start after the coffee break, we see that you are going to get your presentation.
Yeah.
Can run the concept of you.
No, the normal more. This trash. That should be fine and full screen. Yep, sure. Yep. Please continue. Yeah. Yep.
Yep. Hi, everyone. Today I will be presenting our work called ARCP, Uncertainty-Aware Perception in Adverse Conditions with Conformal Prediction and Augmented Reality for Assisted Driving. This is a joint work from Max Mühlhäuser, Alejandro Sanchez Guinea, and myself, Ashraf Dula, from the Telecooperation Lab from Technical University of Darmstadt in Germany. So I'll just start by showing this kind of example, showing how adverse weather conditions can be challenging for perceiving and the environment, especially in autonomous driving conditions. So it may be challenging, and for this there are several models that have been proposed to tackle these conditions based mainly on deep neural networks. However, the deep neural networks are well known for their overconfident predictions, which may lead to some problems. In this case, leading to false predictions with high confidence, and which may alter somehow and harm the decision-making process either of the driver or of the autonomous vehicle there. So what we need actually is an uncertainty-aware prediction framework that guarantees us that the uncertainty is there within the prediction, and also we have some guarantees also on the confidence of the model. And this is mainly what conformal prediction actually does. So conformal prediction is an uncertainty quantification framework that is model agnostic. So this is a post hoc procedure that doesn't have any assumptions on the model, and it is also distribution free. That means we have no assumption also on the distribution of the data with which we train our model with. The only thing that we need to take care about is the fact that the data needs to be exchangeable or IED if you would like to. So yeah, as you can see in the example there, so instead of outputting a single prediction, conformal prediction outputs a set that contains actually the true label with a user-defined probability. So there in the formula, you can see that conformal prediction guarantees us that we have the true model, which is y-test there, that is included in the set C of our image with a high probability that is user-defined. Here, alpha is an error rate that is defined by the user. So let's say that the user says, I would like just to tolerate 10% of errors. That means the conformal prediction would give us the set with 90% guarantees that the true label is already there. But the problem with conformal prediction is that if we get higher in terms of our expectations from also in terms of errors, the prediction sets can go very large. The problem here is that this kind of large prediction sets are not any more useful for decision making, especially for autonomous driving. So what we propose here is actually an approach to assist the drivers in adverse weather conditions that provides uncertainty-aware classification, avoiding wrong predictions with high confidence. This, we do it with conformal prediction. It also reduces the conformal prediction set size while maintaining the theoretical coverage guarantees using a class taxonomy or some kind of ontologies that we put in as a prior for our predictions. And then it also reduces the driver's decision by demonstrating simplified representations of objects in augmented reality. So to show the whole framework here, let me just start with this situation, which is taken from the road data set, which is actually an autonomous driving data set, showing what a car actually sees in low light conditions. So our framework ARCP starts by grasping this framework, this frame, and then we have a detection model on which, and there in the bounding box, let's suppose that we have a car that we could not actually see using the lights because of the lights, the bad conditions there. So what conformal prediction would give us is this kind of set that's telling us that the model is not sure whether the object that we have there is an SUV, a minivan, or some kind of crossover. So we take those predictions, we combine them with the class taxonomy just to render somehow at that position the nearest common parent concept. In this case, let's just call it, for instance, a four-wheeled vehicle. we take that position and then we render the whole thing in augmented reality for the driver, and then we get the new scene that you are all seeing in the end there. Yeah, and here we are replacing the full prediction set through a single representation of the nearest common parent concept, which also guarantees coverage. So the theoretical analysis also you can see in our paper, and the theoretical guarantees also hold as they hold for the normal conformal prediction framework. Now, this is also an example of the class taxonomy that we use to render or to determine the nearest common parent concept there. So we have the child classes, and then we have higher or more abstract concepts. For instance, like for vehicles where we have two-wheelers or four-wheelers, and then we go up in concepts. How do we evaluate our framework? First of all, we would like to see the coverage guarantees if the coverage guarantees still hold for ARCP. For this, we use the road dataset, which is a large dataset for autonomous driving with 11 agent classes, and also with some logical requirements that we use to build our taxonomy. And for the metrics, we use or we measure the set size, which is also an indicator for uncertainty in our case, and also the coverage rate, just to see if we have this kind of guarantees of the probabilities that we promised at the start of our presentation. Now the results. Yeah, as baselines, we combine our approach with one baseline approach and two state-of-the-art models, which are APS and RAPS. And as you can see here, so we actually succeed in keeping the coverage guarantees while reducing the uncertainty, because our framework actually reduces the set size always to 1. And here in this case, the set size reduction is by 38% for softmax and APS, and by 18% for RAPS. Another evaluation, the second evaluation that we have done to see how this kind of the nearest common parent concept influences users for autonomous driving. So we conducted a user study with 15 participants. We have the immersive setup that you have seen there. So just to increase the realism of our for our user study. And we use 4 challenging situations from different data sets, actually, which are the road, the gated to gated, and seen through the fog data sets. So as you can see, these are the 4 situations that we use. And actually, yeah, for the user data set, we have also 3 conditions. So in every kind of video there, we have 3 conditions. So the baseline, so no augmentation, no visualizations. And the second condition would be the vanilla conformal prediction, if you would like to say it, with some bounding boxes. And the third one would be ARCP, which is our framework. And the metrics that we are interested in here are the accuracy of the identifications that the users are doing. That means how good the users can identify the objects that are hard to detect, their cognitive load, and their situation awareness. And the results here show that ARCP achieves up to 50% higher accuracy in terms of identification scores among the participants, 12% lower cognitive load, and 60% higher situation awareness. That means also the participants get somehow alarmed when there are some uncertainties coming around there, which is beneficial actually for more safety. And then in conclusion, so here we present ARCP, which is an approach to assist driver perception in adversarial conditions. It consists of rendering the nearest common parent concept in combination of conformal prediction to have the theoretical guarantees of correctness. And at the end, ARCP reduces the uncertainty because it provides smaller prediction sets. It guarantees the marginal coverage, reduces the cognitive load, and improves perception and situation awareness. And with this, I'm done. Thank you.
In view of time, do we have one person that we want to address? Maybe let me ask a quick question. Is there any downside to the
Yes.
approach? What is it?
Actually, there are some limitations there because the vanilla conformal prediction framework is guaranteed somehow to produce the valid output if the data is exchangeable. That means in the case that we get out of distribution data, this is gonna be a bit problematic. However, there are frameworks also with which ARCP is compatible that also consider out of distribution data. But yeah, one needs to be aware of OODE data.
Thank you again.
Yeah, welcome.
So we're taking a copy for 10 minutes. Please back to where we have over keynote speakers we want to hear.
Nice to meet you.
Your student was like
Oh.
Yeah, we work on the skeleton based that.
Oh, right. It was a long time. Yeah. It was a while.
2022.
Yes, 22. Yes,
Yeah.
yes, I remember that. Yes.
Finally meet you in person.
Yes. Well, we got yeah, I remember that work. It was very interesting, very nice. It was a skeleton.
Aren't Pokemon is in Amazon?
He's in Amazon now, yes. He should be oh, he's in the San Francisco area. 所以你是台湾人是吗？
啊，对对对，
OK，你中文怎么称？
彭冠群。
哦，
冠群，
冠群。
冠群，因为明星。
对，所以 OK，所以
HDMI
好的好的。
明星有问题过，
哦，是
他们技术学长，我们学这个。
哦 OK，yeah， 我和明星是很多年的这个。Yes, it is. Let me just display, right?
Hi, nice to meet you.
Nice to meet you.
Yeah. If I got correctly, I'm supposed to be in the Zoom meeting when I do the presentation.
Yes,
later
that's
and
right.
Share my screen in the Zoom meeting.
Right, so
while, doing
So
my
the
presentation.
online participant can watch the talk.
Yeah.
Do you have the Zoom URL? I think
Yes, I
yeah.
have it. But how does it work with the audio? Will you
So how- 25
use the
minutes,
microphone of my laptop, or will we use this?
No, don't worry about the audio because the audio will come through my laptop. So you directly speak as normal. You can mute yourself on your laptop.
Yeah,
as
so
well.
I should mute myself to avoid any, I don't know, interference or stuff like that, I guess.
Right. I'm worried that if you do not mute yourself, I mean, we have both the there will be like positive feedback, infinite positive
Yes,
feedback.
that's what I'm
Right,
talking
so,
about.
right, so I'll just, use, take the audio from the laptop.
I thought it was
So I keep my mic.
Oh,
muted.
okay.
Yes, that's fine. Yeah.
I'll try to keep in time to that.
Then I can use my camera, I guess, right? I can switch on my camera,
Okay.
just do it, I guess.
Your camera online, I think they will not see your camera.
It looks like in Zoom meetings, usually you see the full.
Right, I assume you want to project your the slides only, right? What do you mean by the camera? You
For
want
the remote attendees, I mean, if when I'm doing the presentation here.
Yes.
I mean, my screen will go here.
Yes.
And I will share my screen at the same time in Zoom, right?
Yes,
If
that's
I'm
right.
switching on my camera, the defaults attending online should be able to see me or not.
Yes, they should be able to see you,
Okay.
but it's optional.
Yeah, of course, yeah,
It's
but
not mandatory for you to
I know,
switch
I
on.
know,
It
but
doesn't matter.
I like it more if if people
Oh,
can
okay.
see me. I mean,
Okay.
this is what I would expect from other speakers when I attend such a remote session.
All
Anyway,
right.
we will make it. Thank you.
Yeah.
See you later.
Thanks.
So you can switch it to the other presentation and then we'll have to introduce it, right? Okay, yeah, this maybe.
Michelle.
You can use a big speaker bio, the slides.
Oh, okay. So I have to get off,
Just, let him check this.
but I need to disconnect and I have to stop sharing, right?
No, you can.
Oh, I
keep
can restart sharing, okay.
This is just for on-site attendees.
Oh, right, so I log it out, so nothing show up there anyways, okay.
All right, so we will get started since we are slightly running behind schedule. It's my pleasure to introduce my colleague in the department, Professor Siwei Liu. So if you want to be proud of your colleague, he is the embodiment of it. In the sense, no matter what channel you are surfing, you will see Professor Liu coverage in the news media because of the deep fake. He has tons of work in the deep fake space and including a open URL which you can look at. He will probably talk about it.
Yes.
I don't want to give away that information. So he is extremely busy and extremely popular in the deep fake world. There is not even a single day probably every day probably he gets added in the media interviews. So we are very fortunate to have him as a keynote speaker for our workshop. So I don't want to take more time. I think we should probably listen to him than to me. So with that, let us welcome Mr. Siwei Liu.
Thank you very much, Nalini. It's a great. Okay, log this.
Yeah, share the screen on Zoom.
Am I still on Zoom? Okay. No, okay. Yeah, that's good.
Yeah, it works.
Does it work?
Yep.
Okay. Okay, all right. Good morning, everyone. Thanks, Nalini, for the nice introduction. It's really a great honor to present at this workshop. And today I will talk about, my talk will be not very technical today, but mostly share experience we have got running a deepfake detection platform in real life, and maybe a few tips that will help us to develop more effective deepfake detection algorithms in the real world. Okay, so let me first explain what are deepfakes. Well, I can give a lecture on this, but I think it's easier to play a video.
An unprecedented new threat has the potential to impact our privacy, our national security, and the integrity of the democratic process. Images generated by artificial intelligence, so-called deepfakes, being used to harm and manipulate horrible information. We need new ideas, new technology, and the support of media forensic experts to solve one of the biggest challenges of our time.
Okay, so oops. Okay, so well, this is a deepfake, obviously, and I used the former president's voices and images to communicate the ideas I want to communicate. So that's essentially what we people use deepfakes for. Of course, I'm using this for a good purpose, but you can imagine there are many ways that deepfakes can be misused for affecting other parts of the world, other part of our society in a harmful way. So including elections, targeting individuals for defamation and emotional attacks, and also financial scams. So there is because of that, there is a high demand for effective methods for defect detections. So typically a user will have a question, will have media, in this case, we talk about images, audios, or videos in question, and they want to know whether this is a real content or is created by AI or being a deepfake. I work in this area. I know that in just past year alone, there are more than 15, maybe even more startups providing such services for detecting deepfakes. But each of these startup services, they usually have paywalls, so users have to pay for that service, and they use closed source code. So we do not know exactly how these platforms make decisions whether something is deepfake. They rely often on a single method, so it's he for me's, and they do not evolve with. Well, they evolve with time, but probably not as fast as possible. And for that reason, they could be responding to the growing threat of deepfakes, not in a timely manner. As we know, the generative AI technologies develop very fast, evolves almost like generations within just a few months. So we need something that can go faster. On the other hand, we do have a lot of research in this area. So we have just publications. What we did is go to archive and search for keywords with deepfake detection in it, and the number of publications grow fastly in the past few years. It means that this has become a very active research area in computer vision. In particular, in this CVPR, this year's CVPR, we have 12 papers in the main conference on this topic or related topics. So it's becoming a mainstream computer vision task. However, if I'm a user and I want to take advantage of the most recent up-to-date development, cutting-edge deepfake detection methods, what I have to do is probably go to the GitHub, and it's not a problem for this audience, but just the process will be go to most of this paper may have usually come up with open source code on GitHub. So the first thing we do, go on GitHub, find that code, and download it, compile it, and then start running on images or images, audio, or videos on our own computer. This is okay for us, but think about a journalist or a forensic investigator who does not have the same kind of technical background and preparation as we do. This is going to cause a huge burden on their side. And that's why, even though we have very active development in this area, many of the methods did not see real world use because of this hurdle. So that's the reason we developed a system. So we call it deepfake-o-meter. What we try to do here is really build a bridge between the users and researchers in the computer vision and media forensics community. So deepfake-o-meter is a free platform. So you just need a registration with the email address. And you can find deepfake-o-meter, by the way. Use the exact keyword in Google, you'll find that platform. It's completely open source. And it's the platform itself is open source. So the code we implement deepfake-o-meter itself is on GitHub. All the methods we incorporate there are also open source code coming from papers with code, computer vision, CVPR, and all the other major CV conferences. And what we do is we package them up in containers and then provide an easier user interface to the users. So on the user side, it becomes much easier for them to use the system. I will give you a quick run through of the system, intuitive and simple, lightweight. For the researchers, I think this gives us a rare glimpse of seeing how our methods actually work in the real world. In the real world, I mean people who actually submit tasks and then how our methods perform there. instead of just running them on benchmark data sets and compare AUCs. Okay. And then I think ultimately what we want to do is this feedback will provide useful information to develop additional future methods, and that's what we have learned in the past. So just a quick overview of deepfake-o-meter is very easy to use. You log into the system, and once you are in there, you can drag and drop media files, and then there'll be a list of analyst modules depending on the media type. User can select the analysis and then see the results. Currently, we have incorporated 18 different modules, and they are for different media types. And you see we cover all the media types, images, audios, and videos. We plan to have text detection modules too in the future. A third of them come from MATLAB, so because that's what we actually do as our daily research responsibilities. But many of them come from the state-of-art detection algorithm in recent years in papers. One of the papers actually come from this year's CVPR. So if you work in this area, you have a very effective methods published in your in papers, please talk to us, and we'll happily incorporate that into the deepfake-o-meter platform. So once the user upload the tasks, it'll be put in a queue. We have a backend GPU server running the computation tasks, and once the result is back, we provide a quick overview of the overall analysis results, including the likelihood score of this media for based on each of the analysis modules. Of course, the user interface is still a little crude, and many users actually ask the question, "What is the likelihood score?" So that's the level of understanding and technical background we expect the user to have. So this, one of the immediate thing we learned is we need to talk with the users using a very different set of languages instead of talking among us researchers. Well, once the image is uploaded, there'll be also a detailed report. Once you click the result link, you'll see that result with some details about the detection method being used. Now, how is the platform being used? Well, we put online earlier this year in January. We have seen a steady increase of usage by many users. Right now, we have the statistics is up to end of May. So we have about 450 active users outside my own use, our research group. So these are external users to the system. We call them active because they register, but they also submit at least once to the system. The total number of submission outside the research group is about 4,000, more than 4,000 submission over a little bit more than 3 months. So, and you can see there's a steady increase. I'm showing here is accumulative number of accesses to the system. So you can see a steady increase trend of those requests. Look at the breakdown of daily accesses. We can see that it happens. Also, there's a steady increase of the frequency of submissions, showing that people are interested in using the system. Now, I've been working with people in law enforcement agencies and news media. So I shared deepfake-o-meter with them. So a lot of the users are actually known to us. We know at least at this point, Associated Press, Reuters, NSA, and NIST and FBI have. So we have users from these agencies using the system. So they are serious users, and they actually use the deepfake-o-meter platform for some real cases they encounter in their daily work cycle. So you may notice that there are some anomalies here. We have a big peak around there. Anybody can guess? Anybody guess what happened there? So we have on that day from like a single user, we have more than 300 accesses for in one day. What do you think happened? Anybody have a guess?
Data poisoning, maybe?
Yes, we got hacked. So somebody used the system to try out different ways to evade detection. We know about this because the files coming in with the same stamp, but with slight variance in the postfix. So it was somebody who's trying to tweak the generated deepfakes, maybe using adversarial machine learning, adding some adversarial perturbations into their into the deepfakes, and see how the detection methods fare. That's one thing we learned. There are high frequency access to the system with this shady purposes possibly. So what we did is we limit activity users' frequency of requests on daily basis. We only give trusted users or something higher than normal. So that's where you see afterwards the number of accesses got reduced, became a lot. And then the second part, this is when these ones are actually legitimate use, legitimate access to the system. And these are actually from journalists in India and where was the other country? I think India and one of the other countries that having elections. So that's when the system got a lot of use and the system did crashes a lot of times. We cannot take so much requests, the server crashes, backend just stop working, front end crashes. So these are another things we learned during the process. But as you see, the system actually got real world uses and we got users feedbacks. So what do we learn? Now, we have some positive feedbacks from the users. I have closed here one user. So he's actually from, I think the user is from one of the third-party fact-checking service for Meta. So he actually used the system extensively, and he said that the system, the strength of the system is the simplicity, the transparency, and the flexibility of choosing from many different methods. So it's actually give options. We do not, so the purpose here is not to come to the user say, we make a decision for you. This one's a deepfake or this one's real. What we want to tell the user is you can choose from different methods, almost like you ask opinions from a group of experts and make your own decision based on all the information there. But we do run into problems, and this is where we like, I think, the most valuable feedback we got from users. For instance, we realized that the detection algorithm, all the detection algorithm, we choose them because they reported high performance in terms of accuracy on the mainstream benchmark data sets. But when they were used in reality, the users come up with a lot of comments that mostly focus on the utility of these detection methods are not always reliable. And because of that, I think coming very fit with the theme of this workshop is, generally speaking, the user's trust to the detection algorithms are not as high. So one of the two of the main points we learned is the detectors are not very consistent in detecting, in reporting deepfakes, even though the artifacts sometimes are very obvious to human eyes. So, for instance, this is a real request. I think in May. So showing an image, here. Now, this image is clearly AI generated because if you look carefully at the details of the image, you can pick up a lot of artifacts. I have seen too many of these kind of images. I almost know exactly where to look at and what kind of artifacts we expect to have. But to say the other thing, this image is clearly coming from a diffusion based generative model. It has that kind of look and feel. Again, I cannot put my finger exactly where it gave me that feeling, but generally speaking, it's a more smoothing and kind of like a painting like feeling is or diffusion, quite like all the many of the images I saw generated by diffusion models. But when we actually put into like the state of art defect detection algorithms, many of them just think this image is real. One image, the one detection that is gave a kind of like lukewarm responses, not very sure. And we have even one method that's refused to analyze this image. So this is the major frustration from the users. You can see that maybe this image has been recompressed, maybe something has been done to this image. Something happened to this image that deviated from the training data all this method has seen. So this may be this is one of the problems. And the other part is in this case, most of the detection methods actually agree with each other that this is a real image. So there are in consensus, but we're in the wrong consensus. We also have a lot of cases where you have split opinions about an image, and then the user got very confused. And there are some ugly parts of this too. The UI is quite buggy. You know, this is something we expect to come from a research lab with grad students and professors working on a system. You know, we're not expert in UI, but more importantly, I think the system lacks scalability, and I don't think the way we're running the system now with a backend server with a couple of GPUs and a simple web front server will be sustainable in the future. So we have to find a better solution to the system. But we want to ask research related questions. You know, what we can do to improve this? Now, actually, this experience gave us some good time to feedback, to reflect what has been done for defect detection. So I think we all agree that these days, as defect detection becomes a mainstream computer vision application, we all run this common paradigm. I call them like the main paradigm of defect detections. Very simply, we form a detector, a neural network type of detector, some architecture. Usually this architecture borrowed from computer vision, other tasks in computer vision. So something work for object detection, we use it. Something work for tracking, we use it, right? So we talk about transformers, attention, convolution, most recently Mamba, and whatever, you know, something hot in computer vision, we'll borrow that network model. Then we train on a label data set, and we hand label them as real and fake. Something comes generated by AI, we come fake, something real, we get a real label. Now at the classification time, we take input, throw it at the classifier, come up with the detection results, and the user, and then give a likelihood score. And the user think about this as, you know, come to the detector, treat this as an oracle. I have a media, tell me if this is real or not, right? So this is the typical paradigm. But when we look back and do some detailed analysis of the performances, we realize something critically different from this main paradigm, that we need to look at this detection problem from a different point of view. The first one is we wonder if borrowing from computer vision models is actually appropriate, is the best way to solve these problems. So you may not realize that, but unlike computer vision, the actual useful signal for defect detection is not the semantic content. It is the noise that we call noise in other computer vision tasks, is the signal for media forensics. What we call stuff, contents in computer vision is actually the noise. Think about this. If you have a diffusion model, you can use it to create any image of any content you like. So if there's any consistent artifacts, it must have nothing to do with the content in the image. So in this sense, the contents, the objects, is almost a distraction to defect detection. So what we should do is actually, you know, maybe we should use a different model that's more sensitive to the traces in the noises instead of the objects. So that's why, you know, we don't have a solution, but these are the things we learn. Maybe we should switch to something that's less semantically oriented. The other big question, especially for people working in computer vision, we rarely ask, when we do object detection, we have labels there. We rarely ask is if this is a classification problem. It's very clear if I'm looking at an image of a cat or image of dogs. But when we talk about real and fake, things become so blurry. It's not actually clear cut. So what do we call real? Now the working definition of real and fake is like something comes from AI, that's deepfake. Something has nothing to do with AI, that's real. Now let me give you an edge case. Suppose I use diffusion model, create an image. I displayed it on a screen. I take a photo of that. What do you call it? Is it AI? Well, it's created by AI. But is it real? It has any signal level statistical feature of a real photograph because you take a picture of it. And there are many, many cases like that. And post-processing actually affects and makes the line very blurry. So I don't even want to answer the question, what is real and what is fake? Because we are reaching at a philosophical level, what do we mean by it? And the other thing is maybe in the coming years, as we are seeing more and more generative AI models around, this question may become irrelevant. Everything may be created somewhat with AI model. So, we may have very few real concepts there. So because there is no clear definition of the labels, we're completely at the mercy of training data. Who label the data becomes the gold standard of what is real and what is fake. Now, I'm not even talking about, the difficulty in labeling this data. But just think about, your classifier may learn something that is completely, relevant to the training data. It's something is a confounding factor from the training data. We actually run into a case where a classifier is trained on real images that are all PNG, fake images are all JPEG. So you just detect the file format, 100% accurate what is real and what is fake, but that's not what we need, right? There are also another side of we call nuisance factors. These are factors like deep blurring, noises, adversarial attacks, compression that will generally reduce degrade the performances. So I think for deepfake detectors to actually work in real world, we need to reduce the reliance on training data, or at least maybe come up with better quality training data. The last one is communicating with the users. As I said, the user come here, think about this as an unconditional probability. You mean with an X, is it real or not? Actually, because our detectors rely on training data, there are a lot of latent, hidden qualifiers. A simple one, some of the detectors only deal with images with face in it. And then when the user drag in an image of a car and ask a question, what kind of answer we expect it to return to us, right? But this is a simple case. There are a lot of latent factors that are not obviously clear to the users that we need to communicate with the user better. To a certain extent, the detectors are answering a conditional distribution problem, conditional probability problems. Under this kind of constraints, I can tell you reliably whether this is real or not, right? So I think these are the holes we realize in this process. Okay, so in summary, I'm showing this deepfake platform is working, and we learned a lot of lessons. I think there are a lot of things we need to do to actually make the detection algorithm better. I'm running out of time, so I will skip the last part. I want to thank all my collaborators, students, postdocs in my lab for doing this. I certainly could not do this work without their support, strong support, and also the funding agencies. Thank you very much. I can take a few questions.
Thank you, Steven, for such an exciting summary of what you have been doing. Any questions? Yeah.
So in the case of the bad actors, do you think about maybe letting them do it? So did you think about maybe just letting them do that to get the kind of data that they could generate?
Yeah, that's insecurity. That's called honeypot. So you can actually set up something and they come to you. And yes, we actually let it go for a while. We observe the behavior. We want to know what they're at. So there are also people using deepfake leader as a cheap way for getting server resources. So when they are working on the paper, they're running out of GPU resources. They just continue doing this. I think that they write an automatic program for AI instead of for UI, so they do that. So yes, we have seen a wide range of behaviors using the system. Some of those are benign, innocuous, but there are also something that's a little shady. So one thing I think we learned, the most valuable experience we got from this is this diversity of behaviors. So what we are working right now is compiling all these user statistics, because these are the things we rarely see in this community. We want to present that in a more organized way, so we can learn more from the users' behaviors and come up with better solutions. Very good point.
What if someone just generates one part of the image? So you take a real image, you emphasize one part.
Yes, that's also a very good question. That's related with the definition of real or fake. So binary classification, in my opinion, is definitely too oversimplified the situation. There is actually, that's one topic I didn't get enough time to actually go into detail. I think we need to break away from binary classification and going for something that's more informative. For instance, the question you mentioned is a localization problem. So we want to identify not only this image has a touch of AI in it, but also where and how and what model has been used, right? So all these questions are more informative than a simple binary answer. So I think, localization, where the image has been changed by AI, model attribution problem. What model has been used? What's the parameter? What's the model, like diffusion? Again, what sort of diffusion you use? Maybe some of the hyperparameters or training data sets may make a difference in the model, in the generated images that we can use to have. All this will help us to uncover the deepfakes provenance of the places.
Really makes sense. But what about the classic dumping? Like someone using, for example, Photoshop,
Yeah.
What's the difference?
That's another good question. So actually, we are focusing mostly this. I work in this area for 20+ years. When I started as a PhD student, I mostly deal with Photoshop editing for images. And I think now the trend goes to deepfakes, because AI is the thing, and deepfakes are always on somebody's priority list. But I want to say, if you go into the real world, I think the majority, there was somebody did this status, 90% of actual disinformation online has nothing to do with AI. So they were created, just most of them are real images, but put into out of context. So these are real images, but paired up with wrong text, for instance. And there are also a fraction of images that are edited with simple photo editing operations, like Photoshop or changing contrast, those simple things. So even though I work in deepfake detection, I don't want deepfake detection to steal all the spotlight. And we need to realize that the bigger problem is there. And so I very much agree with you that this one is only, we bundle all the deepfake detection methods here, but the plan is actually expand this to other type of media approaches. Thank you.
Because you are also adding the audio.
We have audio detection methods. Yes.
All right. Let's thank Trustee Liu once again.
Thank you very much.
So next on our schedule, we have the paper presentation of mitigating bias using model agnostic data attribution. So. Yeah, it works on the, yeah, we can start. Yeah, remember to go start.
Yes. Right. Hello, everybody. My name is Sanj, and I'll be presenting you our work on mitigating bias using model agnostic data attribution. So bias is something that can arise quite easily in machine learning. It's very data reliant. For example, think about the case where the data you train your model on over or underrepresents certain subgroups of the data, or is just differently distributed than the real production data. And we focus on one of these cases, which is actually when the data is being biased by a certain confounding attribute. So, for example, in the Celeb data sets, which is a pretty popular data set involving faces of celebrities, a majority of the women have blonde hair, whereas almost none of the men do. So if you train a model on this data set, it might learn to pick up that blonde hair is one of the confounding attributes, or one of the, well, it might learn to pick up that blonde hair is an indicator of being a woman. So we're trying to prevent this in a pretty straightforward way. By initially first trying to find out which regions of an image are important to classify this confounding attribute, for example, blonde hair, and then subsequently adding noise to these regions during training of a model to prevent the model from overfitting on these confounding attributes. So there's two steps in this. And the first is, of course, trying to find out which of these regions of an image are important for a certain attribute, for example, whether someone has blonde hair or not. So trying to find out which image regions are important is something that sounds a lot like saliency methods, which is quite popular in explainability. But what we're trying to do is slightly different. So instead of trying to find out what a certain model looks at in data to make its classification, we want to find out where the data could arise in the, or where which regions in the image could be important for any model. This is why we created our own model agnostic technique, which works in a very simple way by using a patch-based classifier. So a classifier that takes in a patch of 32 by 32 here of the image, and it tries to predict an attribute on patch level that is of the image on image level. So it would, for example, here try to take in a small patch of the image and then classify based on that patch if the person has blonde hair or not. By using this classifier and using its confidence as a sort of proxy for information content. So if it has a higher confidence, then it would be more sure based on this patch to make its prediction. We use this to attribute the image. So to find out which regions of the image contain a lot of information about what attribute. So that subsequently we can use these regions to add targeted noise and prevent these biases from being learned. So of course, since we use the confidence of a model, it's important that this confidence accurately represents well, how much information there is to be found, which is what we call calibration. I won't go into too much depth on this, but I refer to the poster session for this. So I can show you some examples of our attributions. We see some image-specific examples on the Fairface dataset of these three attributes. On image level, it's kind of harder to make up anything. But we can also do it on a general level because we work with data sets which are aligned and centered in the same way. So if we take these four attributes of the Celeb data sets and we average over a lot of these attributions, we can see that, for example, for blonde hair, the most indicative regions are around the face, whereas for smiling and eyeglasses, they're a lot more centered on the image themselves. So going from these attributions, our goal is to use them to mitigate biased learning. For this, we have a certain scenario set up
we're going to try to do perceived gender classification on a very biased subset of the celeb A data set. So we have 3,000 men and 3,000 women, where none of the men exhibit a certain confounding attribute. For example, none of the men have blonde hair, whereas 2/3 of the women do. So we'd expect that if we evaluate on a data set that is balanced towards this attribute, that it wouldn't perform super well, super equal. So we want to prevent this by adding target noise based on our attributions to the regions of the image. So we can see we try out a couple of different ways, both in a masking approach and an additive noise technique. And then we evaluate on a balanced data set with regard to this confounding attribute. And ideally, we'd like to have an equal performance. I'll quickly show some results of the case where we have blonde hair as this confounding attribute. So you can see on the left side, on the blue bars, that if we train without any noise addition, that we see a large gap between accuracy for men and women on this new data set because it is distributed differently than the data it was trained on. But if we introduce target noise, so the model learns to rely less on these confounding attributes, like blonde hair, we can shift the accuracies or the performance of the two subgroups towards each other, making the model fair in a way. So yeah, we can see we have a couple of different ways of adding noise to the training data. But we also have another hyperparameter, which is how much noise we use. So this is what this noise quantile is that I'm talking about. So this is, well, how much of the noise, what percentage of the image do we actually add noise to? So we experiment between going from 40% of the image that we add noise to only 5% of noise. So we can see the less noise we add, the less we, the less this distribution or these performances shift between each other. But also if we add too much noise, then the performance decreases too much because also valuable information that it does need for its task gets removed. So this was for blonde hair. We also had some more experiments we did on other confounding attributes. I'll spare you the details of the large experiments. I'll refer to the poster for this, but I'll give you some conclusions we were able to make on this. So we tried our approach and also evaluated it with respect to another approach, which was trained on a balanced data set. So similar to our experiment we have 3,000 men, 3,000 women, but there we have so equal amounts of men and women with and without the confounding attribute. So we find that our approach actually approaches this balanced scenario. However, also on this balanced scenario, a small gap always remains actually between the two subsets, between the two subgroups. So this is an interesting observation to make. There's always some bias that arises, not necessarily due to the one confounding attribute, but there could be lots of other attributes as well because our data is so high dimensional in a way. Another interesting we found is that across all confounding attributes, the most optimal arrangement for the way we add noise and how much noise we added varied. So these two, in a sense, remain hyperparameters based on your specific case where you're trying to prevent bias being learned. So that was a quick overview of our work. We tried to mitigating bias using model agnostic data attribution. So we learned this data attribution through sort of classification technique, which we then use the attributions to work towards bias learning through addition to during the training loop. This is just a very preliminary work, but we think it could be interesting to see how these
attributions could be used in other fields. For example, privacy preserving machine learning, not only to prevent certain attributes from being able to learn, but also looking at, say, the limits of what you can do if you want to prevent some attributes of an image from being learned, but you want to keep others, but these two attributes are very entangled, say, because they take up lots of regions that are overlapping. Well, that might not entirely be possible. So that's it for me. Thank you for your attention.
Nalini, since we are quite running behind, so I suggest that people can reserve their question during their poster session at 4:30 p.m. This afternoon. So thank you for the speaker again. So next we have I'm told that we have a remote talk of the paper entitled "Practical Region Level Attack Against Segment Anything Models." So if the authors are online, please unmute yourself. Yep, we can hear you. Wait me for 1 second. Let me project on the screen. Okay. Yep, could you please share your screen?
Oh, sure.
Start presenting.
Sure. Wait a second. Can you see my screen?
Not yet. Hold on. Yes, we can. Please start presenting.
Great. Yeah, just interrupt if you find my voice is too low. Yeah. Okay. So I'm Zhong from the University of Illinois Urbana-Champaign. It's my honor for me to present here, and I'm happy to introduce our work, Practical Region Level Attack Against Segment Anything Models. So segment anything models is very famous. Oh, wait. Okay. So it has revolutionized our. Can you still hear me? There's some.
Yes, we can hear you.
Oh, warnings from my side. Okay. Okay, never mind. So it allows users to segment parts of the image.
Hello, are you still there? Well, we lost you. The connection problem from this end.
Hi.
Yep, we can screen now.
Okay, let's move on. Yeah. So, because yeah, so the robustness against adversarial attacks is crucial because the wide applications. Imagine there's an autonomous vehicle using SAM to detect objects. The camera captures an image of two pedestrians. Normally, SAM segments the pedestrians and the vehicle stops. But if an attacker manipulates the image, the pedestrians may not be detected, and that will lead to potential accidents like the lower image shows here. It fails to detect the pedestrian. So our algorithm has two variants, SRA and TRA. Let's start with SRA, sampling-based region attack. So typically, a user inputs an image and clicks to SAM, and SAM segments the boat. So that's how SAM usually works. But now, there's an attacker who wants to hide the boat. First, he sets a box around the boat, and then our algorithm starts work. We uniformly sample points in the region. Oh, there are some red dots here. And those are sample points. And the points are substitute target of the attack. So that's why it's called sampling-based region attack. We then perform some off-the-shelf attack methods, like the famous PGD attack. And the attack aims at minimizing the region that SAM produces for each sampled point. And then we feed the image to SAM again, and it fails to detect the boat. So this works in the white box setting. In the black box setting, we have two differences. The first is that the example is created using one SAM variant, like SAM B, but it's tested on another, like SAM H. So they are basically some models with different numbers of parameters. And second is that we apply SSA to enhance the transferability for the black box setting. For the other parts, the two algorithms are very similar. So basically, SSA is not our innovation. It's from another paper. I will give a very quick introduction. So the intuition is the following. Different deep learning models depend on different frequency domains of interest to make predictions. For example, for the same image in the middle, so the salience map basically it shows the loss sensitivity of different models. The salience maps in the frequency domain are different for inception V3 and inception V4, like here and here. So now what we do is we first perturb the spectrum of the image, like the frequency of the image with SSA. And then the salience map of the inception V4 becomes similar to the map of inception V3. And then we use any of the shelf attack methods like PGD or FCSM to generate adversarial examples. So that paper has proved that this technique improves the transferability in the black box setting for attacking the image classification models. And we find that without any further modification, these techniques can be utilized to generate adversarial examples against them, which is a segmentation model. We evaluated our methods on 200 images and measured the MIOU of segmented regions from the adversarial examples and original images, which is the lower the better. And it shows that our method, SRA, is better at all noise strengths than the baseline attack sum. And what's interesting is that in the black box setting, we find that due to the model mismatch, both the SRA and the baseline, the performance is downgraded, but the TRA outperforms the other two methods by a large margin. Okay, and now it comes to the exciting part. We also tested our adversarial examples obtained from offline SAM checkpoints on the real SAM website. So this is image from our data set, and those are real output from the online SAM model. So it normally segments out this part of the building. And now we apply our attack method TRA, and it generates an adversarial example, and then we feed the example to the online SAM. And you can see that the regions are minimized. Actually, attacking the online SAM is much harder than attacking the offline checkpoints, but we did find some success cases like this. And actually, you can find this original adversarial example in our code base. You can just search the name of the paper on GitHub. So in summary, our work highlights two main points. First, hiding objects from the model might be a really practical threat. And second, by combining sampling and SSA, our method generates transferable adversarial examples, which successfully attack both local and online SAM models. Yeah, thanks for your attention, and now I can take questions.
Okay. Thank you for the talk. And so since we are running behind, so we have no time for the question right now. So we'll reserve that for the poster session. So next we have the paper presentation towards explainable visual vessel recognition using fine-grained classification and image retrieval. You sure? It's not coming up yet. Have you shared screen?
Yes, of course.
Oh yeah, it's good.
Okay, cool.
Yeah, go ahead.
So welcome to my presentation. My name is Michael. I'm from Germany, from a German company, Handel Electronics. And what I present to you today is joint work with the Ulm University and the Ulm University of Applied Sciences. It's a highly application-related paper, and we asked ourselves the question, how far can we get with state-of-the-art methods in how far can we get with a web crawl data set using state-of-the-art methods for visual recognition, for visual object recognition, to, well, solve tasks where we have objects in different classes, but with highly similar appearance. So what you see in the motivation here is a query image showing a military vessel. And here we have like a database of other military vessels, asking ourselves like which image matches. We can also see that the appearance of these objects is highly similar, as already mentioned. And what we see here is that we are able to find like this query image, the object that is shown in the query image. However, this example is mainly focusing or adopted from image retrieval tasks, which are probably well known here in this community. We asked ourselves, since potentially we can formulate this problem in two different ways, which of these ways might be better for performing visual vessel recognition? So what are these two ways you could formulate the problem? On the one hand, we have object classification, which is basically something like an end-to-end approach for fine-grained object classification. You have an input image, you have an end-to-end object classification in your network, and you will get probabilities for the classes that you trained. On the other hand, we could use image retrieval as problem formulation, which is basically a database query. So you have an image database that we use a neural network as feature extractor to have like something like a feature database. And when you have a query image, you extract the features and you try to find the best matching images in this database and to rank them for the probability of showing the same object that you showed in the query image. Our main observations during our experience were, which is not super novel, I would say, that end-to-end object classification is more accurate than image retrieval, but not so easily extendable to new and previously unseen classes. Since if we do a retraining of an end-to-end approach, we have to cut the last layer and retrain it, which is not that handy, I would say. In image retrieval, on the other hand, when there are new objects appearing, new classes, then we simply can make them part of this feature database, and we made it and we extended the approach for new and previously unseen classes. So what is the contribution of our paper here? So we web crawled a large data set for military vessel recognition, which is highly inspired by the Marvel data set that was originally published at ACCD 2016, not by us, by other authors, but we adopted their method doing web crawling to achieve a database of, in its origin, 90,000 images. We use a ship spotting website called shipspotting.com. And after we did several post-processing things here, like removing duplicates or bad example images, finding distinctive classes, because when crawling images from this ship spotting website, you basically get about 10 or 20 different classes, which is not what we aimed for. And also to avoid biases like photographer bias, that you have the same photographer always for the same class, something like that should be avoided, of course. We came up with a data set finally with about 15 or 16K images and 137 classes, which now means that our fine-grained recognition problem knows about 137 classes and potentially have a highly similar appearance. And we can see some examples here, different backgrounds, different perspectives, hard and similar examples shown here on the slide. Now what we did is we did a big analysis of the state of the art, of the current state of the art. We used two maritime data sets. One is, of course, the one that we propose here. And the other one is called the James Fighting Ships dataset, which is not publicly available, but you can buy it. It's a company that sells such kind of data. We also use two other data sets coming from the, in general, object recognition task, which is called CUBs and CARS. We use them to verify that the methods that we utilize perform as we expect. But then, of course, we try to use them for solving this problem of visual vessel recognition. We did some kind of feature space assessment. I will go over here a bit faster so that you can keep some motivation to see me at the poster later by assessing feature spaces using TSNE plots, for example, as we can see here. In this, to give them some kind of quick insights, we discovered, which is not surprising as well, that vision transformers perform better than ResNet, slightly better. And as soon as we do some kind of fine tuning for either the task of image retrieval or for object classification, we get quite distinct feature spaces, at least for the military model data set. This is not the case for the James Fighting Ships data set, as we can see here on the bottom, which means that the James Fighting Ships data set is more difficult than the military model or less well annotated. And we did an assessment of the current state-of-the-art methods, which, as I mentioned, I go over a bit faster here, but it confirms basically what I mentioned in the first slide, that basically end-to-end object classification has a bit higher accuracy while not being that easily expandable. On top, we wanted to understand if we could utilize explainable AI methods to get some insight in the decision process. Of course, when there's this highly similar appearance of objects, it's even more important to get some indication of what were the key features the method focused on when it made its decision. So what we did here is we used those standard heat map-based explainable AI methods. Of course, we also use those GradCam or CAM-based methods, but they need to use them, you need some insight in the training process, which we actually wanted to avoid. So we were more focusing on what is called black box methods that you can use as an adapter to get this kind of heat maps that indicate what regions in the image were more relevant than others. And the cool thing is what we discovered here is, and this is also shown in the example, that for two highly similar classes, where there is the difference only in this spherical radar that we see, that is highlighted with this beautiful red dot on the left, that the method is able to not only classify the object correctly, but also giving this heat map, it shows that it was really focusing on this spherical radar, which was the key difference between these two classes here. And in general, they look very similar. So that gives us the idea that it seems to perform well. Same thing applied to the image retrieval scenario, where we also utilized several state-of-the-art explainable AI methods to get, again, some heat maps. And also we see here that it turned out well, that these methods seem to perform surprisingly good, I would say. To get a quantitative assessment as well, not only as I showed you so far, those qualitative examples, we used a method called insertion deletion game to quantify the performance of the explainable AI methods. Basically, it means that we mask more and more of the relevant pixels for the decision according to the explainable AI method. And then we understand how fast and how strongly the confidence of the classifier is going down. And of course, you would expect that the faster the confidence is going down, the more significant pixels we deleted, which means that if those pixels were indicated by the explainable AI method, it seems to perform well. Again, we did an assessment analyzing different methods taken from the state-of-the-art. And this already brings me to the conclusions or the key takeaways here. A well-designed and engineered data set, such as the military model, can quite easily be utilized for high-performance visual vessel recognition. What I did not mention here is that we achieved an accuracy of about 99%, which is a bit disappointing when you publish a data set, because then there's no space for improvement, nearly no space for improvement. However, we didn't expect that actually, that these methods that we analyzed perform that good. And what we also can say is transformer-based methods, they slightly outperform CNNs. As I already mentioned, end-to-end fine-grained classification achieves higher accuracy for the price of less expandability. And we used black box-based explainable AI methods that again performed surprisingly well, and we could also quantify that with this insertion deletion game measure. I will have a poster later, and the poster session just gives you a little preview of how the poster will look like. Please come by. Would be cool to have some discussions with you about this work. And thank you for your attention. We published a data set. It's basically not the images itself, but it's more like a script where you can download the images from the ship spotting website, and of course, arrange them in a way that they are labeled and utilizable for you. And we also have some code here for supporting you in evaluations if you're interested in the data set. Thank you for your attention.
Yep, thank you. Thanks for the speaker. So please reserve the question during the poster session. So on our schedule next, we have a presentation entitled "Enforcing Conditional Independence for Fair Representation Learning and Causal Image Generation." So are you on Zoom already?
Yeah, I am trying to open it.
Yes, we can see the screen.
Okay. See the
Yes.
screen. Okay.
Yeah, go ahead.
Yeah. So thank you, everyone. I'm gonna be presenting this paper basically about a kind of regularization method that we experimented with in terms of with diffusion models in order to kind of reduce the effect of confounding variables. So it's similar to a presentation we heard like a couple back, but anyway, yeah, I'm Jensen, and I worked on this project with some other people at Stanford and also at UC San Diego. So yeah, happy to present this paper. So the context that we're looking at here, I'm just going to try to go as quickly as possible to stay within the time frame. But we have, yes, so the task that we are modeling is we have some image data, let's say, where you have images of people's faces, right? And then we have labels for their sex and then also for their skin type. And we want to learn a classifier of the sex of the person in each image while being invariant to some confounding attribute, right? So we don't want the skin type to impact how well we can learn the sex. We don't only want to be learning the classification well on, let's say, like very lighter skin types and not doing so well on darker skin types or vice versa. And so we look at enforcing this condition. So theoretically, it can be represented as this equalized odds condition of fairness. So basically, we're saying conditioned on this true variable, the true sex of that image, we want the skin type to have no effect on our prediction. So yeah, regardless of the protected class, we want the true positive rate of our sex prediction to equal the true negative rate. And so just to more fully formalize this, we have our image is represented as the input X. And so we think about what are the factors that are influencing this image. And so we have not only this gender variable Y, but maybe the skin type or the other confounding variables, and they all kind of impact what appears in that image. And now we're going to train a model that can get a representation of that image V, and then from that representation, kind of we train this classifier that is going to try to predict the sex from that image. And so in our paper, we kind of build off some previous work that models this as this conditional independence formulation as a equality of two divergence terms. So this is referring to like the Jensen-Shannon divergence. So yeah, I don't need to get too bogged down in like the theory of this, but we're basically measuring the similarity of two probability distributions. So you have the joint probability distribution of our predicted sex and the true sex value, and then we want to
essentially now train this what's called like an imperfect sampling of this of our predictor model. So that's this Q function, and essentially this gives us a way to now train a model to enforce this conditional independence condition. So we have this essentially like this new component that we're training this Q function that is going to enforce conditional independence on the output predictor value. And so what we are showing is a way that we can take any encoder, like any image encoder, and then add on some conditional independence enforcing component that is, it acts as like a regularization term. So we give a new loss value that's essentially the conditional independence of like what we're trying to enforce. So we can now add that conditional independence condition along with our original encoder's loss function. So this gives us kind of an added term to our loss function that now accounts for how well we are enforcing this conditional independence condition. And so the way that this conditional independence enforcing component works is it's taking these two discriminators, and so what ends up happening is that each discriminator is estimating this divergence term. So we have work showing that, right, this conditional independence condition that we want to enforce is the same as enforcing the equality of these two divergence terms. And so one discriminator corresponds to one of these divergence terms. And so this conditional independence loss is essentially making these two discriminators loss as close as possible and thereby enforcing that conditional independence condition. So this, yeah, it draws upon like some kind of some insights from GANs, like kind of a that kind of paradigm of model, and we kind of take any encoder and kind of plug it into this kind of GAN formulation, and then that gives us this conditional independence enforcing technique here. So I'll go on here to the next slide. And so what we then expanded upon in this formulation is that we found that instead of just enforcing the conditional independence at the end, we tried to now enforce this condition on the latent representation. It's kind of like going more into the internal parts of the model to see if we can do a better job of enforcing conditional independence at the root, like kind of on the latent representation rather than just on the output. So we extend that formulation into now this latent representation space, and kind of following the same theory, we just replaced what originally on this previous slide we had the output values, the predicted output values. We now replace that with the learned like representation of that image or of what's coming out of the encoder. So this is what we experiment with, and we find that there's some interesting things that happen. So first, in order to get this formulation working, we no longer have a way to model this distribution over the latent space, because that's going to be changing while the model is training. If the model is learning this latent representation, so of course that distribution of the latent representation is going to be changing over the training process. So what we do is we kind of sample within the same batch at each step of the training process. We sample the latent vectors for the same ground truth value. And so this gives us a way of kind of estimating what the instantaneous like distribution of this latent space is. And so that's kind of one kind of tweak that we do in order to enforce this condition on the latent space. But I'll now go into kind of what the results look like. So back to what I was saying earlier, we worked with this image data set. It's called the Gender Shades Pilot Parliaments Benchmark data set, where we have a bunch of face images, and each one is annotated with the sex of that person and also the skin type. There's a scale from like 1 to 7, from lighter skin type to darker skin type, according to this scale. So those are two annotations we take for each image. And now we work with this diffusion autoencoder model we work with the latent representation that's kind of encoding the semantic attributes of this image. And now we can apply our technique to make one portion of the
of the image, one portion of the representation, I mean, invariant to the race, right? By applying that conditional dependence formulation so that this is, this portion of the latent representation is independent of the person's race, conditioned upon their true gender, the true sex value. And then in order to kind of allow this model to still work, we have to still maintain in the latent representation some of the actual race variant features, like some of the other features that actually do correlate with the race. We have to still maintain that in another part of latent representation in order to kind of make the image still look realistic without kind of breaking down the final image too much. But so what I'll do is I'll kind of just go a little bit quickly here. This is just restating the kind of formulations from before, that what we want to do is, make the skin type, independent of our predicted sex value while being conditioned on the true value there. So what we end up doing is, I'll just go to here. We show that the R results of this, it's at least in our final kind of classification accuracy, it's at least as good as existing methods that are trying to enforce this independence with the skin type. We are at least as good as these other methods, but we also maintain a lot of the other attributes of this generative diffusion autoencoder model. So we can kind of take this model and generate new images of the same skin type, where we can define, we can say, segregate which part of the representation corresponds to what kind of attribute of that person. We have a lot more control over what our representation and how the model is working, because we're able to kind of just add on, bring in any kind of image encoder and add on this conditional dependence enforcing feature. So let me just keep going here. Okay. So one interesting thing is, so like I was saying before, we enforce kind of this conditional independence constraint on part of the latent representation. And so what ends up happening when we do that to the representation space directly, we can essentially freeze these features that are independent of the race and only adjust now these race variant portions. And you can see, like, looking across each row, like we're able to actually like separate out what that part of the latent representation is actually encoding. So if we are only adjusting that part, we can basically adapt kind of the skin type while maintaining as much as possible the other features and keeping those the same. And so you can also see the whole point why we have this conditional dependence formulation, where we also have to look at kind of the sex of that person, is that the different skin color representations, it's actually represented differently depending on your skin type, right? So it's not the way kind of the representation might change is going to be different for like male skin type or male gender, right, versus the female gender, in the way that maybe like the hairstyle or other attributes change, the way that the skin type changes, that has some underlying the way that what your sex is going to impact how your skin type is going to manifest in the final image, if that makes sense. And so that's kind of showing you what this conditional dependence formulation that we give provides beyond just like a plain kind of maybe trying to make sure the skin type has no impact at all in that part of the representation. So there's some nuances there that maybe I should explain later when we have more time, but there's so you can see kind of what the effect of this is, and looking at what images we're able to generate when we kind of affect or interpolate between only this part of the race invariant portion of the representation. And then we have one other part here. So if you were to kind of do the other way around, and so now we freeze this portion of the latent representation that we
made to be the race variant portion. And now we changed the other parts. You can see that kind of the skin type would remain the same in all these images, and maybe like the background or the other attributes can now change. So just to kind of show that this is able to separate out what parts of the latent representation are encoding for what. And so, yeah, I'll just go on to kind of this. It's the equivalent causal diagram, you could call it, of what's actually going on, where we have a lot of factors impacting the image, right? The person's sex, their skin type, and a lot of other features we call eye, like the lighting conditions or the background, the other kind of, let's say, like other kind of attributes of that person's face that doesn't have to do with the skin type or the sex. But what our method is effectively doing is we can remove this direct effect of the skin type on the image while still preserving the effect that the skin type plays on the image via this gender kind of variable. So this is just why what we're doing is kind of just taking as like fine-grained of an approach as possible in enforcing this fairness notion, because we still want to preserve some other ways that the skin type can still be affecting that final image. But yeah, anyway, I guess just to kind of wrap up and summarize things here, we introduced this conditionally independent notion for causal representation learning. We apply it to some downstream tasks like image generation. And what happens is we have a way to kind of understand the representation, the image representation, and we're looking at ways we can apply this now to like medical imaging areas or other formulations of conditional independence, other than that, this equalized odds condition. If there's any other kind of fairness notion that can be expressed through this conditional independence idea, we now have a way to model that and enforce that in the representation. So yeah, just a very kind of super fast run through of this, but yeah, hope it's interesting. Thank you.
Yeah, thanks to the speaker. So please reserve a question to the poster session. Okay, do you introduce?
Okay, so we will, before breaking for lunch, let me introduce our keynote speaker, Dr. Richard Zhang. He comes from Adobe Lab, and before joining Adobe, he was a PhD student in Berkeley, as well as he did his master's at Cornell. But more recently, in 2023, he has been recognized as an innovator under 35 by MIT Technology Review. So let us welcome Dr. Zhang to listen. Today, he is going to talk about incentivizing opt-in and enabling opt-out for text-to-image models.
Yeah. Okay, thanks so much for the kind introduction. Give it a minute while I plug in. Okay, great. So everything's working?
Go ahead.
Okay. Hello, everyone. So this is incentivizing opt-in, enabling opt-out for text-to-image models. So there's been astounding progress in image generation, and these days there's actually a plethora of different models that are serving as the backbones of content creation workflows out in the real world today. But these models don't come from thin air. Ultimately, they're a reflection of the underlying training data that went into them. And where does training data come from? Well, ultimately, it comes from people or contributors. Now, unfortunately, these people right now are cut off from the models that they're fundamentally enabling. And so while us researchers and founders are excited, there's been pushback. There are ongoing legal battles, Hollywood strikes, digital artists are pushing back as their data is being used without their consent or compensation.
So what can we do about this? So in this talk, we'll discuss several efforts that we've undergone in reconnecting creators back to models. And we're looking at this in several different lenses. So one is that we believe that in many situations, creators should have the right to opt out of a model. Now, of course, that's very difficult to do after training. And so something we're looking at doing is what we'll call ablation, being able to efficiently remove your data or your concepts from a already pre-trained model. Next, we'll look at actually trying to incentivize people to be an active participant in a model. And so part of that is attribution, that is tying elements like synthesized elements to the specific training elements that made them possible. And finally, we'll look at customization, which encourages people to take an active hand in participating in creating a model by adding their own customized concepts. So we'll do that first. Okay, so this is a paper that we published in CVPR last year called Multi-Concept Customization or Custom Diffusion, and Nupur Kumari was the first author here. And so where we started here was that text image is not perfect. If you take a pre-trained stable diffusion model and ask it for a photo of a moon gate, this is what you get. Here's another random seed. These are actually not moon gates. This here is a moon gate. It's like an Asian architectural element here. And beyond that, there are other concepts that aren't going to be in the model. For example, your personal pet, your personal objects, or maybe some drawings that you've done on your iPad, which my colleague Aaron Hertzman likes to do. So you may want to add these into a model. And here in this project, we're looking at how we can efficiently add a concept into a already pre-trained model. Okay, a quick review of diffusion models. There's a forward process that adds noise and a reverse process that learns to remove the noise. And so you take a large scale data set, sample an image from it, add noise, right? And then you train a model that predicts the noise, and you see how well it does with a simple L2 loss. Okay, so how do we utilize this procedure to inject a user's concepts into the system? Well, a very straightforward approach would be we simply replace the pre-training data set with a small fine-tuning data set. And so, of course, that's the first thing we try. We fine-tune with a small new data set. And here's the result. So here's the pre-trained model, and here's after fine-tuning. And this simple baseline really works really well. We've now added this concept of a moon gate into the model, and we can actually compose it with different priors that are in the model, for example, putting this moon gate in snowy ice. So that's good. The simple thing worked. The problem is that there's a lot of storage and compute that's needed. For every single concept, you'd have to create a whole nother copy of the model weights in your system. That's going to get ugly real quick as you keep adding more and more concepts. And so the next thing we did was we asked, is training the whole network really necessary in this process? And so looking into the architecture, there's different elements like ResNet, self and cross-attention layers, and these kind of repeat. And a special note is the cross-attention layers map elements of the text to visual elements in the image. And so we ran a pilot experiment where we trained the whole network, and then we looked at the relative change of each of the layers. And then we found that the cross-attention layers are the ones that changed the most. And so our hypothesis was that the cross-attention layers are perhaps of special importance in this case. And so we tuned the layers. We kept everything frozen. We just tuned the cross-attention layers, and we found that actually you can get away just tuning the KMV or key value layers there. And you end up having to only tune 3% of the parameters in this case. And if you do that, this is the result with tuning all layers. This is with tuning cross-attention only. And you see that it does just as well. So we've kind of gotten away with tuning much fewer layers. And one additional note is that we don't want to blow out nearby concepts, right? We don't want to overwrite the concept of a moon while learning what a moon gate is. So we also have a regularization data set to keep what was already in the model kind of well preserved. Okay, so at this point, we can fit a concept in about 6 minutes with a much more kind of memory usage, which is good. Okay, so from here, my colleague Jian put in his dog into the model, let him wear some headphones. Nupur put in her toy plushie and rendered it as a watercolor. And we were kind of just having fun. And we took my colleague Aaron Hertzman's iPad drawings with permission, of course, and made some additional drawings here. Okay, and so that's not the end of the story. So far, we're only adding one concept at a time. But in many cases, you may actually want to compose together multiple concepts together, right? We want maybe wooden pots in the style of Aaron's drawings. We want to put Stark in front of a moon gate. Now, how do we go about doing this? Well, the naive approach would be to jointly train, take our previous method and just train 2 concepts at the same time. The problem here is that it's going to be inefficient. You'll have computational blow up for every single combination of concepts that you want. So what we did instead was look at modular training. That is, if you could train kind of a bank of concepts one at a time, and after the fact, have a lightweight stitching process in order to merge them together. And that's going to scale much better and hopefully give as strong visual results. Okay, and so we have some results here doing this. So rendering the wooden pot, the style of Aaron's art, putting Stark in front of a moon gate, or putting this QCat inside of a base. Okay, now our method does have some limitations. For example, it's difficult to separate out the identity of two different objects. And this is actually a limitation that's kind of inherited from the pre-trained model. So any kind of advances in the pre-trained model should hopefully carry over to customized models as well. That's something we're actively working on. Now, our work was a part of a kind of group of initial works in this subject. So there was Textual Inversion and Dream Booth, which were all really great works in addition to ours. They kind of explored the span of different network architectures that could be tuned. And our work specifically looked at embedding or combining multiple concepts together. So that was something that our paper at that point uniquely provided. But this is a very active research area. So now this isn't going to even be all the papers that'll be in this CVPR, but there's works in fast customization, multi-concept, and making things smaller as well. So this is really an active area, an exciting active area of research. Okay, so far we've looked at adding concepts into a network, but of course there are already a lot of concepts in the network. For example, there are people's personal images, like of a grumpy cat. That's someone's cat, or there's like copyrighted content. These models can also emit different artistic styles. You know, living or artists that are living. I mean, Van Gogh is probably okay being the model, but they're living artists that are kind of having their online identities actually kind of co-opted by these models as well. And then there's this issue where some images are actually memorized, so it's emitting exact images out of the training set. And so in a lot of these cases, we may not actually want the model to be able to produce these kind of images. And so here in this next section, we're looking at whether we can actually remove these concepts from the model. Okay, so this is a work called Concept Ablation, also led by Newport. And so where we started with was we're thinking, you know, for content creation platforms, data opt-out are really standard practice. But for generative models, that's actually very difficult to implement because ultimately you see that all the training data is now entangled in the weights. And so how can we actually remove things? Well, basically we're looking at removing things just one at a time, and that makes things a bit easier. Okay, so let me present you a naive baseline first. So first, we could go through the whole pre-training set. We could find all the relevant images to a concept that we'd like to ignore or remove, for example, a grumpy cat, and we can remove them and retrain the whole network. And that's definitely going to work. But the problem is, of course, that that's extremely time-consuming and computation expensive. You won't be able to do this, you know, every time you get some sort of takedown request, or if you've made a mistake in your training set, you're not going to want to undergo this process all the way over again. Okay, so what's a potential solution? Well, this was the diagram for training a diffusion model. Recall that we're here minimizing an L2 loss. Maybe we can just maximize an L2 loss instead. Okay, so let's try that out. So on the left here, we have a grumpy cat. On the right, we have a nearby concept of a short hair cat. So we want to destroy the generations of grumpy cat, but we want to keep the generations of the nearby concept. And so if we maximize loss, we're able to do this with the grumpy cat. We're able to remove him. But the short hair cat has also been severely degraded, and that's not what we want. And furthermore, if we keep training, the grumpy cat image will actually completely diverge as well. And so this is not behavior that we want. We want stable training, right? We want to remove the concept, the target concept, but we want to preserve nearby concepts, and we want this to be kind of a stable process. Okay, so we instead of the naive approach, we looked at this in the form of distribution matching. And so the idea here is that we have a photo of a grumpy cat. What we'd like to do is replace that distribution with a photo of a cat. So we want to override it with a superclass instead. Okay, so you want to take this grumpy cat distribution and morph it into the cat distribution. Okay, so our method here is we can query the model for a condition that on a grumpy cat. We can then condition it on photo of a cat. And then we can take the bottom branch and use that to overwrite the top branch. And we put a stop gradient on the bottom because we don't want to corrupt the cat conditioning. Okay, so we're in essence using the model to supervise itself. Okay, and so if we do that on the left, we are able to once again destroy the grumpy cat. But in this case, the nearby cat was minimally changed. So this is what we wanted to do. Okay, so from here we looked at applying it to a whole bunch of different cases. So here we have some copyrighted character of R2D2 and Nemo, and we want to make sure that Disney's happy. So we can make R2D2 a little bit more of a generic robot and make Nemo into a more generic fish. We've also seen this phenomenon where a network will collapse and emit a specific training image many, many times, which is unwanted behavior. And by doing some ablation, we can apply that to this case as well and add some diversity. Okay, and then we can also look at this example of different artist styles. So Van Gogh on the left has this trademark kind of wavy lines. Our method is able to erase that. And on the right, we have Greg Rutkowski, who's an online artist that people started querying a lot for within these models. Okay, there's an even more kind of nefarious case that our system can target. So the pre-trained model is going to have concepts like kids and guns. And on their own, that's actually okay. You can generate kids and guns separately, but of course, a generative model is happy to compose them in ways that you may not like. And so if you wanted to remove this combination of kids and guns, just from a data perspective, you would have to remove all the kids from your model, from your training set, or all the guns from your training set, which is really way too heavy-handed. But our system instead can actually target just this specific concept. So we can still generate kids, we can still generate guns, but we don't want to generate that concept combined together. Though you can see it's not perfectly disentangled in this case. Okay, so in this work, we looked at removing concepts by overriding the network with itself in this efficient manner. There's some limitations that really there's not completely perfect disentanglement. And there are, of course, like philosophical questions about if something is really removed, that's really hard to evaluate. And so there's more room to push in this area as well. Okay, so far in this section, we looked at enabling people to opt out of a network, which I believe in many cases should be their right to do. But of course, we don't want everyone to opt out, right? These are positive technologies that are enabling content creation workflows for people who otherwise wouldn't be able to participate. What we do want is actually people to actually be incentivized to opt into a system, because actually by all of us working together, we can get more effective Gen AI systems. Okay, so how do we actually incentivize people in a positive way to opt in? That's what these next group of works are going to be about. So this work is on data attribution. And so the first author here is Sheng Yu. Okay, so the problem statement here is that given an image that's been generated from a model, we'd like to find the specific elements within the training set that had high influence for making that generated image possible. And we can think about that as these influence scores. Now, there's a very fundamental challenge in this problem, which is that ground truth is just unknown. You know what's in your training set, right? You have millions or billions of images, but through this kind of training process, they're all munched together and distilled into network weights. And it's really hard to understand the individual contribution of different training images into a specific generation at the end of the day. So how do we actually gain insight into the relationship between training images and synthesized images? Well, in some way, we need to intervene in the training process in order to kind of start understanding and analyzing that relationship. And fortunately, for us, we've actually been working on this, right? We were working on customization, we were working on ablation. So we start to have some tools for being able to do this. And so that's our first attempt at this problem is our idea is to leverage our insights in customization and see how they can be used for model or data attribution. So this work is called attribution by customization. Okay, And so the idea here is that we're given this generation from a model. We don't really know what influenced it, but if we intervene in the generation process by adding an image and customizing towards it, by construction, we know that this building here was generated, was heavily influenced by this exemplar image. It's not only influenced by it, but it's definitely heavily influenced by it. And then we can ask an attribution algorithm, which is the influencer out of this exemplar or other random images. And we have the ground truth, which is we know the exemplar. So in essence, we've converted a very difficult attribution problem into a more straightforward retrieval problem. And we kind of have language and tools that we can leverage for doing it. Okay, so in this work, we set about curating an attribution benchmark. There's two parts of it. One is more artistic centric. So that is, we take a pre-trained model, we can fine tune it towards a collection of art pieces from an artist, for example, Fernando Botero, and we can get generations like that or like that that are heavily influenced by this artist. Another part is this object-centric section, which we looked at for this building example. Okay, and so in the end of the day, we trained 18,000 customized models, and we gathered 4 million samples from those models. So we now start having kind of a medium or large-scale data set for learning and evaluating attribution. Okay, and so how do we do that? Well, we can learn attribution from customized models in the following way. We know that an exemplar kind of gave way to the synthesized image. We can then turn the problem around by looking at different elements in the training set. We can then ask an attribution algorithm which image was the influencer. And if you're doing some sort of kind of embedding matching kind of procedure, at least, you would want the ground truth to be closer than the other distractor images. And this starts looking like something we have very standard technology for. We can use contrastive learning to do this. So we can learn a feature space that puts corresponding images together, right? What that means is if you have corresponding images, you want their similarity to be higher. Non-corresponding images should be lower. And we can have a base representation here and a learnable head on top. So we can evaluate different pre-trained models and then calibrate them to be more effective towards attribution. Okay, so we can actually measure different feature spaces as to how well they perform attribution. So on the y-axis, we show on artistic models, x-axis, we show on object-centric models, up and to the right is good. These are different feature spaces. We see that these representations here are strong for objects. Clip has middling performance, but on top of that, we can calibrate them for our purpose. And what we see is that Clip is actually primed for large improvements after training. And here our paper kind of defines this Pareto front that trades off between artistic style attribution and object-centric attribution. And so it kind of sets a benchmark for future methods to continue pushing it. Okay, so from here we can show some custom diffusion results. This is before and after calibration. You see the ground truth moved up from the 4th spot to the 1st spot. And here is kind of with more artistic styles. And our method was able to capture one of the ground truth images that the baseline wasn't. Okay, and just for fun, we can run this on some stable diffusion results as well. So generate image and the attributed, and so on. Okay, so there are some problems with this work. The biggest weakness is that the pre-training set is ignored because we know that the pre-training set, line 5B, has influence on the custom diffusion examples. It's just in this case, we kind of really only kept track of the exemplar. And so we wanted to kind of dig into this a bit more. And so we're inspired by prior work that looks at, instead of adding an exemplar in, which is what we do, they instead look at the idea of removal. So Shapley values, this landmark concept in economics, and it was an implementation of that is to train on random subsets and analyze a population of models. And there's this seminal work of influence functions as well as follow-ons of that in both discriminative and generative settings that looks at up or down weighting a training image, making some linear approximations and seeing the effect on an evaluation. But what well, a lot of this comes down to is that properly evaluating attribution on a large scale training set is actually really challenging. Okay, so how do we actually go about doing this? Well, what would like a gold standard evaluation of attribution be? And one version of them is this. So if you have a training set, it's going to emit a certain image. If you're able to identify the highly influential images, what it means is that if you remove those highly influential images and only train on the less influential images, that model, that counterfactual model, we'll call it, should not be able to generate the original synthetic image that you're targeting. Okay, so if the critical images are identified, removing them should destroy the generation. And that can be measured in a few ways. One is you can check the DDPM loss if you're using a diffusion model, or you can ask it to try to emit the image and assess the difference to the original generation. Okay, so this is kind of a gold standard definition. Now, one difficult thing about it is it's really expensive. And that's why a lot of previous works didn't go about really scaling up this evaluation. But in our next work, we decided, forget it. You know, it's really hard to make approximations to this gold standard evaluation. Let's just do it. Let's just train all these models from scratch to do evaluation. I had a very brave kind of collaborator who was willing to do this. Okay, so we can actually do this for modest data set sizes like MS COCO. We're not going to do this on stable diffusion because that's going to be way too ridiculous. Okay, but so let's work towards this evaluation. Now, the question is, how do we actually find these influence scores? Now, I can give a brute force approach that tries to approximate this counterfactual evaluation. What we can do is we could, as a thought experiment, train on a whole bunch of subsets of the training data, train all these models, and then analyze this population of models and see which one is most damaged when trying to generate this synthetic image. Now, as you can just see from this diagram, this just looks too expensive. And there's no way this is going to be tenable for all subsets of the training set. You know, training these things from scratch even once is way too expensive, let alone for combinations of the data set, or even if you do like leave one out or something a little bit more clever. So what can we do here? Well, this is what we looked at in this recent archive. So we started thinking about how we can leverage our insights in ablation or unlearn. So what we're going to do here is have an unlearning procedure that tries to remove the synthesized image from the pre-trained model. And our hypothesis is that if we do that and then take this unlearned model and evaluate which one of the, sorry, there's a little bug on my slide. If we look at which one of the training images here are actually damaged by proxy, our hypothesis is that this will identify or form a causal link between the training images of interest for the specific generated image. Okay, so we're erasing the synthesized image and seeing which training images are damaged by proxy. Our learning procedure is we try to maximize loss on the synthesized point, and then we try to minimize loss on the original data set. And that's approximated by EWC, which is a tool kind of from the continual learning literature, which makes a local second order approximation that tries to create some representation of your original training set so you don't stray too far from your pre-trained model. Okay, so we went ahead and did this. How does it do? So here's a generated image. Here's different results from our method versus baselines. And now all of them kind of retrieve buses. They all look reasonable, especially the first two. How do we really know which one is doing better? Well, here we're going to do our counterfactual test. So we're going to remove 500 images, which is just 0.4% of the data set. And we're going to see which generation was actually damaged. And you can see here that ours, if you compare our image of the bus to the one on the left, it's very different, which indicates that we perhaps found a critical 0.4% of the data set that enabled this specific generation, whereas baselines weren't able to do it really as effectively. They're still able to generate effectively this same bus. Okay, we can give one more example of the skier. Here are the different attribution results. as well as the counterfactual evaluation. And again, you see that our method is able to basically destroy this skier more than the baselines. Okay, so we'll just give some more examples here, qualitative examples. Okay, and one thing I'll note is that even though I talked about everything in terms of whole images, there's nothing in our formulation that prevents us from running it just on local regions. So you can take an image with multiple kind of visual elements and do attribution on those elements separately. Okay, so in this section, we looked at attribution in several different ways. One was through customization, that is adding exemplars in. This is able to establish some notion of ground truth, but unfortunately has limited generalization to general pre-training. And so after that, we looked at unlearning, which is kind of, again, leaving one out. There, we're able to efficiently unlearn a synthesized sample, which is able to identify training samples, which we could verify through counterfactual evaluation. Now, this work is not done. It's still expensive to evaluate unlearned models on specific training samples. And so there's a lot of future work to do, for example, on more effective approximations, or even looking at group effects, seeing how different training images, when put together, actually perhaps have some sort of non-trivial coupling effect. Okay, so in this work, we're looking at really this idea of reconnecting creators back to generative models. We're looking at enabling them to opt out when that's appropriate, but also we want everyone to be incentivized and enable them to opt in and participate in this technology as well. Okay, here's the different works that I mentioned. I'll especially call out Sheng Yu and Newport, who are the first authors on these works, as well as my wonderful collaborators. Thank you.
Thank you for your insightful talk. Any questions? I had a strange thought as you were speaking about it. What happens in the degenerate case? At what point the model becomes purely dysfunctional? Because 30% of the people come back and say, hey, remove my data, remove my data. By that time, at what point it becomes dysfunctional?
Okay, yeah, that's a great question. I think for ablation, we looked at what happens when you keep removing, and eventually the removal procedure just breaks itself. And at that point, you might as well retrain from scratch. You know, 30% of the people want out, you should just retrain the model from scratch rather than do the ablation procedure. My feeling is that for like Lion, if you 5 billion images, if you just take a 70% random snapshot, you'll probably get much of the same behavior because there's probably a lot of redundancy in the data set. But there may be kind of unique concepts that if people were to pull, like if Disney wanted all the R2D2 images out, that model should not be able to generate that concept anymore.
So are there some influencers which will 30% of generic data versus 30% containing 80% of the influence?
Yeah, so definitely the kind of concepts are going to be non-uniformly influenced, right? So some things are just like very generic landscapes. You could probably remove like 99% of the data and still get like reasonable looking landscapes. But if it's like a very specific kind of style or character, that influence distributions could be much sharper. And so we should treat all these things kind of differently.
Great. Maybe we should break for lunch with this inspirational talk. Thank you.
Thank you.
So we meet back at
1 p.m.
1 p.m. or after lunch, we can start at 1 p.m. Hey.
Yeah. Thanks so much.
Thank you. How long was it? It was too long. Right?
No, that's fine.
Yeah, no, I need to cut it. It's too much material.
Oh, okay. I mean, don't worry about editing. I think the staff on CPF will edit the video for ourselves. So they automatically edit it, but the video will only be out like 3 months after the event, after today. Sure. Yeah. Thank you.
All right. Thanks.
Like that, you can okay. Do you remember? So you can try and get into this talk with the put in the USB directly.
But where do you put CPL workshop slides? CPL workshops. Okay, I'll copy to my locally, just in case. Okay, yeah, that should work in there. So let me present project mine. Yeah, excuse me. Yeah, sure. Now you need to introduce you. Yep.
Yeah, in view of time, let's get started because we ended up getting extended, we're cutting into lunchtime, but I guess we have to still get going. It's my pleasure to introduce Professor Venkatesh Babu. He is the chairperson of the Computational Data Sciences in one of the premier institutes in India, the Indian Institute of Science, and he did his PhD there, as well as afterwards he had worked in industry as well as in other academia. So he is very deeply interested in vision and deep learning. So today he is going to talk about uncovering and addressing biases in diffusion model. Please join me in welcoming Professor Babu.
Thanks so much. Okay.
Thanks, Professor Nalginathan, for the nice introduction. I'm Venkatesh Babu. Yeah, I'm the chair of the Department of Computational and Data Sciences at IISc. And I'm also kind of a convener for Vision and AI Lab at IISc. So today I thought of giving a brief talk on uncovering and addressing biases in diffusion models. So let's start with what is a bias. So where this bias originate? Okay. So this is actually the reflection of our real world, basically. So the whole world is actually kind of biased with various parameter attributes. So you can see this in various kind of domains as well, right? If you take economics, so the GDP, you can see each country is not kind of, there's so much of discrepancy in the kind of a GDP, as well as if you say per capita income, there is a huge discrimination. So there are some countries which are very rich and some are very poor. And apart from this, even if you look at the corporate world, you can see There are these top 20 companies. If you look at, almost 16 of them or 15 of 14 of them are there in US, and others are kind of spread across China as well as Taiwan kind of places. Okay, and you can see this is kind of this is what is actually happening. And even if you look at our CVPR papers or any of the top conference papers, you can see there are a few countries that dominate and few are kind of having very few number of papers and authors, and some of don't even get represented at all. So this is the real world, and what is happening in the real world comes as a data to us, and then this data is what is being consumed by a model, right? So when you build a model based on this kind of a data, obviously the model itself is going to be biased. So the sole responsibility we want to put why this bias crops up is because of the data, underlying data that we are looking at, right? And so especially this is for computer vision community, you can say once we started deep learning from 2012 onwards, we are heavily data dependent, 100% data dependent, right? And we don't use all this feature extraction kind of a technique, which is independent of data. So once we started using data, so obviously the data which is available online or wherever it is, so this is kind of giving you the bias when you train a model. Okay. Also, the bias, the data set is typically collected by rich corporate companies and universities, which can afford this kind of a data collection. Okay. So that also kind of increases the amount of bias that we see in the data set. Also, language, if you take all the publications that are coming out are in English, okay, and that is going to be a dominant language, and most of the data set that is being used in all LLMs kind of thing, they are kind of biased towards English. Okay, so that is also a major issue because all the other regional languages are kind of not kind of having sufficient amount of data to train such huge models. And the amount of images, language that is present on the internet, that also hugely affects models. Culture is another thing. So bias mitigation is the only thing that we can do because we cannot get an unbiased data set. We don't even know how it is going to look. Even if you very carefully collect these data sets that is going to be unbiased, there are something which we don't even know. There are hidden biases are there, which you will come to know maybe later, right? So collection of data set is when you start doing that, there itself a bias comes in. And so that is how we can build the models because all our models require huge amount of data to train, okay? So what we can do at this point of time is, yes, we build huge models, but it's possible to go and fix the model once it is trained. Okay, so this is the post-correction kind of. So the solution is kind of how we can do bias correction. So that is all we can do as of today. Okay. And biases in deep models are kind of not new. It is there for so many years. So this is one of the 2016-17 models by Amazon. You can see it does not kind of recognize a particular class of people. Okay, so especially darker females, you can see the accuracy is somewhat very subpar, less than 70%. Whereas for lighter males, you can see it's almost 100%. Okay, so this is also coming out of the training data set that you use. Also, if we take other models, they are kind of various models from IBM, Microsoft, all those things we can look at. The light male kind of gives you very good accuracy compared to all other one. The worst performing thing is kind of Asian, black, female kind of category. So the only way what we can do here is train our model with a huge amount of data, and it's going to have a lot of biases. And now is it possible to do something on top of this model to kind of reduce the bias, right? So this is the kind of model that is trained on some phase data set. Can see when we try to generate the data, can see there is kind of it is not quite representative of the gender, basically. So you have many female faces and there are very few. male faces. Similarly, if you use a text-to-image diffusion model, you can see the photo of a doctor. It usually tend to give kind of a male kind of thing. So this is again coming out of our underlying data. So just I will cover a brief two techniques which are prior works, how to mitigate this bias from the diffusion models. One is safe latent diffusion, another one is ITI generation. So if you look at this safe latent diffusion, basically you want to find unsafe direction of the latent space. So that is what is actually represented by this red arrow, which is an unsafe direction. And you wanted to make it kind of a safer, right? So, so basically this is the classifier free guidance where you have the diffusion model, classifier free diffusion model. So now you have some kind of a prompts which will lead you to unsafe direction. Okay, so again, you have to be very careful in constructing this kind of phrases, okay, which will give you the unsafe direction. So once you have this, then you can find the unsafe direction for the diffusion model. So once you know this is the direction in which you're moving towards unsafe region, so you can always go against that and then make your model safe. So that is what is done here. So basically, the difference between the safe and unsafe gives you the direction of how to move towards safe, right? So basically, the added term that is this gamma of what CS is the kind of safe direction. Okay, so you go against this direction and then make your model safe. Okay, so the same thing is being used for bias mitigation as well, right? So if you find a bias direction, you make it more bias. Okay, and once you know how the bias direction is, then you can go against and then reduce the bias. So, but these are all kind of this again a text-based approach, and you need to have the list of unsafe prompts, okay, which manually you have to curate for each of these attributes. The second work is a kind of ITI gen, okay, inclusive text-to-image generation. So what do they do here is actually, so you have a kind of regular prompt, and then you wanted to make it more inclusive, okay. So this is a kind of a headshot of a person. It's a very regular prompt, which is going to give you a biased output. Okay? Now to make it kind of unbiased, so you are going to find out various directions in this. So male, female, as well as black, white, all these directions. So we are going to add kind of suffix to this base prompt and then make it okay. So person, male, white, person, female, black, person, male, black, all those things. So all these combinations that you make it and then use these prompts again, and then to generate your images. But actually you are going to fine tune for each of these prompts as well here. You are going to optimize your text prompts for this. So basically, again, this is a text-based model. Okay. So they optimize the text embedding here, and then the biases from the reference set will also kind of the model is going to inherit in this. So if you are going to use few samples for mitigation, if these samples are not good, then you are going to be biased again because of these reference images. So now the question is how to mitigate biases for unconditional diffusion models, right? And the one way is actually guiding the iterative denoising process with the reference attribute distribution. This is one of the ways actually. So you have the generative model, it gives you the output. You look at how the distribution is, okay, and you'll find out whether it is biased or not. So once you know how much it is biased from the reference distribution, then probably you can mitigate that, okay. So this is one of our works which we will be presenting in the CVPR on 19th of November. So what we try to do here is kind of a balancing act, how to use this distribution correction for the generated output. So basically, this is a regular diffusion process, and the reverse diffusion process, you start from the noise and you reach the generated image. Yeah. So we are going to intervene in each of these steps and then going to condition in such a way that you want to produce a particular output. Okay. So this is why we need the classifier guidance. For example, I have a image. These are the noisy version of the image, and I give it to the classifier, and I get the classification output. Okay. So if I wanted to move this towards a particular class, basically, I'm going to add a term to here in such a way that the resulting output belongs to that particular class. Okay. So this is typically done this way. So at each step, you are going to have a classifier. For example, if you're having 50 steps and you are going to have some 50 models between the noisy version to the generated output. And you are going to say, okay, so you have 50 classifiers, and each classifier gives you a direction in which you have to move to get this particular. Here we want to convert this particular phase into a male phase. So this guidance comes from the classifier in such a way that at each step you push your generated output towards getting the male phase, right? But the problem here is actually the training is pretty slow, okay? And because you're having 50 classifiers, and each classifier is a kind of a bulky one. Typically you use a resonance 50 kind of model. And the generation becomes slow because there are 50 steps and you have to train all the models in this line, right? So how to make this kind of efficient? So that is the direction in which we are going to look at. So what we looked at is the hut space, which is actually the bottleneck of the unit, right? So which is actually more semantically meaningful here, right? So this hut space is kind of represents the latent, is so semantic that you can use this directly for a classification purpose. So here you just add a simple linear classifier, and then you can easily classify this into one of these categories, right? So it's not a bulky model here. Here it's a simple single layer linear model, basically, right? So linear headspace classifier. So you have 50 classifiers, but these are very simple and then easy to train also. So now you can inject, that is the bias direction to each of these steps, 50 steps, and then make your model produce a male phase of output. So it's quite efficient here. So usually you train for 30K iterations in the previous version, where here we need only 2K iterations. And it's quite faster also, 7 times faster than the other approach. And how to move this, how to get the required distribution. So, here, for example, this diagram, you see there are few male phases and many female phases. And what you're going to do is, I want 50% male, 50% female. You randomly sample the excessive female phases and then try to move towards the other side, okay? So what happens is, since you're randomly sampling, the samples could come from anywhere, okay? It's very close to the boundary, decision boundary, or it could be from far away from the decision boundary, right? So when you try to push each sample to cross this boundary to get the male phase, so you don't get the proper output in that kind of a scenario. So what you can see is when you try to push all this red ones towards the male, across the boundary, can see is the phase gets distorted, right? So very strong female phase, you are trying to push to across the boundary and make it a male phase, which is not appropriate, right? So whatever is closer to the boundary is easy to move, and even if you move, you're not going to get this unexpected artifacts, right? Right. So what to do in this kind of scenarios? Okay, whether we can do a distribution matching instead of going at a sample level, right? So all we are going to do is, since we are doing a batch processing, take a batch, and then all the images coming in the batch, you try to classify and then see the distribution, how it is, okay? And you go ahead and then correct at that level, okay? So this is what we are doing here. So you take the headspace thing and then try to classify all the images in a batch simultaneously, and then see how likely they belong to each of this category. Yeah. So now you know, okay, you want a specific distribution, okay, 50% male, 50% female. Now you can look at this, how this required distribution is away from the current distribution. And you just find the distance measure between these two distributions, scale divergence kind of thing, and then use this as a loss function and then train your model, right? So this kind of a guidance is a kind of makes you, it selects the samples that are most likely easy to transform from one to the other. You can see here. So you can see if you partition this latent space into various quartiles, you can see the first one is kind of dominating. More than 40% of the samples are coming very close to the boundary. And as you go far away, the number of samples selected are getting lesser and lesser. Also, if you look at the output, you can see the phases are kind of very clear. So this is, here you can see this phase is kind of changed to a proper male phase. Okay. And yeah, here also you can see this one. Yeah. So the output is kind of very nice compared to the sample-based approach. So some results on gender, debiasing the gender, you can see here. So this is the kind of other approaches. When you look at the last one is the proposed approach. The other one is kind of universal guidance where you have only one classifier to do the job instead of 50. Whereas sample-based guidance also is not doing well. You have fewer male phases here. And when you do the distribution balance, yeah, the output is also nice and you have a balanced output. So similarly, if you look at the eyeglass category here, you can also see the proposed approach is giving you a very balanced output. So how to generalize this for a kind of stable diffusion kind of model where you are going to give a text input as well, right? So these are some of the outputs, okay? A photo of a person. So you can see here, the proposed approach gives you a proper number of male, female phases. Even for this photo of a firefighter, you can see it's quite balanced across the gender. And so these are some of the numbers to say, okay, the proposed approach indeed works well. And so this first part of the talk, I'll quickly cover the other work which we presented in ICCV last year. So when we generate the images, we wanted to look at how representative these images are with respect to the region, okay? Whether it is representing fair enough for all the countries or it is representing a particular country well and not the others, right? So if you look at this output, photo of a software engineer, you typically generate this kind of male outputs, whereas photo of Indian person, so it gives you something which is kind of course, they are Indian, but it represents a very small part of the community. It doesn't represent the entire community from India, right? So we wanted to check how the generated outputs are inclusive, okay, with respect to the region, right? So what we did here is kind of, there are various attribute nouns we use. So for example, we generate a house and then ask each one whether it is actually representative of your neighborhood there, okay? So if you look at this, these are the generation from DALI stable diffusion. So it may not be a representative of various parts of the world. And why it is important, we know obviously because this data is again and again used for various applications. And, you keep on adding more and more by modifying these data. So whatever is there, the bias that gets amplified. Okay. So basically, this is what we did for, we picked up to 27 countries and then we used the mechanical Turkers and then asked each country mechanical Turker how this particular image is representative of your neighborhood, okay? So there are two types here. One is unprompted, another one is prompted. Without telling the country, you just generate and then ask. Okay. The next one is you give the specific country name and then generate the image and again ask. Okay. And this is done for both two popular models, Stable Diffusion as well as DALL-E. So basically, 1 means it's not at all very likely. 5 is kind of generated image very closely resembles my neighborhood. And if you look at this output, you can see, so 3 is the kind of a midway, okay? Whoever crosses 3, okay, it is highly representative of that country. Less than 3 is not representative. So there are only 2 countries come out without any prompt, right? How good this particular house representing your neighborhood. Only US and India, they come out, and all others are kind of below that. Whereas in Stable Diffusion, yeah, only US comes out in this. Whereas if we add the country name, country agnostic, whereas this plot shows both country agnostic and once you add the country name, how it improves the generation. Okay, so all the generated output with prompt improves dramatically, right? And all the scores almost crosses the middle line 3, right? And this is for DALL-E. This is very kind of representative. All are very close to 4, between 3 and 4. Whereas Stable Diffusion, yeah, it's kind of, it is not touching 4. So yeah, it at least reaches the middle one. So these are some of the country-specific output. So these are some of the examples. Okay, so how the houses are shown for various countries, DALL-E and Stable Diffusion, right? So you can see clearly, yeah, so the Japanese houses, you see that the specific structure that is coming out again for the European countries. You see this kind of a specific windows and then other decorative elements. Okay, so again, what about the training data? How they are coming from? Okay, you can see here, this is the huge long tail distribution. Most of the images are coming from US, UK, and then Canada, all this kind of places. These are the top 10 countries. You can see there itself a huge this thing. So one is dominating, really 1 or 2 countries dominate. All others are kind of representing very less amount of data. This is for 2 attributes. One is for the house, another on the right side is blue is for the flag. So this is the training distribution. There's a huge amount of bias. And one more thing, what we noticed is photorealism. How does it help? So when we ask for, okay, generate a photorealistic image, then actually it improves. Okay, so we are able to easily guess looking at the photography output. So if it is a kind of a sketch or something, we are unable to guess easily. Okay, so the correlation basically improves when you have a photographic output. So basically, yeah, these are kind of future directions in which you have to look at. So how to automatically estimate the geographical representation? Because getting mechanical Turkers from various countries, it's not at all easy. For about 15 countries, we could not even get a single mechanical Turker. So we have to drop those countries. Only for 27 countries we could get. So that's not a scalable approach. So there should be another way of trying to get from the huge data set. Is there a way, indirect way that we can find out whether GPS tag or somewhere it is mentioned the state or country name? So pruning all this data, whether we can automatically collect data from the huge data set. And yeah, so how to augment for the underrepresented countries is also one of the important directions that we should look at. And so we need kind of improved evaluation for underrepresented countries. And because we always talk about inclusive models, right? So if there is less amount of data, then it is definitely not going to be represented properly. So how to make an inclusive model that can generate data considering all the regionals, all the countries. So then actually, yeah, so we need to go ahead and then it's not an easy task, of course. So we need to put a lot of effort to make the model more fair and unbiased. Thank you. Any questions?
Okay, we have time for a couple of questions, some comments if you want to say. Yeah.
Hi, thank you for the great talk. I think like it's a chart where there were many groups that look like US and India, although in the training sample we saw a lot of groups from US and UK. I didn't quite understand why that happened.
Okay, so that is a different data set. We started collecting from what is the data set that we use? Leon data set is the huge data set which is available, right? Which has image text pair is there, right? So we are trying to clean this data and then try to find out this country specific images. Basically, even house is there may not be house. So you have to prune in so many ways. So after collecting some data, and then we looked at what is the distribution. That is actually another work actually. This is not the mechanical Turkers they looked at, right? Yeah, that's a kind of different data.
Hi, thank you for the very interesting talk. Peter also mentioned that current approaches are not scalable and you need to find some alternate approaches, right?
It's not the approach itself. Okay.
Sorry, the way to identify what.
Correct, yeah.
What do you think about using foundation models as experimental tasks and then using them to, so instead of mechanical talking, have them maybe they might have some weaknesses themselves, but even the acquired weaknesses.
Okay, so foundation models also they are trained on the data, right?
Yeah.
Isn't it? So if I give an unseen image, when newly it is coming from a remote country, right? It has not seen this kind of an image before. So it will try to classify as into one of those existing categories, right? So bias is already there in all these models, which is trained with a huge amount of data also, right?
It will be noisy. It will be, they have their will be noisy, but do you see an approach where you can combine this noisiness? Because
that's what, yeah, so that's what we are doing actually. So the huge amount of data we are using to prune country-wise how many images that we can collect based on that. Still, there will be a huge long tail distribution that will be there, but at least we can get some amount of data for unrepresented countries, right? Once we get the data, probably we can augment this with other techniques, generative techniques, and then use it. Yeah.
Okay, let's thank our
So next we have a paper presentation entitled Force Efficient Machine Learning with Data Augmentation, Guided Loss Increasing to Prevent the Catastrophic Model Utility Job.
Thank you. Oh, that. Yeah, Richard, come on. You don't have it. Okay. Yeah, can you share from Zoom? Oh, sure, from my computer. Yeah. Can you go to Zoom and share screen? Yeah,
You're in muted, right?
Okay.
Okay. Try again.
Is that okay?
No, I'm looking at those. It's,
Not.
yeah. No, I don't know why it's not shared. Can you share that again? On my screen it's okay, but it doesn't share
No, this is still showing the old,
the previous one.
did we share your screen on the Zoom?
Hold on.
Yeah.
Give me a few minutes. Yep. Go ahead.
Hey, hello everyone. My name is Tasuri Choi from NC University. Okay, NC University. Today I will present our work towards efficient machine learning with data augmentation, hybrid loss increasing to prevent the catastrophic model utility drop. This research was conducted in collaboration with my 3 colleagues and our advisor, Dongbin Nam. Machine learning is a process that allows a model to forget specific data used during training. This is crucial for privacy. This is crucial.
Do you change your slides? It's not on Zoom.
Yeah. Okay.
Yeah. Do you connect to the network and then yes.
Yeah.
Because it doesn't change it on Zoom accordingly. Is it your network problem?
No, it's not. Maybe.
Share the entire screen. Yeah, okay. Now switch the slides. Yeah, it works now. Yeah.
Okay, so machine learning is a process that allows a model to forget specific data during training. This is crucial for privacy and compliance with regulations, which mandate the right to be forgotten. By enabling machine learning, we can protect personal information by removing the influence of specific data. Let me explain the process. Initially, you have a trained model, data original, which has been trained on data set that includes both data you want to retain and you want to forget. The learning process involves updating the model to only retain the data you want to retain. And ensuring that the influence of the data you want to forget is removed. This results in the unlearning model, which no longer retains information from the forget data. In the domain of machine learning in image classification, several works has been explored. First, we have a loss increasing method.
This directly increases the loss on the forget data to enforce unlearning. Next, the data separation method. This method split the training data into shards and retain only the retained data. Finally, we have model manipulation method. This method uses teacher-student frameworks to transfer knowledge while unlearning the data. However, this method can be computationally expensive, require additional resources, or might not fully address the utility drop issue. So among these previous works, we have particularly focused on loss increasing strategies. They are effective at learning data, but they can also accidentally change the important features, leading to significant decline in model performance. As you can see in this graph, the model's accuracy and final score drop sharply after a certain point. To address this issue, we present a novel method called guided loss increasing. It includes additional classification loss guidance, which adds extra guidance to make sure the model don't hurt the model. Don't make sure that the changes don't hurt the model's performance. Now let's define the problem we are addressing. We focus on task-agnostic machine learning. This means we aim to unlearn specific instances from the model without changing the fundamental problem the model is designed to solve. The left figure represents one of our experimental tasks where the model's objective is age classification. Before unlearning, the model has noticeable activation for an image we want to forget. After unlearning, the model no longer retains the information, but still performs well on new test images. And the right is the dataset configuration. We start with the original training dataset, dtrain, which is split into two parts, dretain and dforget. The test dataset, dtest, is used to evaluate the model utility, and unseen dataset, dunseen, is used to evaluate the forgetting score by comparing the model's responses to the forget data and unseen data. This setup allows us to efficiently manage the unlearning process without disrupting the model's primary function. So in our method, guided loss increasing, we use the data augmentation method that guides the direction of data updates. We start by sampling data from the retained dataset and adding perturbation. The goal of this perturbation is to increase the distance between the perturbed data and the data we want to forget. The perturbed data is then used to update the model's parameters through a gradient update. This ensures that the updates do not affect the critical features of the retained data set. Now let's look at the components of our method. First, class loss guidance optimizes the retained data to increase the distance from forget data while maintaining original classification. This is achieved using the following optimization equation. Eta represents the perturbation added to the data, and the first term represents the distance between the perturbed data and the data to forgotten in the feature space. And the second term is the loss function for the perturbed data and its true label. Next, class loss warming up gradually increases the guide loss rate during training to prevent rapid escalation. This formula slowly increases the importance of class loss guidance during training. By starting with the lower rate and increasing it slowly, we prevent sudden changes that could make the model unstable. So at the bottom, you can see the examples of original and perturbed image samples. This integrated approaches ensures effective learning while preserving the model's utility. So let me discuss the training setup and evaluation metrics used in our experiments. First, we use two data sets. MUFA is used to multi-class age classification, and LOOKUP is used for multi-label classification with labels with gender, age, and whether the subject is smiling. We implemented our method on 3 different models: ResNet, wide ResNet, and EfficientNet. For evaluation metrics, we organized 3 measures. Model utility is measured by test accuracy on the retained data. Forgetting metric is measured using membership inference attack, which compares the model's responses to the forget data and unseen data. This evaluates how well the model has forgotten the data it was supposed to learn. The closer the MIA accuracy is to 50%, the better the learning performance. To combine these 2 metrics into a single score, we set the final score like this formula. Let's take a look at our results. The original column shows the performance of the model before any unlearning. The retrained column shows the performance after retraining the model with only a retained data set. We conducted experiments with other benchmark methods for comparison. Our method achieved the highest final score and lower forgetting scores on both data sets. This demonstrates our method effectiveness in both unlearning and maintaining model performance. This slide compares the forgetting performance of different methods using loss distribution. The blue peaks represent the forget data set losses, and the red peak represents the unseen data set losses. Our method achieved a better overlap, demonstrating the superior forgetting performance. We also use Johnson-Shannon divergence to compare the performance of different methods. JSD measures the similarity between 2 probability distributions, and lower JSD values indicate a more effective forgetting performance. Our method shows strong performance. Importantly, we propose the JSD can serve as a robust metric for unlearning evaluation due to its high correlation with the membership inference attack score and its ability to reflect probability distribution. So in conclusion, our method fully effectively unlearns specific data while maintaining model performance. It outperforms other benchmark methods in both final score and forgetting score. Thank you for listening.
Since we are a little bit behind, so we will reserve the questions to the poster session. So next, we will have a remote speaker of the paper, reweight OOD, loss reweighting for distance-based OOD detection.
Hello, can you hear me?
Yes, we can hear you. Could you please share the screen? Yes, please go ahead.
Hello everyone, I'm Sudarshan Regmi. So today I'll be presenting 2 presentations. The first one is reweight OOD, loss reweighting for distance-based OOD detection. This is a joint collaboration with Vivek Pante, Ife Ming, Prasanna Gyali, Daniel Stoyanov, and Binal Bhatrai. So out-of-distribution detection refers to detecting the samples from the out-of-distribution. Out-of-distribution detection is critical for the safe deployment of the deep learning models in the safety-critical application. For example, the out-of-distribution datasets for CIFAR-10 datasets can be CIFAR-100 datasets and MNIST datasets. So there are broadly 2 types of OOD detection approaches. One is a post-hoc method, and another is training time regularization. In the post-hoc approach, the OOD likelihood scores are directly derived from the pre-trained models, while in the training regularization method, first the model is regularized to enhance the ID-OOD separability, and then the post-hoc methods are used to derive the OOD likelihood scores. So reweight OOD is one of the training time regularization method. So it introduces a simple modification to the contrastive loss. So it has the dual objective The first objective is to maximize the dispersion between the empirical class centroids, and the second objective is to minimize the minimum enclosing sphere for each class. And both these objectives are imposed in order to have the less overlap between the in distribution and out of distribution samples. So ReOIT OOD introduces a ReOIT mechanism in the loss function to achieve the higher ID-OOD separability. So in the unweighted optimization, we can see in the left figure, the unweighted optimization can induce the lower average compactness. However, because of the hard samples, the OOD samples can potentially intersect with the hard in distribution samples, which compromises the OOD detection. So in the ReOIT optimization, even though the minimum mean compactness is not achieved, the minimum enclosing sphere is achieved of a smaller radius in comparison to the unweighted optimization, which potentially reduces the ID-OOD overlap. So ReOIT OOD contrastive optimization focuses on a poorly optimized pairs to achieve significant reduction of impossible ID-OOD overlap. So we have two components to achieve to ReOIT the each contrasting pairs. First of all, we linearly transform the cosine similarity and then we apply the similarity weighting function. For the positive pairs, we use the reverse sigmoid function, which has a monotonic nature like that of a sigmoid function. And so after this linear transformation, we apply the sigmoid function to get the weight for the optimizing pairs. So the UMAP visualization of cross entropy loss and ReOIT OOD loss can be seen in this slide. So it shows that the feature space obtained through the ReOIT OOD objective is highly separable, thereby reducing the chance of in distribution and out of distribution overlap in the feature space. And to obtain the OOD likelihood, we can use various post processors like KNN, MDS, etc. The quantification of the embedding quality for OOD detection can be done in terms of MES and centroid dispersion, CD. So from this table, we can see that ReOIT OOD achieves the lower MES in comparison to the cross entropy, supervised contrastive, and CIDR objective function. At the same time, it achieves the comparable centroid dispersion to that of CIDR. So this both the embedding quantification are near optimal in ReOIT OOD in comparison to the baselines. So it helps in OOD detection. So we can see that the OOD detection results on C500 datasets that ReOIT OOD is highly performant in comparison to the current approaches. And here are some of the highlights of ReOIT OOD in the OpenOOD V1.5 benchmark. OpenOOD benchmark is a widely used benchmark in which there are numerous methods which are benchmarked. Specifically, ReOIT OOD achieves the state-of-the-art performance in this PAR OOD AUR symmetric on C500 datasets. So there's the live public leaderboard in this given link. So in summary, ReOIT OOD achieves the higher ID-OOD separability. It enhances the OOD detection performance. So the implementation is available in this given link. So this concludes my first presentation, and my second presentation is T2F now, train time feature normalization for OOD detection in image classification. Like we discussed previously, out of distribution is the task of detecting the samples from the out of distribution. And so traditionally trained neural network, which are trained with cost entropy loss, are notorious for having the high softmax probabilities for both in distribution and out of distribution samples. And this situation makes it very difficult to detect the OD on the basis of the confidence score. Now, previously, we saw the distance-based OD detection, whereas in the confidence-based OD detection, there should be a clear separability in terms of the confidence. So this TTF norm is also one of the example of training time regularization method, and both the post-hoc methods and training time regularization methods, they to derive the OD likelihood scores, they use a function of either confidence score or the feature space or the combination of both of them. So in TTF norm, we propose a simple modification to the baseline. So we propose normalizing the feature space during the training and inference phase. After the normalization, we propose to scale the features with the temperature parameter. While during the OD scoring, we propose to avoid this normalization and only scale the features. This simple modification yields a surprising enhancement in the OD detection capability. So we can see the separability ratio in the left figure. The separability ratio is formally defined as the ratio of ID norm and OD norm. So we can see that is with the training progression, the separability ratio in terms of features of the TTF norm is much higher than the baselines. And in the right figure, we can see that the overconfidence of the TTF norm is the overconfidence is reduced by the TTF norm regularization. So if we do not avoid the normalization at the OD inference stage, it activates the features for the OD samples, which is not ideal because it causes the OD samples to mimic the behavior of ID samples in the feature space. But the removal of normalization helps to preserve the difference in the response of the network towards OD and ID samples. Hence, we avoid the normalization at the OD inference stage. So we can see the implication of TTF norm in terms of FC layer visualization. Recent works have shown that the non-trivial dependence on the unimportant features leads to the suboptimal OD detection performance. TTF norm is shown in the left has a distinct assignment of the important features in comparison to the FC layer visualization. It's of FC layer visualization of the model induced by the logic norm. Hence, TTF norm performs better than logic norm. So we can see the sensitivity history of the temperature in this slide, and from this slide, from the FPR metric, we can see that the scaling hyperparameter is also important to achieve the good OD detection performance. And we can also see that OD detection results in this slide. We can see that TTF norm is highly compatible to various post processors. So again, it demonstrates a superiority over the baselines. So the highlights of TTF norm in OpenOD benchmark is that the major highlight is that it ranks fourth in the FAR OD evaluation metric on the CIFAR 10 datasets, and yeah, the live public leaderboard link is given below. In summary, TTF norm achieves a higher ID/OD norm ratio in comparison to the prior works. It is very simple to implement, and it selectively applies the scale and to normalization to mitigate overconfidence. The implementation is available in the given link. Thank you. That concludes my presentation.
Okay, thank you for your presentation for the two papers. Due to the limitation of the time, so if anyone has a question, please directly contact the speaker. Right. So next we have the paper presentation of our deep CNN matches have developed achromatopsia. Go ahead. Oh, you want the project? Okay.
Do you want my microphone on or off? Off.
Off. Yeah. Yep. Go ahead.
Very good. Good afternoon. Are you awake? I hope so. So I changed the title so I wouldn't have to explain achromatopsia, which basically means you don't see color. I'm Kevin Boyer. That's not one of my pictures. This is actually Aman Bhatta's lead author paper, and the other people and the other authors, Mike King here from Florida Institute of Technology, Domingo Mary from University of Chile, Joyce Ammon from Florida Institute of Technology, also, and Hayu Wu from Notre Dame. Just so you have some idea who the people are. This is part of a long-term project that Mike King and I have been doing on demographic accuracy differences in face recognition. Why do different groups of people have different accuracy in face recognition? This is all going to be about color and grayscale. All face recognition, since some of you were born, has been done only in color. You don't even think about it. Everything's RGB. All images are color. When was the last time anybody here posted a grayscale image to a social media site? You've never done it, right? There are a bunch of grayscale images online. They're usually stored in RGB format, but they've been converted to grayscale. So you can take the R and the G and the B, you can get them, add them and divide them by 3, or use a better equation. You can get the grayscale value for every pixel. You can have 3 planes of the same value. You can load it into an RGB color format, and you will see grayscale. Of course, that's kind of a waste of 2/3 of the storage, at least in memory. And so you could have just the single channel grayscale. And I'm going to move from color to 3-channel grayscale to single channel grayscale in different parts of this talk. And I'm probably also giving you a quiz. The question we're posing is, does matching color face images give you anything over matching grayscale equivalents of the same images? In other words, I have the color RGB, I turn them into grayscale. Do I get anything from the RGB that I can't get from the grayscale? So I'm going to describe an experiment to you. I'm going to ask you what the result is going to be, and then I'm just going to show you what the result is. You ready? So I'm going to take ArcFace, a ResNet 100 backbone, trained on Glint 360K, which is a reasonably good size data set for today, not the largest. Almost all the images in Glint 360K are in fact in RGB format and do contain color content. That is, the pixel values are not the same across R, G, and B. I'm going to take that matcher and I'm going to run it on the Morph data set, which is a set of booking photos out of the state of North Carolina created by Carl Wixnick, both in the original color versions and in the grayscale created versions that we've done, right? So I'm going to have, for every pair of images, 2 different similarity scores. One similarity score computed between color images and one similarity score computed between grayscale images. If the similarity scores were identical, whether it was color or grayscale, then the point for every pair of images in Morph would all lie on this 45-degree line, right? That makes sense? If RGB gave me higher similarity than grayscale, then I'd be further out on this axis than I am on this axis. It would be something laying down here, okay? That can in fact happen, and here's an example image pair out of Morph, where you get higher similarity for the color than you do for the grayscale. So that's possible. On the other hand, if for some reason the grayscale similarity value was higher than the color, then we get a higher value here, and things would be in sort of that upper left area of the image. And I'm going to tell you that that can in fact happen also. This is a different pair that's got a higher similarity in grayscale than it does in color. Okay. I'll also tell you that the imposter pairs are in the lower part of this, and the genuine pairs, two pairs of images of the same person, tend to be up here. You might think that it'll do one thing for genuine pairs and something different for imposter pairs. You might think color is better. You might think grayscale is better. So take about 5 seconds. Take a $100 bill out of your wallet and write on it what your bet is. What do you think?
I have one.
I think the color one. August, distinguished researcher, what do you think? I think the color one. Really? Will it make a difference if it's male or female or black or white? The person?
As long as they're different.
Okay, well, so this is what we actually get from that experiment. This is the Caucasian female subset of morph, African American female subset of morph, Caucasian male subset of morph, African American male subset of morph. And this is the 45-degree line for each of them. This is a set of imposter pairs, and this color is the genuine pairs. Right? So it's not a really perfectly tight cluster around the 45-degree line. But especially for the imposter distributions, it does seem like the 45-degree line runs through the middle of it. You could maybe, if you stare at some of these just right, think that there's a little bit of shading down for the color, but hard to imagine that you're buying a lot from having used color if this is what you see in that sort of plot. So one of the main results in the paper, which I'm not going through everything in, I'm just sort of giving you a motivation for the paper. One of the main results is that we are going to claim, based on that last slide, the results of that experiment, a matcher trained on color images struggles mightily to get anything better out of color than it gets if you give it grayscale input. Get that? Matches we train seeing nothing but color struggles to get anything extra out of the color version of a pair versus the grayscale version of a pair. So here's another experiment. We're going to take 3 different depths of backbone, and we're going to train on different versions of images, and we're going to test on the standard color test data sets that people know. So we're going to train on color and test on color. We're going to train on one channel grayscale of the same color images and test on the one channel grayscale of the same color. This previous slide was the 3-channel version. So to do this, we actually have to go in and change the first layer of the deep neural network where it's taking in red, green, blue. So it takes in only one plane. There is no red, green, and blue, it's just gray. So instead of having 27 weights at every one of 67 filters, it's got 9 weights at every one of 64 filters. And then we're going to say, well, wait a minute. When I do this compared to doing this, I'm actually using less storage. It's a different kind of less storage on disk than it is in memory. In memory, it's really like 1/3, but on disk, it's not because you've got file headers and stuff like that. We're going to then increase the amount of gray so that we're using the same amount of file storage that the color would have used. So this is a bigger version of this with images that this one didn't get to see. Does that make sense? And this is a terrible slide, I know. It's got way too much data on it. So all the students out there don't ever do anything like this. ResNet 18, ResNet 50, ResNet 101. And these are the different test sets that you're probably used to seeing. And this, for ArcFace, is the result saying that when you start off with ResNet 18, a shallow network, it looks like working in color is beating working in gray most of the time. You go to a mid-range, that's neural network. I don't know that 1850 and 100 deserve those labels, but okay. And now all of a sudden, wait a minute. The gray is sometimes beating the color. And you go to the 100 and the gray is sometimes beating the color. That is, right, on the same data. But if I use as much gray as I would have storage space for the color, then I'm over here, right? Color is winning, and then it's losing, and then it's losing. So if I'm willing to do a same storage space on this comparison for my training data size, I can actually get a more accurate matcher working entirely in gray. All the images are one plane, there's no RGB, there's just gray, training and testing. That just says what I said, didn't it? Okay. Yeah, color seems to have some advantage when the network is shallow. It seems to lose it when the network gets deeper. And when you take advantage, are you going to tell me when I hit 10 minutes? You look like you were about to just, okay. Yeah, so if you go into the details of the paper, you're going to see some figures like this. This is an attempt to explain what we've seen in the structure of the deep neural network. So there's 64 filters in the first layer of the trained network. There's a set of weights for red, a set of weights for green, a set of weights for blue. And this is showing the variation across red, green, and blue. So all the black ones in the first one are doing nothing, or they're gray. The only ones that are substantially different are something like this across red, green, and blue, which will got the spot detector in red or something like that, right? So these are the primitive filters. There's just nothing color focused there. And if you go through the later part of the paper, you're going to see something like this, where we pick out 4 people that by colloquial description would have widely agreed different skin tone. And they have 50 images each or more in the Glent 360. And we say, okay, if color is really important, then these people ought to represent separated clusters in color space, right? But I'm not going to tell you what the answer is. You have to go to the paper to find out. Okay.
Thank you so much for your talk.
You're welcome. I assume there's no questions. Is that right?
The question will be reserved to the poster session. So come to the poster session to ask questions. So next we have the paper presentation for test time assessment of a model's performance on unseen domains by optimal transport. Yeah, it's good to unmute. Mute. Yeah. Should be good. Yeah. Go ahead.
Hi everyone, I'm Yunbei Zhang from Tulane University, and I'm going to present our work on assessing the model's performance and test time. This is a joint work with Akshay Mehta and Jigong Han from Tulane University. I'll start with our motivation. So consider you have a private data set without any labels, and there is multiple pre-trained models available on public. So which one should you use for your own data set? Well, if you have labels, then you can just select two. You can just use the one give you the highest accuracy. But in real world, the labels usually that's not available. So what can we do? A simple method is that you can choose the one with the highest in distribution accuracy. However, this won't work well because existing works have shown that the performance of machine learning models usually degrade on data from unseen domains. such as the common natural corruptions and style changes. Therefore, matrix that can gauge the performance of machine learning models and test time is essential. So suppose you have such a matrix, what can you do? In practice, this matrix can be used for various applications, such as the model selection that I mentioned before, and the source selection. So you have the model architecture is fixed, but you have different source data sets, which one you should train your model on. And the third one is estimating the accuracy on different unseen domains. So I'll start by giving a short introduction to optimal transport. So for example, you want to move bread from M bakeries to N cafes. Well, the cost for moving I's bakery to the J's cafe is Cij, and the amount of bread to be moved is Pi-ij. Optimal transport is trying to minimize the total cost of moving all the bread from the bakeries to the cafes. And the same analogy generally holds for any two distributions. So the optimal, in short, the optimal transport is trying to evaluate the distance between two distributions. And the cost function, you can use different cost function to define optimal transport distance. And this is the key part of our method. So in this study, we define the transferability of a model trained on the source domain as the accuracy of the target data. So the transferability cannot be directly computed because you don't have the target label. And we use the base distance or the cost function C here, is defined as the composition of the feature cost and the label cost. I'll mention this detail later. So based on all of this, we define our method T-tot as the optimal transport distance between the source distribution and the target distribution. So here is the algorithms to compute the T-tot. The input is the labeled samples from the source data and the unlabeled samples from target data. And the feature cost is defined as the L2 norm of the difference between the source and target embeddings. In terms of the cost, label cost, since the target label is not available, so we are using the pseudo label predicted by the source model, and use the L2 norm between the true source label and the pseudo target label at the label cost. And in order to so our experimental setup is we consider the three tasks mentioned before and demonstrate our method on two benchmark data sets, PAX and VLCS. Since there's no existing method, so we are comparing it with the entropy, which is commonly used at test time, like the test time adaptation. So we evaluate these two methods by the correlation between the transferability and the matrix. So a higher correlation means a better matrix. So for the first task, the model selection, given a target task, we want to identify the best model architecture to use. So we are considering like 8 different models here. They are pre-trained on single source or multiple source. And the first row is our method. The correlation of our method is it outperforms the second row, which is the entropy-based method. Moreover, the table in the right is the average correlation across different target tasks, which you can see that the correlation is much better than the entropy-based matrix. Just note that this is a negative correlation. So the higher correlation means a higher negative correlation. And for the second task is a source selection task. So in this setting, we fix the model backbone as less than 15, and we consider different source. And still we're computing the correlations to compare the correlations between these two different methods. As you can see, our average correlation is almost double, twice at the entropy. And for the third task is to estimate the transferability of unseen domains. This is you have a fixed model trained on a pre-selected source task, and at the same time you have different unseen different data from multiple unseen domains, but without labels. So you want to compare, you want to estimate the transferability of all of this, and still we are computing the correlations between the accuracy and the metric. Still, our method consistently outperforms entropy-based method. And lastly, we evaluate. We show that our method can be computed with only a handful of source data. And we know that requiring the source data sometimes can be restrictive. So we have an approximate version of our method that can only require the statistics from two domains. For example, the mean and the covariance. And the correlation is still high. To conclude, we propose a method to assess the transferability of machine learning models and test type without any labels using the optimal transport. And we demonstrate it on 3 different tasks. For more details, please stop by our posters. Thank you.
Let me introduce our next keynote speaker, Dr. Yuchuan Xu, who is a Google research scientist, and he got his PhD degree in computer science from UT Austin. He received also Best Paper Awards at ACCB 2016 and Best Thesis Award in IPPR 2015. So he has been working in a variety of image and video related problems in computer vision. And today he's going to talk to us about content creation beyond text to pixel. Please, John.
Should present to the room or right, you thoroughly share your screen on Zoom. Yeah. Okay. Yeah. Okay. Or do you want me to? You cannot see the screen.
Should be.
Is that okay?
Yeah.
Okay. Can you share on Zoom?
Oh, yeah.
Or you want me to project on the screen? Okay. Yeah, Zoom is also looking great. Yeah, please start.
Yeah, okay. Thank you everyone for joining the talk. So as the introductions, I'll talk about our work on how to extend existing text to image generation model for more capability. Yeah, so I think like most people will agree that text to image generation is one of the greatest achievement in or of the computer vision community over the past few years. In just a few years, it goes from like a cool demo or even not so cool technical demo to a practical tool which impact or like transform how people create content or express their creativity. Like as a researcher working on this domain, I'm always surprised by what people can achieve using this model. They're using this in a wide range of applications in their everyday workflow in a way that as a developer, I never imagined it can be done when we're developing this model. Despite their great success, we can clearly see there are still limitations in this model. And there are definitely many different aspects that can be or have to be improved in this model. But in practice, I think like there are one important aspect that are missing in this model, which limit their in wide range of scenario, which is the ability to control or like a stronger provide stronger conditions. So here's an example, like a common pipeline or like workflow for people who want to create an image is that we'll try to iterate on the image and gradually edit the image to achieve the result we want to achieve. Now, like this process nowadays can be approximated in base text to image generation model in some approximate way. So here's the example. You can probably see that like here adding a sun is the instruction I'm adding to this text to image generation model. And you can see the model is more or less doing that. But in most cases, this is probably not what will as a content creator will be expected. We'll be expecting something more local and like and the rest of the image should follow the original image even better. And this is just an example, but the general idea is that this text to image generation model are usually just designed for a one-shot generation. While like in practical application, we always want to something we can iterate and provide stronger condition, control what we want to in the output. So in the following talk, I will talk about our effort on how to mend this gap between like the common content creation pipeline and this text to image generation model. Specifically, I will start with how we extend this text to image generation model for personalized image generation. And then like I'll extend it to, and then I'll introduce how we extend it to something more generic where we can extend the model to take arbitrary like condition and to better control the text, the generated output. Yeah, so let me start with how to extend this model of text to image generation model to personalized image generation. And I'll start with a little bit of a motivation why we step into this area. So before we start working on text to image generation, we're working on blind face restoration for various Google products. It was a great success for like this blind face restoration model was a great success from the application point of view. It's now deployed in a wide range of Google products. But very quickly, we realized there's a clear limitation of this model, which we believe is not solvable if we're still sticking with this blind face restoration paradigm. And here's a great example we grabbed from the web that illustrates the problem. So here the left-hand side is the input image and the right-hand side is the model output. Now from the blind face restoration perspective, people probably will consider this image, this result as a pretty good result where the output image aligned with the input pretty well and there's no artifact and the aesthetic quality of the output is pretty good. But I believe I don't need to explain or like persuade you that the left-hand side image and the right-hand side image is obviously not the same person, as I believe most of us will identify the left-hand side image as the President Obama. So this clearly, I don't show the limitation of this blind face restoration model where it's well known it's an ill-posed problem and need to generate something that's not available in the input. And obviously, like when you start to generate something you don't have in the input, it inevitably like leads the model to hallucinate or generate something that's not as desired. And like a practical example we encounter where it's practically blocking the feature when we're developing it is this example. I don't know if like any of you can see what's the difference between the left-hand side and right-hand side. I have to tell you that that's not because of the projector or the screen. It's really a subtle difference. If you look close, take a closer look at the eye region, you can see the color of the eyes actually change a bit. So this is the kind of like the problem we're dealing with when we're trying to productionize this generation model, particularly when we're talking about like person generation. And to overcome this problem, we believe it's important to exploit external knowledge. That is basically knowledge beyond just the image we want to generate. So that's a little bit background leads us into this field of personalized image generation. But instead of studying it into in the like face restoration field, we're studying it in the text to image generation domain. So like as people know nowadays, like text to image generation are very good at generating general concept. Like it can now generate very good like image that align very well in the instruction you're provided. However, it's also well known that these text to image generation model are not that good at generating a specific concept. So for example, what if I want, instead of generating arbitrary dog standing in the garden, I want to generate like a picture of my dog standing in the garden. One way you can do is like because like this model are very good at in their text alignment nowadays, you can provide a very detailed description about what the content should look like. But this is obviously not very efficient, and even if you and also like this model nowadays still have a limitation about how much input it can take. Basically, like the length of the input, and even if you can fit like a very or infinite long text description, it's still hard to ensure that the model can follow every bit of detail. So this leads to a very well-known work or a stream of work of like a subject-driven generation or like or most well-known work as a dream book, where the idea is trying to fine-tune the model to a specific concept you want to generate. So for example, you will given a general text to image generation model, you will fine-tune it to a specific dog, for example, and then you will use it to generate new image of that specific dog. So it has been a great success, like of line of work, but there are still some obvious limitations of this work. First of all, it's still like need one model per subject, which means that the cost, especially the story cost, will grow linearly with the number of specialized concepts you want to generate. Also, like no matter how fast we accelerate this model, it still needs some kind of online fine-tuning, which make it not applicable for real-time application. Finally, like a practical issue of this model is that although like they're able to fine-tune the model with just a few images, in practice, if you're just using one image or like a few images with very little variation in their appearance, you'll find that this model always or almost fail to generate diverse generate variation of the subject in most cases. So in light of all this limitation, we propose our problem of like a personalized image generation or like in context personalization, where our requirement for the model is as follows. So first of all, we want the model to be able to take a few example of the subject as input example of the model. And we want the model to like we want to avoid any like inference time fine tuning. Basically, we want the model to just take this as we call it input context following the like language model, and just using a single forward path to generate the output. And finally, last discussed point we want to achieve is that we want the model to be able to generate diverse output that covers a wide range of variation of the subject, even using just a single example of the subject. So the approach is actually pretty simple. We just take an existing like generation model based on diffusion model. We then augment the original model with a kind of additional encoder, which can encode subject like the image of the subject into in this case, into an embedding feature and condition the generation process using this embedding feature. And like, so that's the overall framework. And like, given a data set consists of a group of image of a subject, we can simply just take several images of the subject as training example and the other as an output example, and then train the model end to end. So basically, like given this group data, the rest of the model is trivial. Except we make some like a modification on the training loss and model design to encourage the model to generate diverse output. First of all, is that we encourage the model to learn a set-to-set mapping into a point-to-point mapping. The idea is that like every point in the embedding space should be so basically like, because we're casting the example image of the subject into embedding space, our hypothesis is that like every point within the convex hull of the embedding of the example of the subject should be a valid representation of the subject. We want that and we want to encourage the model to learn this to learn this mapping. And also we impose a soft nearest neighbor loss on the embedding feature in the middle to encourage the model to separate different subjects in the embedding space. So with this modification, like we're able to train the model end to end given and being able to generate diverse output. Now, one thing is that due to the policy reason, I am not able to conduct a very systematic study or like show you some kind of like a formal evaluation of the model, which I'll touch a little bit later. But fortunately, I can just show you some like a visual result of what the model can achieve. So here, like the first like here, like I'm showing like given the same set of input, we're able to generate different appearance of the subject or in different style. So I think I probably don't need to tell you or persuade you who I'm trying to generate here, but like you can see that like given in practice we're just conditioned on free image of the subject and then like trying to generate it in different style. And you can see the model actually align pretty or being able to generate like the same subject in various style pretty well. And you might argue that okay, you are generating image of celebrity, which your model probably have already seen. So we also try to generate the image of like some less well-known subject. So in this case, we're just asking our colleague to donate their photo, and we're trying to see if we can stylize them. And you can see like even if these subjects are not or like rarely seen in the original training data of the model is still being able to generate pretty well. It still can generate image of the subject pretty well and preserve the most of the apparent feature of the subject. So usually I'll stop here and go on, but like in this case, I want to talk a little bit about like what I mean when I said like the policy doesn't allow us to do the evaluation, and specifically like what we're doing to avoid this like abuse of this model. So there are obviously like a lot of different steps to take, but in generalizing, we can categorize our approach into two categories. The first one is from the data and the data processing side. Oh, and by the way, I'm not allowed to put those into slides, so it's purely verbal, but hopefully you can get a sense. But the first one is the data and data processing side. So from the data side, like we're only allowed to use licensed data. So unlike some people might imagine, we're having access like to a lot of different applications in our company, and we're able to use that to do our research or even train our production model. In practice, it's very rare that we can get access to those data. There are like very strict restrictions on what we can access. So in most cases, what we're using is just some data that are explicitly licensed for this to train this image generation model. And in most cases, those are data purchased from like some external company that are dedicated for this kind of application. And also like the usage, obviously like every usage has to be reviewed and approved. And this approval is per use case basis. So basically like it's not like we purchase a bunch of data and then we can use it in our scene. It's usually like for every use case, say if we're trying to train a model that can generate faces, that has to be a specific approval for the data. So that's the kind of like a process we're going through. The only exception is that synthetic data. So I think so far, like the restriction of using synthetic data is like less strict. So as you'll see later, we're heavily relying on synthetic data to train our model. Another thing like about data processing is we're not allowed to, we're calling it biometric processing on the data. So, but basically like idea is that we're not allowed to extract any information that is specific to a person unless it is explicitly allowed or consent by the person. So this means that we're not able to use any kind of like face recognition model on this face image, which is the reason why I'm saying that I cannot do the evaluation, as like obviously people will want to say, okay, how will your generated face align with the original subject, which we're not allowed to do the evaluation. But yeah, so that's why I'm only able to show you the visual example here. So that's on the data and data processing side. Another thing is on the like a product design side, where so because like that part is purely avoiding us like the model builder to abuse our data or abuse our model. But the other side is other aspect of the problem is how to avoid our user or the user of this model to abuse this model. So at this moment, it's mostly relying on how we design the product. So actually, in most cases, what you will see is that this generated image is obviously generated. So basically, like in most of the product, you will see that it's only being able to, it's only allowed to generate something that's like say cartoonish or something you can obviously see that's not a real photo. Despite that, the fact that these models are, most of these models are trained on photorealistic image, and they are able to generate photorealistic image. So yeah, so these are the two main kind of like approach we're taking to protect this the abuse of this model. So back to the talk itself, like a short summary of this part is that we're showing that we are able to augment existing text-to-image generation model with some additional context encoder to achieve like fine-tuning free personalized image generation. But of course, like although personalized or subject-driven image generation is one of the most asked application in text-to-image generation, there are other applications people want to achieve using this model and require this additional like input information. For example, like people might want to control the output with using some structure control. People might want to do image editing, which means that your generation model needs to condition on another image, which is the image you want to generate. So the next part I'm going to introduce is how we extend this like context encoder idea into something that's more general that can take arbitrary condition for a wide range of tasks. So here's a visual illustration about what we want to achieve. So for example, we might want to combine like a several subject example and say hand drawing scratch to generate an image of the subject following like what we're drawing. Or we might want to even combine with an image that example that show what the style of the output image should be looking like. And the list can go on, for example, like editing. So you can imagine, like these are the type of thing we want to achieve. And for people who have been like working on this field or like following works on this field, probably can quickly identify or quickly imagine what or think of approach that are dedicated for this task. For example, you can clearly see like for the edge or the subject-driven generation is what I just introduced, but for the like a structure control-based generation, you can quickly think of things like control net. And for style-driven generation, there are things like style drop or all the style transfer works like in the literature. But one problem of this existing approach is that there are dedicated model or even dedicated approach for each application or each task. But that means that but in practice, very often what we want to do is the combination of this task, and there's no, in many cases, there's no natural way to combine this different approach. And even if there is, it means that you need a very complicated pipeline to combine all these different tasks to achieve your goal. So what we're trying to achieve is we're trying to have a single model following the same like context encoder idea to solve or accommodate all these different tasks. So again, the first step is how do we prepare the data? And as I mentioned, like we're heavily relying on synthetic data as it's usually easier to get some generic data being approved for arbitrary tracing and doing some like less sensitive processing to get the other modality or the other signal you want for the training for the task. So here, except the source image we're trying to generate, most of the input image we're obtaining them from like other model or other approach. And with this like a different approach, we carefully curated the data as an output. So basically like we're preparing data for each task, and for each task we're using different model to prepare the data with proper filtering of the data to ensure that all the input data are of high quality. And most importantly, what we're doing here is that we're providing the text description or text prompt associated with all the data, such that like the model can learn to how to utilize this like input output and how to connect the input and different input following by following the instruction in the text prompt, which I think will be more obvious in the following example. So here's how we prepare the like multitask data for our model. And a little bit about the approach. Again, we're trying to, as I mentioned before, we're trying to have a unified model for all different type of tasks that basically follow the structure that like you want to generate a 2D image following text prompt plus other signal that can be formulated in the form of 2D image. So what we're doing here is pretty simple. We just take an existing text-to-image generation model. We kind of like reuse the encoder in the text-to-image generation model as the encoder for the contact information we want to condition on, and then we insert some additional layer in the original model to take this contact information as condition. And then what we're doing is just again train this model end to end, except in this time because the contact can present different information. So we're augment them with the text description about what information is representing, and use the text description as a referral expression in the target prompt referring to what we want to generate. And again, then everything is just end-to-end training. So I think I don't need to persuade you like whether the model performed well on the task that we're training the model on. What's really interesting thing here is that we see the model actually after training on different tasks were provided, the model actually performed pretty well on generalizing to a new task where it's not trained from. Previously, remember, like all the tasks we're training on are kind of like a single task, like a control to image generation, subject to image generation, style to image generation, so on. But in practice, like after training it on all these different tasks, we find that the model can be easily applied to combine all these different tasks, just similar to what we see in the language model, where after massive pre-training, the model can easily pick up new tasks and generalize to unseen tasks. And here we're starting to see this capability in the image generation model. So after seeing this initial success, what we're doing next is we're trying to further scale up the model, not in terms of the model size or the data size, but in terms of the task. So we're trying to add more tasks to the model, including object detection, image editing, and so on. And also we're trying to improve the quality of the data to further improve the final output. And okay. So here, where am I? Yeah, so like what we're doing is trying to increase the number of tasks during training time and hoping the model will achieve even better generalizability. And also like we're adding some auxiliary tasks like object detection, trying to in the hope that we try to teach the model to better understand what a text description or text prompt mean. One thing I want to emphasize here is that as I mentioned, like here, our primary goal is to increase the number of tasks rather than the number of data. So in practice, for each task, we're using the size of the data varies a lot, but in most cases, it's around just 20,000 image or 20,000 example pairs in each task. But we're doing a lot of filtering to make sure the quality of the data is high. And here by quality, it's not just the aesthetic quality of the image, but also how well the output align with the input, and also how diverse the input represent, or how diverse the content the data set cover. And here, the following, I'm going to show more the result of the model after we extend this data. So here's the first thing is the subject-driven generation, where you can see the model actually achieve an amazing kind of alignment between the input and output. So here again, the left-hand side are the free image we provide as an input for the model, and the bottom is the text description we're asking the model to generate, and the right-hand side is the model output. So you can see like the very same model are able to generate, like first of all, the alignment with the input example is actually very well, where I think most people will agree that like the output looks just like the input on the left-hand side. But more impressively is that the model actually do very well on the text alignment, despite that like there are limitations in the variation in the input. So you can see we can change the pose of the subject, change the material of the subject, or even change the context of the subject, while still like the general like the output quality is still remain very well, and we can see that there's like in this case we rarely see in this subject-driven task we rarely see like any artifact in the output. And disclaimer, like indeed we do spend some time to pick some more impressive result from the model output, but here we didn't really do a heavy cherry pick on the output, where the success rate of the model is actually pretty high. In practice, what we're doing is we're always generating four image of the same input, and we in almost all cases we find at least one example which match this quality. So what we're picking is mainly about the aesthetic, or like how impressive the content will look like in the presentation, rather than like picking a successful example, which I believe for people who've been working in this field realize what I'm talking about. The second example, like a second group example I'm trying to show, I want to show is the style-driven generation. So again, the left-hand side is the input, like basically what's the style we want the model to generate, and the right-hand side is the output, following and the bottom is the text prompt. So you can see that the model really understands what we mean when we're saying that, okay, this is a style example rather than subject example. In other words, we often find that the model has trouble disentangle the concept of style and subject, but with this additional task, combination of tasks, the model are starting to be able to disentangle this different concept. And again, and I want to emphasize this, all these examples are generated from a very same model, and the way the model distinguish different output are from the text description associated with the input. And we're also, as I mentioned, like image editing is one of the very common tasks people want to achieve in like image and content creation. So we're also applying this model to image editing. So here we're showing the example of mask-free editing, where again, left-hand side is the input, right-hand side is the output, and the bottom is the text description. So you can see the model can do some like a very local change on the subject, like inserting a dog, changing the color of a object or in the image, or even changing a text on some of the subject in the image. And with this model, we're able to achieve some more fancy tasks like iterative image editing. So like here are two examples where we're doing like a combination of mask-free and mask-based editing, and other capability like style-driven generation. And finally, we're showing other additional capability of the model. So not surprisingly, the models can still do things like structure or control to image generation, similar to ControlNet. And it's also, and remember, I mentioned like we're adding tasks like object detection into the model. And you can see indeed like our model are able to perform object detection. Remember, note that here, like the right-hand side is just the 2D image input of the model, following the instruction in the below. So we're not doing any specific design for object detection or segmentation. It's just RGB generation. And you can see the model actually do very well on this type of understanding task. And like it can, for example, on the bottom right, you can see it accurately place the bounding box around the car. Although in the model, we don't really teach or we don't explicitly or like design the model to draw a bounding box. It's purely from like learning how to generate an RGB pixel of the entire 2D image. And here are some more traditional paths like image colorization or even image restoration. Remember, like I mentioned, like we all start all this line of work because we're working on blind face restoration. And you can see that like without like a specific fine tuning for this task, nowadays model with proper multitask learning is able to handle this this task which previously was handled by task specific model. So a summary about like our multi-model instruction work. Like we were extending text to image model to accept like we call multi-model instruction, or in this particular case, it's a instruction in a form in the text description and any conditional signal that can convert into like 2D image signal. And we can see like by combining multiple tasks into a same model, we can see new capabilities start to emerging from this model, similar to what we observe in large language model. Yeah. And so a quick conclusion of my talk. So as I mentioned in the beginning, we find that text to image generation model is a very powerful tool, but it's often fall short on some scenario, especially in some practical application where people want to apply it in like a common kind of a pipeline for content creation. But we find that we can easily augment this existing model with some additional context
benchmark and learning from noisy input. So this work is jointly from University of Illinois Urbana-Champaign, Irvine University, and University of Tokyo. So this is a problem I have been working on human pose estimation in 3D or 3D human pose estimation. For the monocular RGB videos, it is a very challenging task. And especially in this case, we are focusing on the 2D to 3D pose slitter. That's basically it operates on a sequence of 2D pose detected from off-the-shelf 2D key points detectors. And from the 2D key points, we have a much derived from the human 3.6M dataset. And in order to do this, we're trying to corrupt this original dataset with some kind of operators. For example, we randomly mask patches of the original videos. We can perform some cropping. We can add in some impulse noise or encode in some motion blur to bring this dataset collected in a very ideal condition with 3D motion captures data to something closer to videos that captures on the wide, or suppose the videos captures using your smartphone devices. So in the stream, you can see some example of our dataset. So in this case, we are studying the robustness of 2D to 3D pose slitters in two different scenarios. In the first scenarios, we suppose the models, we don't see the corruption. So the models basically will not be trained on this corrupted dataset. Only the original dataset is given. So in this case, how can you do to improve the performance? So that is our first scenario on unforeseen corruption. On our second scenario, we are looking at the scenario when your F theta or the 2D, 3D pose slitter know that there is some corruption in the dataset, and you can use this kind of dataset to train the model so it can be more robust in the inference stage. So we propose two baselines on top of these two scenarios. So let's assume in the first scenario, suppose you don't have any corrupted or don't have that noisy data. What can you do? So here we propose a data augmentation strategies. We call it temporal additive Gaussian noise. So the key idea of this approach is that you're trying to add in some jitter or try to train your data set on noisy 2D pose data, not the original one. And in order to do this, it is very simple. Instances when you training the 2D to 3D pose slitter. In the second scenarios, when suppose you have the data set is corrupted, you know that it is corrupted, and you have a data set with noisy 2D key points, what can you do? So in this case, we propose a new model architectures using a confidence-aware convolutional block. So remember at the scenes I showed you earlier, when you have a 2D key point detectors, it can output the location of some choice, but it can also give you the information on the confidence of that prediction. So we believe that the confidence score besides the location is very important. So previous work, they didn't take into account this confidence score from the 2D key point detectors. And that is why we are trying to incorporate this kind of confidence or some information you can know from the 2D pose estimator on the certainty that it can has on the specific 2D locations. And you incorporate this information during your model architecture's design, it can improve performance. So really our models have two main blocks. The first one will be the adding the post location, and the second one will be the confidence score corresponding to that location. So here we have some technical details. We are adding some linked list toys to accommodate the situation when you have sometimes you have the estimation you have on the 2D pose estimator sometimes have a very low error and also the low confidence score. So you don't want to be like, suppose you have the pose location with a very low confidence score. You don't want to throw them away completely. You want to keep a small portion of that, and these terms can help you to keep the information flows, to keep the information from the pose with low error and low confidence score. So this will be some qualitative results when we apply our method on a traditional VD-Pose 3D baseline. You can see that under some corruption, some occlusion, sometimes the subjects moving around in the below in the white, you can see some occlusion. For example, if you're looking at me standing right here, you cannot see the lower part of my body. So what happens if you can still see cover and improve the performance of the robustness?
Are you still?
So these are qualitative results when we compare our method versus the traditional baseline. So the plot here is showing the mean errors, lower is better compared to different corruption times we added to the original human 3.6M data set. And our baseline, you can see in the color lines, they are much better compared to the upper bound models. So we saw that a very simple trick during training is doing some data augmentation, adding some noises during the training process can actually help you to generalize well on the corruption you observe on the original RGB images. We have some and the new architectures using confidence awarded convolution, which is also take into account of the confidence score besides the post locations. So that is all I have, and there's some paper, and see you at our poster. Thank you so much.
And next on the schedule, we have the paper presentation of RNet robust linearized networks for efficient private inference. And you have to share the screen. Okay, answer you have it. Yeah, you probably need to duplicate this. Right now it's extension. Duplicate the display. Or do you want me to project that for you? Okay. Yeah, go ahead. Yeah, you can just present like this. Go ahead. What happened? Okay, do you have a local copy?
Okay, I think I do this. Someone laptop is.
Can you just present your local file?
Yeah, but I think.
That's fine. Do you need more time or we can switch to the next?
Okay, I will.
Oh, okay. Yep. Okay. So for the since we're running late, so if you need the coffee break, so please help yourself, but we will continue the schedule for this workshop. So next we have the paper presentation for the paper Robust and Explainable Fine-Grained Visual Classification with Transfer Learning, a Dual Carriageway Framework. Yes. Can you join Zoom?
I'm not sure, presenting for the second author.
Okay.
I'm not sure what the idea or anything.
Okay, can I try one more time?
Oh, okay.
Sure.
So, no, you don't have to worry about the, just, do you have the Zoom link?
No, I mean, so, because I think the main author's probably asleep now, so.
I'm receiving our website. Yep. Go to the virtual platform. Go down. So the virtual platform here. Yeah. Sorry, go to workshop. Control F trust. Sorry. Okay, it's our workshop. Yeah, good. You can click on the join Zoom. Yeah. Great, thank you. Is it working?
Yeah, but maybe you can connect it on this.
Okay.
Why once I like if I stop sharing, if I stop sharing, I can do this like slideshow.
Can you download to a local copy?
Yeah, I have a look.
Yeah, you just present a local file. But you have to share your entire screen right now. We didn't see it. But do you need more time? I mean, we can.
Continue to copy this.
Yes.
Okay, maybe I
Yeah.
Okay, in the meantime, maybe I'll just try out sharing, but yeah, we can continue.
Oh, okay.
Do you want to?
No, I'm going to continue with the next speaker,
Okay.
next presentation, because
Okay,
you
fine.
need more time.
Okay.
Yeah. Please. Sorry for the struggle.
So. Should I just share my screen?
Yeah, share screen on Zoom, and then you have HDMI.
Yeah.
Okay. There we go. Let's try that. You share the entire screen.
Okay.
Yeah, that's great. We can see it on Zoom.
Cool.
Yeah, we can see coffee break.
So, hi, my name's Joseph Smith. I'm presenting a place for Chunming Zora today because he couldn't be here due to visa issues. But I'm presenting the paper, Robust and Explainable Fine-Grained Visual Classification with Transfer Learning, the Dual Carriageway Framework. So classification is kind of a cornerstone of deep learning image and computer vision. But in the real world, data changes over time. Oh, sorry, in the real world, data changes over time, and a model that's trained on one data set may struggle in the future with a temporally consecutive data. So that kind of brings up a question that needs to be answered, which is that should you train a model on a mixture of the two, like the previous data set and the new data set, joined together, or should you start again and train on one model and then fine tune on another? So some of the major challenges overcame in the data that we're using on this is varying luminance, imbalance in the data, some noisy textures, and then also camera bias. So in this work, we aim to find a way to train a single model to leverage the performance of a model used on a testing set instead of one which performs well for only one of the testing sets and not so much for another set. And to this end, we propose a dual carriageway framework to achieve this optimization. Our framework contains two consecutive components, which is the padding scheme adapter, as you can see there in the sort of like orange to the far right, or left, sorry, and then also a training pathway selector. So the PSA is proposed to work out the appropriate way to pad images, which will then be used in the TPS. And the TPS is where we look at the accuracies of a fine-grained classification model on A tilde, which is the testing set of the first data set, and then build B tilde, which is the newer data. So we look at that and then maximize on leverage to find the optimal pathway to take. So to achieve this goal, the hyperparameters learn for the dual carriageway form. The model is trained on A hat and B hat in settings 1 and 4, as you can see on the slide. And then based on that, we can further fine-tune the model using either the newly released or pre-existing data sets in setting 2 or 5, depending on what the model was first trained on. We also cover the scenario where you just take both data sets, mash them together, and train a new model. So the data set in question that we're using was provided by our industrial partner, P&G. It's just the underside of shampoo bottles. Where both data sets contain a mixture of shampoo bottles made by different manufacturers. So that's F1 and F2. And you can see the sort of like distant differences between the two data sets, where the data set 2 contains like larger bottles and the printings are slightly different. And the region of interest that we use for the classification is this ACF code at the bottom there. When the classification is done, it's on like a segmented, cropped version, after using a model we trained. So we first evaluated the effectiveness of different padding schemes. So this was done by training a ResNet 34 model using the most commonly adapted zero padding 5 times over to make up for like randomness of different seeds and stuff. And then the model was then tested on 6 different methods of padding, which are zero padding, RGB mean, LAB mean, reflection, gray padding, and then white padding as well. From the results, you can see that reflection padding had the sort of most optimal across both the previous data set and the new data set. But to move towards sort of more explainable AI and not sort of just take a result go of it, we wanted to visualize the reflection padding and work out why it's outperforming the other methods. So you can see from the graphs the relationship between the mean pixel values of the image and the model's confidence classification for that image are really quite strong for the reflection padding. And you can see the reflection padding, has the most consistent mean pixel value regardless of the concept drift between the two data sets, A tilde and B tilde. As another effort towards explainability in fine-grained image classification, we explore the image-wise pixel frequency distribution and the corresponding attention maps that were generated from the model during inference. So the richer text is yielded by reflection padding greatly expanded the perspective range of the model. And based on these results, we continue using reflection padding for the training pathway selection section of the paper. So yeah, in that second part of the training pathway selection, we evaluated using the adopted reflection padding with each of the 5 training settings specified before in the framework slide. We can see that the training setting 2, which is training first on data set A, so the original data set, and then fine-tuning using the new data, achieve the optimal testing accuracy when used for both the testing set from the old data and the new data. But yeah, really performed like doing the reverse. Given that data set A, the original data is much larger than data set B, this suggests that it's better to train first on the larger data set and then fine-tune using that smaller data set rather than going the other way around. We also wanted to look at the explainability for this section that we did before. So we visualize the attention maps of the model trained on each of the 5 training sets. The benefits of selecting the second training pathway are twofold. First, it is compatible with learning meaningful features for both blurry and clean images. As you can kind of see there from the first row, the first row of images is much blurrier than the other images. The second one's a lot more sort of clean. And then second, it can also mitigate the inference noise caused by printed dents in the product, which can be seen in the last row of the figure, where I don't know how clear it is, but there's like a sort of bump in the plastic of the shampoo bottle. So to sum up, we propose an automatic, best suited training solution searching framework through 5 training settings, configured in a dual carriageway manner for robust, fine-grained visual classification, where the prediction performance on testing sets of 2 temporary consecutive data are maximized. Second, we proved the feasibility and applicability of the proposed framework through not only the prediction accuracy and the degree of confidence yielded by the 3 training CNN models, but also the quantitative and visual explanations in a pull-through manner from the actual model input to the layer-wise attention maps. Lastly, we showed that determining the most appropriate padding scheme is a reasonable starting point for deploying the proposed framework, where merely the CNN model trained before on the original data is all that's needed. So yeah, thank you for listening to my talk. Since I was the second author, it might be best to point most of your questions towards Jimmy. You should be available over email or have you contact him. But thank you.
Yep, thank you.
One shy.
Thank you. Share screen. Yep. Please.
Hello everyone. Sorry for the confusion. Sorry for the confusion earlier. So I am Sritama Sarkar, a second-year PhD student at the University of Southern California, and today I will be presenting our work, RLNet, Robust Linearized Networks for Efficient Private Inference. So privacy is a major concern in AI everywhere, which includes both data and model privacy. This has led to the growth of private inference frameworks, where the user encrypts the data, sends to the server, and then the server operates on encrypted user data and sends the model predictions back to the user. But although private inference preserves privacy for model and data, this comes with its own challenges, which is the high cost for communication and latency. A breakdown of the latency cost shows that most of this latency can be attributed to the presence of nonlinear units in models like ReLU in convolution in neural networks, and this has led to a lot of works which try to reduce ReLU for latency efficient private inference. However, the robustness of these latency efficient private inference techniques remain unexplored. So in this work, we present RLNets, a class of models that yield improvement by the reduction of high latency ReLU operations while improving the model performance on both clean outer distribution as well as adversarial images. As we can see in this graphs, state-of-the-art non-linearized techniques, although achieves good clean accuracy while reducing ReLU, they lack in terms of naturally perturbed accuracy as well as adversarial accuracy. And in this work, the class of models that we build, a class of shared mask, shared weight conditional models, we achieve an optimal trade-off between clean accuracy, naturally perturbed accuracy, and adversarial accuracy. And our models not only improves adversarial and natural perturbed accuracy by significant amounts, but also improves clean accuracy by almost 1.5% over standard training. So the techniques that we used for improving model robustness for linearized models, for out of distribution samples, we use the standard data augmentation technique, AugMix, which is where we generate augmented images using translation, rotation, shear, etc. And then we linearly combine them to generate augmented images. We also train on adversarially generated images by adversarial distillation, where the adversarial images are generated by maximizing the tail divergence loss between the student and the teacher output models. And we further use dual batch normalization. We know that batch normalization statistics for adversarial and clean images are significantly different, which is what primarily causes adversarial training to perform poorly on clean images. So we see that normal adversarial training causes significant accuracy degradation on clean images. However, if we separate the batch normalization statistics for clean and adversarial images, we see a significant improvement. So in this case, we build a conditional model where we have two separate paths through the model, lambda equal to 0 for clean and augmented images and lambda equal to 1 for adversarial images. And these two paths differ only in batch normalization layers. Now, do we need triple batch normalization? Like, do we need to also separate the batch normalization for clean and augmented images? So we observe that when we plot the batch normalization statistics for ResNet 18 on Tiny ImageNet, it shows two distinct clusters, which shows that the batch normalization statistics for clean and augmented images are pretty identical. And we further also do a triple batch normalization formulation and see that separating the batch normalization statistics for clean and augmented images do not yield any benefits over dual batch normalization. So we go ahead with dual batch normalization for our conditional models. Regarding our model architecture, we replace each CNN block with the conditional with two conditional paths, as I already explained. And then we replace the ReLU with a masked ReLU operation, where we append to each ReLU layer a ReLU mask, where ones indicate the presence of ReLU units, whereas zeros indicate the absence of ReLU units. And the way we assign this mask is that we compare the post-ReLU activation for all ReLU as well as partial ReLU models. And we observe that the absolute difference between the activation for this post-ReLU and absolute difference of activation in post-ReLU activation map for all ReLU and partial ReLU models, and where this absolute difference is maximum, we assign the ones. So our training framework primarily consists of 3 stages. As the first stage, we train an all ReLU model, which is an all ReLU teacher model, which is robust on all 3 fronts. In the second stage, we generate a ReLU mask, which achieves the target number of ReLU operations. And finally, we fine-tune the partial ReLU model, so to close the performance gap with the all ReLU model on all 3 fronts. These are the loss functions that we use for our training. For each loss function, like cross entropy loss, tail divergence loss, we have 3 components of the loss, where we have like each component of loss corresponding to clean, augmented as well as adversarial images. And we also use a post-ReLU activation mismatch loss, which is simply the L2 norm of the post-ReLU activation map between a partial ReLU and an all ReLU model. We use this post-ReLU activation mismatch loss only during fine-tuning to close the performance gap. And for stage 2 training, we use cross entropy and tail divergence loss. These are the evaluation matrix that we use. If we have clean accuracy for accuracy on clean images, adversarial accuracy for accuracy on adversarial images, and naturally perturbed accuracy, where we evaluate accuracy over 15 different corruptions, where accuracy on each corruption is again averaged on 5 different severity levels. We observe, so now coming to the experimental results, even for our all-weather teacher, we observed that our conditional training achieves better performance than 3 separate models trained using standard training, augmented training, as well as adversarial training. These are the results for our partial ReLU model. So we present the clean accuracy, adversarial accuracy, and naturally perturbed accuracy for similar ReLU budgets. And we also compare our RLNet models to state-of-the-art linearized models. And we observe that not only do we improve adversarial and naturally perturbed accuracy by significant amounts, but we also attain an improvement in clean accuracy. And we are able to achieve ReLU reduction by 11.14x, which translates to latency improvements in private inference. To sum up, RLNet models achieve a triple win ticket of improved accuracy on clean, naturally perturbed, and adversarial images with over an order of magnitude ReLU reduction over baseline models. Here are the links to our paper and code. Thank you for your attention.
Thank you. So on the schedule next, I believe that we have a remote speaker for the paper presentation entitled Data-Free Defense of Black Box Models Against Adversarial.
Yeah. Can you hear me?
Yes. Could you please share your screen?
Yeah. Can you see my screen?
Yes. Please go ahead.
Yeah. Hello, everyone. Today I'm going to present our topic, data-free defense of black box models against adversarial attacks. My name is Gaurav, and this is a joint work with Inder, Ruchit, and Professor Anirban. So this is the overview of black box models. So generally the black box models, there the architecture details, the model weights, and even the training protocol that has been used for training is not accessible. And we are only given input and output predictions. In fact, to save the model security, the companies can even protect the data. For example, they may not release the data because of the privacy and security concerns. For example, Google GFT dataset is not publicly available. But still, in that case also, existing works have shown that due to data transferability, it is still possible to do adversarial attack using data-free model steering techniques. So our objective is to defend against adversarial attacks on the black box models, even in the absence of original data or even their statistics. So what I mean is that given a black box model, we want correct predictions, even on clean and adversarial image. So our motivation is that when we do wavelet decomposition, difference between the adversarial image and a clean image, we can see on the B that that most of the perturbed coefficients are the LL, HH, and HL components, while the LL components are least affected. And also, if we see that these LL components are high in magnitude. So based on that observation, what we do is the detailed coefficients that lies in the high frequency regions, as they are mostly highly corrupted by adversarial attacks, we tend to filter out these detailed coefficients and keep a limited number of them. But then removing them blindly can lead to decrease in the discriminability. So in order to do that, we train a regenerative network that can also generate these missing coefficients. So what I mean is our proposed approach has these two different components, wavelet noise remover and a regenerative network. So these two components are appended to a black box model in order to provide defense. So our wavelet noise remover, they remove the noise by only selecting the top tier coefficients after the wavelet decomposition, followed by the inverse discrete wavelet transfer. And the regenerative network is basically a unit network that trains the network in order to predict similar predictions on clean and adversarial image. So to show in more detail, our first step is to perform a model stealing given a black box model. We first try to generate the surrogate data and then obtain a surrogate model. In the next step, we use wavelet noise remover at a particular uh, interval of k value, which is given by our region of convergence. So where we select the top coefficients based on our wavelet coefficient selection module, and then the sample that we obtain is being passed to stage 3, where we pass it to our regenerator network, where the goal is to train the regenerator network using these 3 losses. For example, the first loss is the cosine similarity loss, where the goal is to maximize similarity between the generated data as well as the original synthetic data. We also apply this loss on the input space of the regenerated data, where our goal is to make similarity between the generated data and the original data for both the clean and adversarial sample. And then we also have a KL divergence loss that aligns the predictions between the regenerated synthetic data and its adversarial counterpart. So once we do the training, during testing, we append our wavelet noise remover and the regenerator network, and then pass the test data uh, where the wavelet decomposition is performed at our estimated K value. And then the generated data is passed to regenerator network, whose output is being passed to the black box model. And then we determine the clean and adversarial accuracy. So here are some ablations on the coefficient selection strategy, where we show that the high magnitude coefficients, specifically while taking the top k, gives better performance than bottom k and random k. Also, we determine what should be the value of k. So here, rate of change of coefficients are being plotted against the retail coefficients, and the value at which the rate of change of coefficients starts saturating, we take the value, and that gives us a good trade-off between the clean and adversarial accuracy. Here we can show that when we take a low k value, it gives good performance on the clean while it deteriorates performance on the adversarial, while the high k value gives good performance on clean but low performance on adversarial. So our k value that is being chosen gives a good trade-off between the clean and adversarial performance. Here we show that when we just have wavelet noise remover compared to without having that module leads to a good performance improvement. And then later on, when we also train our network with the regenerator network with a different combination of losses, the best performance is obtained when we have all the 3 losses combined. Finally, when we apply our both the components, it gives much better performance across different data sets and architectures. To conclude, this was the first time where we applied defense mechanism against a black box model, even in the absence of training data. And to do that, we proposed 2 different components, where the first component was a wavelet noise remover that removes the contaminated portions that can be mostly affected by the adversarial attacks. But removing these coefficients can also lead to decrease in discriminability. So retrieve these coefficients back, we have a regenerator network that helps to retrieve the information lost and improve the performance further. We showed the efficacy of these components via several ablations, and then our model contains these defense components that are appended to a black box model and provide significant robustness against the data-free black box attacks. Thank you, and for more details, please also visit our project website. Thank you.
Yeah, thank you. Next, we also have a remote speaker for the paper presentation entitled Fractals as Pre-training Datasets for Anomaly Detection and Localization. So for the authors online, please unmute yourself and share the screen.
Yes, I'm sharing the screen. Can you see my screen?
Not yet. Hold on 1 minute. Yes, we can see the screen right now. Please go ahead.
Okay. Okay, perfect. So good afternoon to everyone. My name is Cynthia Ugo, and I will speak about our work on fractals for anomaly detection. So anomaly detection is a crucial and challenging problem in computer vision, and have numerous applications like in healthcare, monitoring, autonomous driving, or industrial inspection, to name a few. However, anomalous data are rare and unpredictable. The nature of the effect highly depends on the specific application, and even if we have a knowledge about the dataset, predicting the type of defect remain challenging. So for this reason, in the literature, the anomaly detection problem is addressed as an unsupervised learning problem, where only anomaly-free images are used for training the deep model. However, obtaining the data is still expensive, time-consuming, and also privacy concern may limit the availability, in particular in industrial setting or also in medical application. So to solve this problem, many state-of-the-art methods rely on deep feature model that are pre-trained in a proxy task on a large-scale dataset. A very common method is to do classification of ImageNet, and these methods are called feature embedding based, where the idea is that a pre-trained model is used to extract features, and the target is to learn the distribution of anomaly-free features, anomaly-free samples, and usually in the training process, models is kept frozen most of the time, and ideally during inference, anomalous samples are detected as a deviation from the distribution of anomaly-free images, assuming that the feature extractor is able to discern between normal and anomalous samples. And in anomaly detection is quite challenging because normal and anomalous samples are semantically identical, but they differ in small local appearance. While recent work in anomaly detection mainly focus on the development of new framework built on such a structure, for the best of our knowledge, none of the anomaly detection method has focused more on the data used for the pre-training. Obviously, acquire large-scale data have different challenging. Apart from the high cost of acquiring the data and labeling, more recently, more questions have arisen related to the privacy, ownership, or inappropriate content or unfair biases. For example, Lion 5B dataset, which was used to train the famous Stable Diffusion model, was withdrawn due to severe ethical concern. So what if we have a way to harness the power of large-scale dataset, but without of the problem I just mentioned? Fractals comes to our help, and fractals are complex geometric structure generated by simple mathematical equation. So meaning that everyone can produce them, they are open source. We don't have cost because they're just generated from mathematical equation. We don't have a problem related to ethical or privacy concern. So fractals are generated by exploiting the affine iterator function system. So what we did was to generate different fractals and group them into classes. Then we train a model to do classification on these images. And in our work differ from the existing literature that focus mainly on fractal transfer learning ability on some real-world classification problem, because the classification setting are simpler than anomaly detection because we have to discern between semantically distinct classes, so the discrimination process is easier. In our case, instead, in an anomaly detection, more specifically in defect detection, as I said before, normal and anomalous samples are very similar. So we need also a network that is able to extract features that can discern even minor visual variation. So what we did, we trained 8 state-of-the-art anomaly detection methods using the pre-training fractals, and moreover, for all the method except one case, we didn't even fine-tune the network. The evaluation was performed in two famous benchmark datasets, which are MVTech and VISA. And for the classification and segmentation accuracy, we use a common metrics, which is the AUROC metric. So here you can see some qualitative and quantitative results. In the table, we have summarized all the performance for the different datasets, and we have highlighted in red the results for the best method with the pre-training with ImageNet, and in blue, the best method when using pre-training with fractals. On average, as you can see, the best method is PatchCore, which is a memory-based implementation. We also plotted the weights of the first convolution. And as you can see, the weights learned by fractal are very simple pattern with horizontal and vertical line, while ImageNetWare are more complex, meaning that our network probably is learning very basic features. Here on the left, you can see some predictions on some segmentation results, where in the red box, we have the segmentation result for ImageNet pre-training, and in the blue box, the result for fractal pre-training. So I would like to highlight this particular case of defects, because this case is called cable swap. So this type of defect is rather a position violation rather than simple defect. Usually in anomaly detection, the defects are more structural anomalies like scratches, dark spot, or stain. Here is this positional violation is rather as logical anomalies, and also both ImageNet and fractals underperforms because this is more related to the method rather than the type of weights used for training. Both the dataset, the benchmark dataset, MVTech and VISA are composed by different classes. So we group the classes into categories. For MVTech, we have 15 classes, and we follow the original benchmark grouping, which is texture category and object categories. And from the spider plot, we can see that the texture category, which is the blue area, is larger. So on average, the performance are better on texture. And instead, for VISA dataset, we categorize the classes into single instance, which it means that we have a single sample per image, multi-instance, where we have multiple sample per image, and printed circuit, which is in blue. And I would like to highlight the fact that for multi-instance, which is the red area, is not very clear here, the performance are the worst, but this is because the method used for training, this comparison are methods that are over-tuned and over-optimized on MVTech, which is a very common data set in anomaly detection. And MVTech has only images with a single sample per image. So this is also rather related to the method rather than the weights. Finally, we also compare the impact of feature hierarchy for two methods, which is PatchCore and PADIM, which are memory-based methods, and they work by creating a memory bank by extracting features from different hierarchies from the ResNet. And we know that the different hierarchies can have lower or higher level features. So we wanted to analyze the impact, and for ImageNet, which is the blue column, we see that the choice of hierarchies doesn't impact too much the performance, while for fractals, it's better to use low-level features. Moreover, we noticed that the classification accuracy, the performance gap between ImageNet and fractal for the classification is higher than the segmentation. So, in conclusion, we choose to focus on industrial defect detection because it's a very particular specialized area with is affected by the scarcity of data due to the privacy regularization. We observe that results highly depend on the type of defects. There were some cases where fractal pre-training were leaded to better results than ImageNet, but on average, it's clear that ImageNet is the winning approach. But what I would like to stress out the fact is that we use completely geometric structure generated with just mathematical equation, and we were able to have quite good performance. And future improvement could be, for example, work a little bit on the weights to improve the weights learned. Maybe try to work also on fine tuning, which is more in line with the fractal literature, and also maybe try to see the impact of fractal in supervised learning. So in particular in few shot learning. And yeah, hopefully we will see at the poster session, and these are some references, and thanks for the attention.
Yeah, let's thank the speaker, Cynthia, for her presentation. Next on the schedule, we have another remote presentation paper entitled Skip Plus, Skip the First Few Layers to Better Explain Vision Transformers. So for the authors, if you're online, please unmute yourself and share the screen.
Hello, do you have my voice?
Yes.
Okay, I will share
Yeah,
my
and
screen.
you look interesting.
Yes. Where is the share screen button?
We haven't seen your slides yet. Can you share your entire screen?
Yes. Let me. Are you seeing the
Yes,
slides?
we can see the slides right now. But please go ahead and present.
Okay. Let me close this windows. Okay. Okay. I want to present our Skip Plus paper today. I start by showing some qualitative results to motivate the paper. Then I'll go over the method. Finally, I'll show some highlights of the more important quantitative results. And then you can ask me any questions. If there is any more time, I will also go over our proposed Full-Grad Plus method, which is similar to our main proposed methods, but there is some slight difference. Okay, our proposed methods, Skip Plus and Plus, are designed to be composed with other attribution methods. Attribution methods are methods that show the contribution of each input feature to some target model output. For example, in the first row of this image, you can see an image of some zebras and an elephant fed to the model EVA large. And the target is set to the zebra logic before the softmax. We see that in these heat maps, the attributions for the different pixels, the more yellow a pixel, it means that it has had a more positive contribution and has increased the probability of this zebra class, while the more purple pixels have decreased the probability. As you can see, the vanilla versions of methods such as Decomplex and Full-Grad and GenAdd don't really show a very good performance. Their outputs are both very noisy and do not really highlight the correct class. But with our proposed Skip Plus method composed with them, both of these problems are improved. The noise is reduced a lot, and the correct class is highlighted more. In GenAdd, we have not shown its composition with our Skip Plus method because our methods do not really help GenAdd, but our quantitative results in the supplementary materials show that composing it with our method at least does not reduce its performance. Here is some qualitative examples of newer methods, which I call attention-based forward layer-wise relevance propagation methods. These methods usually use the attention width as their main component, but they also incorporate some other modules of the transformer to further increase the accuracy and faithfulness of their attribution maps. These methods usually produce different maps for each layer and use a method called rollout to differentiate, to aggregate these layers. But as you can see, they are not really very good. For example, on ALTI, we see that a lot of the times, all 0 attribution maps are produced, like the ones that I'm showing with my cursor. I don't know if you can see my cursor. Can you see my cursor?
Yes.
Yes, okay, thanks. You can see that ALTI has produced all 0 attribution maps for this image. This happens a lot for ALTI on this model. If you look in our qualitative examples in the supplementary materials, on some other models, this behavior actually happens to GlobInk, but while it no longer happens to ALTI. So overall, while I'm not completely sure why this behavior happens, rollout is not very stable. And it also has some bias towards highlighting contiguous regions, even if this is not actually what the model uses. For example, you can see the corners here are all highlighted. It's very noticeably contiguous. If you see in the supplementary materials, you can clearly see the pattern. But our plus and skip plus methods produce more meaningful heat maps. And you can compare especially between the complex skip plus and GenAdd, which is one of the strongest attribution methods on transformers. And the complex skip plus has less noise, and it seems to highlight more salient features of the image. Okay, you can find a lot of random and uncurated images of these methods for different models in the supplementary material, which I encourage you to check out. I now start going over the method. The first method, plus progressive layer unification through summation, is a very simple method. We take the underlying attribution map, which we want to compose it, and run this on the different layers of the model. Usually, each attribution map takes a start layer and its input and some target output and produces an attribution map. And we can set this start layer to any layer we want. Here you can see some qualitative examples of varying this start layer on this image. As you can see, when the start layer is set to the start of the network, the outputs of the attribution method decomplex are rather noisy, but from around the halfway point, the attribution maps look a lot better. We have also verified this phenomenon with some preliminary quantitative evaluations, which unfortunately I couldn't include in the paper, as the results were not on some other models rather than the ones that we use mainly during the paper. But even just using some later layer, such as this decomplex L7, has very strong performance. Okay, so in the plus method, we just sum the attribution maps that result by varying the start layer, and we use all the layers. This is the plus method. And in the skip plus method, we throw away the first half and only use the second half of the model. We can see the formulas here. If the model has L layers, we take L divided by 2 and start from that and go to the last layer and aggregate all the attribution maps. This concludes our method. Our methods are really simple, and while skip plus is completely novel, plus variants of different methods have been previously proposed, but they were always used on some specific method and never as a general method that can be composed with any other method, at least that I'm aware of. Here, we start looking at the quantitative results. I again encourage you to look at the paper and particularly supplementary material for quantitative results, as I only go over some highlights. In this plot, I have chosen between the vanilla variant, the plus variant, and the skip plus variant of each method, and only shown the best one to compare between different white box attribution methods. But I have also included the vanilla version of our strongest method, the complex skip plus. The complex skip plus is this green line here, and the vanilla version is this continuous gray line. As you can see, the complex skip plus both outperforms the other methods, even when composed with plus or skip plus. And it also significantly outperforms its vanilla the complex version. I don't go over these metrics here, but you can see descriptions of all of them in the paper. The metric hidden beyond this legend is deletion accuracy. This plot was on VIT base. Here you see the same thing for EVA large. The results are mostly the same. And here we see the results on Mura VIT. The Mura VIT is trained on the Mura medical dataset of X-ray images of chest scans. The previous two models were, of course, pre-trained and fine-tuned on ImageNet, as is common for vision transformers. Here we see some ablation studies of skipping different number of layers. As you can see, skipping exactly half the network seems to be optimal. And this even happens on EVA large, which has a different number of layers. As you can see, the normal VIT base has 12 layers, but EVA large has 24. But again, using the halfway point seems to be almost optimal. Okay, any questions?
Yep. Thank you for your presentation.
Okay. Is there time to go over Fulcrad Plus, or should I end the presentation?
So I assume that you have the delegate at the poster session, right? So our question can they can ask a question at the poster session.
Oh no, we don't actually have a delegate
okay.
there.
Then so then we can take some questions. If there's any, please let us know. Right.
Okay. Thank you.
Right. So thank you. So right. So next we have the keynote. Professor Lu Zhang, are you here online with us?
Yeah, I'm here.
Okay, great. So up there, microphone.
Okay, so I guess we are coming to the last part of the workshop. with a closing keynote talk. This was originally supposed to be given by Professor Ganming Liu, who is in a different time zone that did not work. So his collaborator, Dr. Lu Zhang, who is in incoming faculty at Indiana University, Indianapolis, will be filling in for him. They have been collaborating. So Dr. Lu Zhang is joining Indiana University, Indianapolis soon, and she has won the UTA College of Engineering Doctoral Dissertation Award and the MICCAI NIH Student Doctoral Dissertation Award and ICMA PhD Fellowship Award in 2023. And the talk is entitled Brain-Inspired Design of Vision Transformers. So go ahead, Sajjan, talk about your groundwork.
Yep. Professor Zhang, you can share your screen. Can you hear us?
Yeah, I can hear.
Great.
Can you see my screen?
Yes, we can. Please go ahead to for your talk. Thank you.
Okay. Thanks, Chair, for the kind introduction. And I'm Lu Zhang. In this August, I will join Indiana University, the Department of Computer Science, as an assistant professor. Today, I will present Brain-Inspired Vision Transformer. Actually, this presentation was originally supposed to be given by Dr. Tim Liu. Due to some matters, he cannot attend today, and I came to help with this talk. In the past 5 years, I have very close relationship with Dr. Liu on the topics, research topics about brain and AI. So today, I'm very honored to have the opportunities to introduce our group's work. In the past 15 years, our group have been dedicated to the discovery and the representation of brain architectures, including structural, connectional, functional, cognitive, and molecular architectures, primarily used in medical imaging and biological imaging data. Our working hypothesis is that human brain is one of the most intelligent organs in the universe. Its architecture has been highly optimized by millions of years of evolution, and the computational representation of its architecture can be used to inform and guide the design of artificial neural network in deep learning and artificial intelligence. And in the other hand, in AI domain, in the recent 1.5 years, AI has advanced to the era of generative AI and artificial general intelligence, or AGI. This new era is featured by the release of ChatGPT in late 2022, which has significantly impacted the entire AI domain and the society. Since then, many new general AI and AGI tools and the products have been released in a very fast pace, and they have changed our understanding of AI. My group and my collaborators have been closely monitoring, testing, and using these tools. Currently, the number of parameters of these large language models is close to or even exceeds the number of neurons in the human brain. Although these models have shown amazing performance in many tasks, current AI is still far from human level intelligence. Therefore, we hope to leverage the superior organizational principle in human brain to optimize and supervise the architecture of AI system and promote the development of AGI. This is the motivation of AI. Actually, for brain-inspired AI, I believe there are two important problems. The first one is whether it is possible. The second one is how to do it effectively. For the first problem, we can get some insights from the historical development of the two domains, the brain and AI. People in computer science should all be familiar with Alan Turing. In one of his papers, Turing asked, can machines think? So Turing machine is expected to imitate a brain. This was recognized as the beginning of AI. So from its very outset, AI has a very close relationship with brain. In 1960s, the invention of a light microscope allowed us to observe the microstructure inside the brain. and inspired by the organization of nervous cells. A simple model named perception was proposed in AI domain. It is expected to mimic the basic neuronal activity in brain. And then from 1960s to 1970s, the neuroscientists make breakthroughs in human visual cortex. They find that the whole visual cortex was divided into a group of hierarchically organized receptive fields. Different fields handle different input features, ranging from the simple features like edges and lines to the complex shapes and objects. And in AI domain, an important model, the convolutional neural network, they usually call it CNN, exactly follow the same design. CNN is composed of filters hierarchically organized in different layers to capture different features. And nowadays, transformer-based large language models are making waves worldwide. Actually, the beginning of this wave is this paper, Attention is All You Need, published in 2017. Attention is one of the core design in transformer and transformer-based large language models with the aim to use a limited computational resource to capture the most important features. Actually, attention is initially explored in psychology and neuroscience to understand human brain and mind. When our brain handles the information, it pays attention to the most important features rather than paying attention to all input informations for the information efficiency. So attention is an important mechanism in both systems. From this hierarchical development, we can say that some milestones during the development of AI domain, they have been inspired by the development of brain. So the two domains have a close relationship. And in addition, in recent years, there are also several pioneering works try to connecting the two domains, the biological neural network and artificial neural network. Among these works, one interesting work is this one published in the ICML 2020. In this paper, the author proposed a relational graph method that allows to represent any artificial neural network as a graph. And conversely, given any graph, it can generate a corresponding artificial neural network. By this way, the search of the optimal architecture of artificial neural network can be conducted by systematically examining the graph structures in the graph space. So in this figure, there is a graph space, right? Each graph in this graph space can generate one artificial neural network. So in this work, they examine a lot of graph structures and identified several top performing architectures. They compared the graph structures of these top performing artificial neural networks with the real biological neural networks. They find that they share some similarities about the graph structures. So this work provides a very good way for us to study the architecture of artificial neural network and compare the graph structures between the brain, between the biological neural network and artificial neural network. But in this work, they only examine the graph structures of MLP and CNN, the two types of models. For the most latest architecture transformer, it have the similar conclusion is still unknown. So to fill this gap, our group tried to extend the relational graph method to the transformer. In transformer, there are two different structures, the token mixer and the channel MLP. So we designed two different graphs to represent the two different architectures. By this way, the three major architectures in AI domain, the MLP, CNN, and the transformers, can all be represented as a graph in a unified graph space. We examined a lot of graph structures for MLP, CNN, and transformer, and identify some top performing architecture for the three different types of models. We compared the graph structures of these top performing architectures with the real biological neural networks, we find that the graph structures of transformer are close to the rat, cat, and macaque's brain, while the MLP and CNN-based models are similar to the Wang's neural network. Given the fact that currently the transformer-based models show more powerful performance in a lot of tasks, and the rat, cat, and macaque's brain are more advanced than Wang's neural network. So this result may indicate that models similar with more advanced biological neural networks perform better. So the most advanced human brain may be the best reference for us to design more efficient artificial neural network. And this work, together with the original relational graph work, provide a solid experimental foundation for us to further our study about brain-inspired AI. So in the next step, instead of this kind of post-hoc analysis, we try to borrow the rules from the brain into the artificial neural network to design more efficient AI models. In biological system, core periphery organization have been recognized as the foundation property in biological neural network to support the efficient information transmission. In core periphery organization, there are two different types of nodes, the core nodes and the periphery nodes. The core nodes are densely interconnected with each other, and the periphery nodes are sparsely connected to the core and among each other. In brain networks, previous study have shown that core periphery organization is also widely existed in brain networks, with a group of brain regions acting as core nodes play a very important role in the brain activities. So in our recent work, we also developed a novel twin transformer to study the functional connective patterns of the two major components of our brain, the gyri regions and the south side regions. We find the similar conclusion, that is the gyri and the south side are play the core and the periphery roles in the whole brain functional network. So based on these results, we believe core periphery organization is a good organization for us to design more efficient, intelligent system. In our recent work, we try to instill the core periphery organization to guide the redesign of vision transformer. In the regular vision transformer, the self-attention, all the patches are densely connected, forming a complete graph. In our work, we try to replace this kind of fully connected architecture by the core periphery graphs. So this is a very straightforward method. We just use our CP graph, the core periphery graph, to replace the original completed graph and propose a new architecture. We named it as the core periphery vision transformer. We call it CPVIT. So there is an interesting phenomenon, because in our in my previous slides, I introduced one work. We used designed a novel twin transformer to identify some rules in brain, and in this work we try to use the rule to improve the architecture. So this is the interesting about the research about brain and AI. I believe for the two domains, there is a bi-direction, not a single direction, for example, from brain to AI or from AI to brain. Actually, the two directions can work together. We can link the two domains and promote their mutual enhancement and development. So in this work, we used the 4 different datasets to evaluate the proposed CPVIT. For the first in-breast dataset, this is a medical imaging dataset. It covers the breast cancer images, and the other 3 datasets are the natural image datasets. For each dataset, we examine a lot of graph structures in the graph space and highlighted some top performing architectures by red crosses. in this figure, the regular VIT are located along the diagonal, and the other part are the architectures with the CP structures. We can find that for all 4 data sets, the top performing architectures are the ones with the CP architectures. We also compare the proposed CP VIT with the other state-of-the-art models, including CNN-based models and the regular VIT-based models. You can see that the proposed CP VIT achieves the best performance in for all the 4 data sets. In addition to the improvement of the classification performance, the proposed CP VIT also have the potential to improve the interpretability of the model. Because during the training process, some important image patches are assigned to the core nodes. We visualize these patches assigned to the core nodes to have a better understanding of the decision-making process inside the model. For the medical image data set, we can say that the core patches have a highly overlap with the IGAS map. The regions covered by the IGAS map are the important regions that the daughter are focusing on during the diagonal. So these regions have a close relationship with the disease. It means the core patches capture the most relevant features with the disease. And for the other 3 data sets, we can say that all these important patches have a highly relationship with the class labels. So this result indicates that the model can capture the features most related to the class labels, to the tasks. Actually, this work is just one attempt to the brain-inspired AI. This work, the promising results can give us more efficient about the first question, whether it is possible for brain-inspired AI. I believe it is possible. It is a very promising result, a promising direction to develop more efficient AI system. For the second question, how to do it effectively? Actually, this work just gave an initial attempt because currently we don't have a lot of methods to do it. We just try. It is the brain-inspired AI is just at the initial step. I believe in the future we can develop more efficient way to do that. But the brain-inspired AI is a promising direction. So in the future, I believe we can link the 2 domains, the brain and the AI, to study them together. Because the brain network is a very complex system, we need 2 powerful tools to analyze, to understand our brain, and AI system is such a tool. And for AI, I believe there are some good organizational principles of brain can inform and supervise AI development. So the 2 domains can link together and promote their mutual enhancement and development. So in the future, we will work toward developing a digital human brain that integrates both human intelligence and the AI system. This system can preserve human brains' efficient architectures, but implemented by the AI system. And we can, by this way, we can take the advantages of both systems, both the brain, human intelligence and artificial intelligence, while preserving human values. So in the future, in the future, I believe brain-inspired AI is a very good research directions. This is my current lab. This is a very warm family, and we still have some position for the PhD student welcome to apply. And in this August, I will also build my lab. And if you're interested about my research topic, also welcome to contact me. This is my current collaborators, and Dr. Tim Liu is one of my important collaborators. I graduated this May, and during my PhD, I have a lot of opportunity to attend some academic events, and I build some connection with other researchers and scholars, I welcome to contact me and collaborate with me together to do some interesting research. And this is my contact. Please, you can send me email and if you are interested to my research. Thank you.
Thank you, Professor Zhang, for your talk.
Thank you.
So whoever has a question, please come up to the podium to use microphone so that the Professor Zhang can hear the question.
Yeah.
Please.
Thanks for the great talk. I have a question about your methodology.
Mhm.
So you said in your vision transformer design,
Mhm.
the difference between the standard design and your CP method is that in the standard design, all patches interact with other patches, but in your methodology, you have a sparse interaction where each patch does not interact with all other patches, right?
Excuse me, cannot hear you clearly.
Yes, here, sorry.
Okay, I repeat my question. So you mentioned that in your CP methodology, each patch does not interact with all other patches, right?
Yeah.
And this is inspired by the brain architecture, but how do you decide with which patches each patch interact?
Okay, actually, there are only the core nodes can connected to other nodes. The periphery nodes only can connect to several of the nodes. This is different from the regular self-attention. How to decide which is the core, which is the periphery? Actually, currently we have two ways to do that. The first one is predefined. We just to use some fixed nodes to act as core nodes and others to act as periphery nodes. But the image patches are learned to assign to these core nodes. I mean, for the core nodes, which image patches are assigned to these core nodes are automatically learned by that. Another way is we can learn to decide which nodes are the core nodes, which are the periphery. But in this work, we only explore the first step. We just use a fixed CP graph. So in this graph, the core nodes are fixed. Yeah, the difference is the core nodes learn to capture some image patches, and this process is learned during the training process.
All right, got it. Thank you so much.
Thank you for your question.
All right, so let's thank the speaker, Professor Zhang, again.
Thank you.
Thanks so much. So, do you want to do the conclusion? Yeah.
So with that, I think our regular schedule is done. But please visit upstairs for the posters. There are probably some of the authors are still hosting their posters there. And definitely the success of the workshop depends on what you all submit next year. So we look forward to, assuming the CVPR approves our workshop again, we look forward to seeing all of your papers next time. Thank you all.
Thank you. And for the poster session, so the poster boards belonging to our workshop is number 206 to 224. So the poster session will be from 4:30 to 5:30. So please go upstairs to look at the poster. Thank you so much, and then hopefully see you next year.